Hey guys, welcome to this full course on stacks and queues in data structures. First, we will start with stacks, where we will be learning about basics of stacks, how to declare and use them, and we will also cover some of the applications where stacks can be used. You will also learn about syntax and semantics along with implementation of stack functions. After that, we will move on to queues in data structures. We will start with the basics of queues along with its applications. Then, we will move on to the implementation of queues using stacks and arrays. We will also come to queue using STL and BFS using queue, and finally, we'll wrap up with easy, medium, and hard problems along with their solutions using queues. So to get all the knowledge, watch the video till the end and make sure you subscribe to our channel and hit that bell icon so that you can never miss any notification from us. And also guys, if you have any query or any comments, you can put them in the comment section below and we will answer each and every question. So now let's get into the topic.
Let's talk about a very important topic called stacks and queues. Stacks and queues is one of the most important topic when it comes to computers programming. Recursion, for example, is based on stacks. Understanding stacks enables you to better understand how recursion works internally, and hence you can use it to optimize space of your program as well. It's extremely important for interviews. You can expect direct questions on stacks or queues. For example, if you want to find the maximum area under a histogram, you can do it using stack. The parentheses problem as well can be solved using stack. The sliding window problem can be solved using a queue. So these are important from an interview perspective. But having said that, it's also important for day-to-day activities as well. Why? You might have heard about Kafka or Redis queues. These are nothing but the data structure queue, right? At a massive distributed scale. So these are not just important in terms of an interview, these are also important in day-to-day activities as well. Hence, do not skip these topics.
Okay, so today we are going to cover stacks. So let me give you first a little introduction about stack. So first of all, the stack is very much important. It's the most favorite topic of the interviewers. Be well versed with this topic. Like first go through the basics, understand it because they are very straightforward, and then attempt as many questions as you can. There are some standard problems that you should definitely attempt. That was the gist about stacks. Now let's get started. Cool. So stack is very much similar to the stack of objects you see around yourself. So be it stack of plates, stack of books, so stack of plates, stack of books, then stack of, let's say, bowls. So you see it and use it every day, right? So let me draw the stack of plates. So this is how a stack of plates look like. Now from the stack of plate, you can insert a plate only from this end, that is top, right? You can only insert a plate on top, and you can only remove a plate from top. You cannot insert or remove a plate from in between because that will disturb all the plates, right? So you cannot do that. You can only remove and insert a plate only from top. So that's essentially the idea behind stack, that we can only insert an item from top and we can only remove an item from top. Okay, so conceptually or logically, you can think of a stack like this, where one end is open and three ends are closed. So from only this end, we are going to perform operations, that is to remove an item and to insert an item. As I was saying, that we can only insert an element from one end and remove an element from that end only, and therefore stack is known as lifo data structure. That is the last, as you can see the stack of plates over here. So this plate which was inserted at the very end will be the first one to come out. That is last in, first out. Okay, cool. So first what we are going to do, we are going to understand stack as an abstract data structure, that is ADT, abstract data structure. What do we mean by abstract data structure? In which the implementation details are hidden but the operations are given to us. Okay, so let me write it over here, that implementation hidden. Okay, it's not there, it's not given, but only the operations are there, only the operations are there with which, using which we can use the stack. Okay, so for example, you can see the fan on top of you, right? So you don't know how it's working internally. All you care about its operation, as in you put down the switch and it turns on, and you put off the switch and it turns off. That's what you care about. So that's an abstract. Cool. So we are given, let us understand the basic operations that are available with stack. Okay, so there are 4 basic operations. The first one, I am sure you guys, if you know about stack, you must know about all these operations. So that is push function, and then second is pop, the third is top, and the fourth is empty. Okay, so the push operation actually helps us to push an element on the top of stack. So this pushes an element on top of stack. Then here we have pop. So pop removes an element from top of stack. Then we have top, so it returns the element present on top of stack. So whatever element is present on top of stack, it just simply returns it. Okay, so don't worry, we are going to see an example over here. Is empty is the function that tells us if the stack is empty. So if the stack is empty, it returns true, else it returns false. Okay, so these are the 4 operations, that is push, pop, top, and is empty. Push pushes an element on top of stack, pop removes an element from top of stack, top tells what is on top of stack, and is empty returns true if stack is empty, else it returns false. Remember that pop simply removes an element and top does not remove an element. It simply tells what is present on top of stack. Is it clear now? Okay, so basically while performing a question, you will have to use in C++, let's say you can use STL, right? In STL you have stack. So in C++, you declare a stack like this. You can use a stack like this, and on this object basically you can call all these functions. So push x, then s.pop, and so on. Likewise in Java, you have collections using which you can use stack. So while attempting a question, you don't have to implement a stack of your own until and unless told. Okay, so but in a while we are also going to see how to implement a stack. We are going to actually implement these operations. Okay, cool. Okay, so let's actually see a dry run of these functions. So here this is a stack, and these are the operations that I would want to perform: push 2, push 1, push -1, push 5, then pop, pop is empty, top. So let's perform these functions. Okay, so it's push 2. So what we'll do, from where we'll put it? We'll put it from here. So basically 2 will come over here. Then it's push 1. So 1 will come over here. Then -1, -1 will come over here. Then there is 5, 5 will come over here. Then we are popping. So 5 will be gone, right? 5 will be gone. So we have removed 5. Now again pop is there. So -1 will be gone. So we have removed -1. Okay. Then we are checking, is the stack empty? What will it return? What will this return? It will return false, because the stack is not empty, right? The stack is not empty. Okay, so now there is top. So what will be the top function return? it will return whatever is present on top of stack. So basically top is pointing over here. So whatever is on top of stack, it will return that. So it will return 1, right? It will return 1. So that was a simple dry run of how can we use these operations. Okay, how these operations work. Now let us come to the applications of stack, which are very important. Applications of stack. So some of the applications are undo, redo. Then we have arithmetic expression, evaluation, right? Then we have recursion. So these are some of the, then we have string reversal and so on. So these are some of the applications of stack which are very important and you must know. So try to figure out that how a stack can be used in these operations. You know, that's an activity for you, that do try to search that how we can perform an undo, redo. So this is actually present in your browser, right? So whenever you go to any page, from any page and want to come back, so basically you store, for example, let me give you an example. So you are at link, let's say 1, then you go to link 2, then you go to link 3 and you want to come back to link 2. So what you can do, you can actually maintain a stack of them. So like first you are on link 1, you can put it on a stack, link 1. Then you are going to link 2. So put it on top of stack. Then you are going to link 3. Then put it on top of stack. Now you want to come back to link 2. So what you can do, you can simply remove this. And now you are back to link 2. Does that make sense? So likewise, you can also have a redo stack. Okay, so that's an activity for you, that how you can perform a redo operation. Okay, so likewise try to figure out. And we have arithmetic expression evaluation. So I think you all must be very much familiar with this. That is, you know, converting to infix to prefix or postfix, then evaluating the postfix notation. So that's where you can use stacks. Okay, and then you have recursion. Stack is a core of recursion. So you make function calls, and when you come back, so that basically those function calls get stored on top of stack. Okay, likewise string reversal. Okay, so there is another application that you may be using in your daily life. You must have seen this InShots app, right? So what happens in this, you are on this screen, okay, and so here I am actually at my feed. I am at my feed, okay, and I am watching this news. So I can only see another news if I remove it, if I remove this. So can you see that how this is an implementation of stack, right guys? Now let's talk about the implementation of stack. So could you guys tell me how can we implement a stack? So using arrays, second is using linked list. Okay, so how can we implement a stack using arrays? So basically, let's see. So we can have an array. So size of the array is, so array is A, and size of the array is 7. Okay, so what we can do, so let's say I want to push 2, push 3, push -1, pop, push 7, pop. Let's see how can we implement these operations using stack. Okay, so what we can do, basically we can actually enforce that one end of the stack will be there to perform all the operation. So you can imagine it like we are pushing the elements from here and removing the elements from here. So let's say I want to push 2, so 2 comes over here. Now you can also maintain a top variable which is right now pointing over here. That means what is on top of stack? 2 is on top of stack. Then we have push 3. So what we can do, we can simply increment this top variable and push 3 in here. Then push -1. So we can simply increment this top variable and push -1. Now how to pop it? How can we pop it? top minus minus. So basically we are now at index 1 and we have so basically minus 1 is gone. Okay, then we are at, so this was done, then we are at 7. So again we can increment the value of top and 7 comes over here. Now again pop's coming, so we can come over here and this is gone. So basically that's how we can operate a stack using arrays. Okay, and now can someone tell me the problem of stacks? So problems of stack are, which are very important if let's say an interviewer asks you to implement a stack using arrays or linked list. So if I talk about arrays, then we have problems, overflow and underflow. Let's say I want to push 1, 4, 0, 5, 6. These are the items that I would want to push. So 1 comes over here, then 4 comes over here, then 0 comes, then 5 comes, then 6 comes, and now I would also want to insert, let's say, minus 1. So as you can see, as I move my pointer forward, there is no space because array has a fixed space, right? So I cannot insert any more element, and that leads to the condition of overflow. Okay, and it's very important. So if interviewer has asked you, he's basically maybe judging you that will you cover these cases or not. Okay, so this is the thing. So how can you handle it? So basically here you have mentioned a size, right? You can keep a check that if size, so if top is equal to the size minus 1, so in that case that's an overflow. You cannot insert any more elements. So that's a drawback of arrays, and to overcome that, basically you can use something known as dynamic arrays. Okay, you can use something known as dynamic arrays. Okay, now let's say I want to pop, I am calling pop 7 times. Okay, so basically this is gone, third time, fourth time, fifth time, sixth time and seventh time, and now I am again calling. So now what will happen? Will I be able to pop any more element? No, I will not be able to pop any more element because the stack is empty. So if I attempt to do so, that will lead to underflow condition. So how can you make it all right? Basically, you can put a check that if top, so if top is equal to, let's say, minus 1, then print underflow. Okay, and simply return. So that's how you can manage underflow and overflow condition. Does that make sense, guys? Underflow is when you are trying to pop an element when there doesn't exist. When you are popping an element when there is no element. So how will you be able to pop? Will you be able to pop? No, right? So that's the case of underflow. So you can manage the case of underflow by checking that if top is equal to minus 1, that means you have no element. So you simply print underflow and return. Cool. So let's talk about linked list. So in linked list, what you can do is, so you have nodes in linked list where this is the data part and this is the address part. So basically the nodes of the linked list can be present anywhere in the memory, right? Like array, you don't have everything in a contiguous manner. Everything is scattered. Every node is scattered in linked list. Basically, if you have this as a memory, so if let's say one node is present over here, another node can be present over here. Okay, third node can be present over here. So basically this address field actually links node. So basically this will be linked to, let's say, this, then this is getting linked to this and so on. That's how we store data in linked list. So basically let's say you have 2 and 1 right now. Then you want to insert, you want to push, let's say, 7. So how you can do? Right now top is here. So at what position, if you so you are actually, remember, you are actually implementing stack using linked list. Where would you want to insert this node? This is your linked list. This is what you are building. This is the temp node, current node, that you new node that you want to insert into your linked list. So where will you insert it? That we can actually put it on top of head. So now we can actually make this its next pointer point over here. So this is how our stack would look like. Now top will be over here. Okay? So you can, in case of a linked list, you can imagine a stack like this. Like this it's growing, right? Like this is it's growing. And when you want to pop an element, so basically you can actually shift this top to the next position, and this will be, so basically you can free up this space. Okay? So that's how you can implement a stack using linked list. Now with linked list, the cons is of space. A lot of space is used in linked list. Okay, so basically you are storing pointers as well, that will take a lot of space. And pros of both stack and cons is that you will be able to perform push and pop operation in just order of one time complexity. Okay, in just order of one time complexity. Okay, cool. Let's get to the question. Okay, so the first question that we have is of very much famous question and very much asked question. It's of valid parenthesis. Okay, valid parenthesis. So the question says that you are given brackets, the round brackets, okay, and you have to tell whether the parentheses are balanced or not. Let's say you are building this compiler in which you will be writing your code, right? So basically you will be you want your compiler to check, verify your code. So in that case you will definitely want how can we check if the bracket are valid or not. So how can we do that? Let's see. First of all, let me give you some examples. Let me write down the examples. Okay, so what do you say about the very first parenthesis? What do you say about the very first parenthesis? Are these set balanced? Is it balanced? Yes, it is balanced because a corresponding opening bracket has a corresponding closing bracket. So yes, it's balanced. Then if I talk about this, is it balanced? No, it's not, because this is complete. They are balanced, but here this opening parenthesis is lacking a closing parenthesis, or you can also say that this parenthesis is lacking a closing parenthesis. So this is not balanced. This is not balanced. Likewise for this, so this is lacking an opening bracket, or you can also say that this is lacking an opening bracket. So this is also not balanced. Okay, so you have to basically tell, are the parentheses balanced or not? Let's say we want to attempt this question without stack. Can anyone think of something? Okay, so let me first actually put some observations. Let's do the question step by step. Okay, let's do the question step by step. So observations are, the first observation is that, can an opening bracket make a string invalid? As in, let's say I'm traversing the string and I find an opening bracket. So can that opening bracket make the string invalid? Well, it depends upon the future. It depends upon the future, that if I have this opening bracket, maybe in future I'll find a closing bracket and that will be valid. Or let's say I don't find a corresponding closing bracket, in that case it will be invalid. So it totally depends. It totally depends if I get an opening bracket. Okay. Now if I talk about a closing bracket, so what about a closing bracket? Can a closing bracket be a problem to us if we encounter it? Well, so if till now for a closing bracket there was no opening bracket, in that case, yes, it is a problem, because even if we move any further, the string that is given to us will not be valid in any case, right? In any case. So basically, let's actually okay, let's take look at it like this. So I have something like this. So what will happen? Let it be like this. So I am at here. I will maintain, what I can do, I can maintain a left and right count, which can be initialized to 0. Now I am at an opening bracket. So that means left actually tells a opening bracket and right tells the count of a closing bracket. So I found an opening bracket. This becomes 1. And so let this be the thing. Let this be the bracket. Now I am here. Now I am here. So what I can do? I can simply decrement the value of this, and that will tell us that we actually found a match for an opening bracket. We actually found a match for an opening bracket, so we can actually set this to 0. Right. Now let's say I have a string like this. What will happen? What will happen? That I am here, left and right. So basically I have left 1, then I have a closing bracket. So initially both are 0. So now this is a closing bracket. So is left greater than 0? Yes, it is. That means there is an opening bracket. So we can simply decrement it, telling that we have found a match. Now next we go to the next character. This is a closing bracket. Okay. So what's the value of left? It's 0. That means there's no opening bracket. In that case, we will simply return that it's invalid, because at this point there is no use to move any forward, because this closing bracket does not have a matching opening bracket. So we can simply return from here. Does that make sense to everyone? Okay, so whosoever is saying that can we count the number of opening bracket and the closing bracket? Guys, we cannot simply count the number of closing bracket or opening bracket. Okay, let's take an example of that. Let's say I have this as a string. So now left is equal to 2, right is equal to 2. But are they valid? Are they valid? No, they are not valid, because they are not placed in the correct order. Therefore, this is not a right approach. Is that cool? The time complexity of the approach is what? What's the time complexity of the approach? So if we have this case, here the number of opening brackets, closing brackets are 2, number of opening brackets are 2. So are they valid? No, they are not valid. So this is wrong. This way is wrong. So what's the time complexity, guys? Time complexity is just order of length of the string, because we are iterating the string just once. And what's the space complexity? Just order of 1. We have not used any space. Okay, we have not used any space. Now let me make a question little trickier. Now let's say I have brackets these and these. So this is an extension of the question. Extension hai ye question ka. Now I am saying that I have these 3 sets of parentheses. Now I have to tell, basically my string can contain these set. So I have to tell if those are valid or not. Let's take an example. Examples can be this, then we have this. So this will be given to you. Now you have to tell, are they valid or not? Now can you, how can you do it? How can you do it? So whenever in the interview you're telling the interviewer that okay, we can use stack for this, but she or he already knows, right? You have to get to it. Like how? What's the intuition? So that's is very important. Okay. Some of you are saying that we can use 3 variables. So that will be wrong, because then you won't be able to actually find the order. You cannot judge the order by taking that many variables. So first of all, I am sure that you guys understand that it cannot happen by taking just the left count and the right count, because if okay, so first of all, let's take the example of this. Now here left is 1, okay, and now I find a closing bracket, but here they are not same, right? So this will not work. Having left and right is a bad idea. Now taking 3 variables. So here I have this string. So if I take 3 variables, let's say round, or let me write first bracket, second bracket, third bracket. Now here the first type. So this is type 1, type 2, type 3. First bracket ka left, right, iska left, right, then iska left, right. First ka left is 1, okay. Third ka left is 1, okay. First ka right, so we have found a right bracket and this manages to be 0. Then we have third ka right, so this becomes 0. But is this valid? No, it's not valid, because the order is different. Order doesn't match. So therefore, that's a bad choice. Does that make sense? You should have a clear idea that why your approach is wrong. You should take as many, is like if you are stuck, you are not able to think, take examples and try to generalize it. You guys are clear with it? Cool. So let's move forward. Now let's actually build some intuition of this. So one thing is that let's consider these bracket. One thing is that so this is invalid, right? This is invalid. This is also invalid, right? This is also invalid. This is valid. This is valid. They have right set of pairs. Now this is also, this is what? This is what? This is also valid. Okay. This is also, as you can see, that this is also valid. So if I talk about this string, then it's a property of the valid parenthesis that if the complete parentheses are balanced, then their sub parenthesis will also be balanced. As you can see that this is balanced, this is also balanced, this is also balanced. So we are not considering all the substrings, right? We cannot consider anything like this or something. We have to choose the right set. But what it means is that whatever the parentheses are inside it, they will be balanced anyhow. So this is its corresponding pair. Then we have this, it's correct, then it's correct, then this is there. So does that make sense? That inside of it parentheses are balanced? Now, so an opening bracket does not bother us, right? An opening bracket does not bother us because in future we may find a closing bracket for it, right? But let's suppose I am at this closing bracket. Let's suppose I am done with everything and I am at this closing bracket. Now for this closing bracket, this is an opening bracket, this is an opening bracket. Does these brackets are of any use to me? No, they are not. Can I get rid of them? Then that will be great, right? So if I can get rid of them, because they are valid in itself, right? As I told you by this property. So since they are valid, if I can get rid of them, then I can actually find out if this bracket has a matching opening bracket. Okay. So let's actually see a dry run of this using stack, because stack is the data structure that helps us find. Just look at just the past. Okay. Just the past. So how and what we can do? We are at this bracket. This is an opening bracket. We'll see about it in future. So push it onto the stack. Then this is an opening bracket. We'll see about it in future. Put it on top of stack. Again an opening bracket. Put it on top of stack. This is a closing bracket. Was there an opening bracket for this? Yes. Where can I see? I can see it on top of stack. If there is a corresponding match for this closing bracket, then I can simply pop it off. Next time here. This is a closing bracket. Does this have a match? And see how nicely we have removed between whatever was presented. That is here, we have removed it. We have removed it. And now we are actually comparing this. Where can we find it? On top of stack. So yes, it has a match. Remove it. So now we are here. Now we are here. Put it. So this is our closing bracket. Yes, match found. So remove it. Remove it from top of stack. Then we have an opening bracket. Push it on top of stack. Okay. Then we have a closing bracket. Is the corresponding opening bracket present? Yes, it is present. Remove it from top of stack. Now we are at the last bracket. Is the corresponding opening bracket present? See here how we have gotten rid of all of this, right? So basically, yes, it's present. From where we can find? On top of stack. Just remove it. What's the condition we have to check for validity? That if the stack is empty, then return true, right? If the stack is empty, return true. But if the stack is not empty, so we have to return false. That tells, even after iterating the string, let's say we have completely iterated the string, even if the stack is not empty, so we will have to return false, right? Because there are still left some unmatched opening brackets. So at any time, let's say you have something like this. So at any time you don't find, so okay, let's do a dry run of this as well. So this is an opening bracket, move ahead, opening bracket, move ahead, closing bracket, but no corresponding match. Simply return from here. Simply return from here. Okay, so now let's move on to the next question. But before that, let's talk about the time complexity. The time complexity of this approach is just order of n, because we are going to each and every bracket not more than twice. How? Once while pushing it and another time while popping it. So that's only 2 into n, which makes it order of n, right? That makes it order of n. And the space complexity is order of n, because in the worst case we may end up pushing all the brackets in the stack when, let's say, the string was something like this. In that case you will end up pushing all the brackets in the stack. So the space complexity is order of n. Okay, so I hope that's clear, and we'll quickly move on to our next question. So intuition is that how can we, previously clear up something to get just the, so here as I talked about that step by step we made the intuition, like, sorry, I just removed it. So as I was talking about that, inside of it will also be, balance. So if we can remove it, I will just be able to look at here. That's what I want to do. So we can simply remove it, and that is possible using stack. Okay, so let's move forward quickly. Cool. So question 2, and this is very, very famous question, which is of next greater element. Okay, so question is that, let's suppose you are given an element, you are given the elements in an array. Let's suppose 10, 13, 22, 7. For each of these elements, you have to tell that what is the next greater element to its right, just the next greater element to its right. So what's the next greater element to the right of 10? It's 13. Okay, it's 13. The next greater element for 13, it's 22. The next, is there any next greater element for 22? No, it's not. So we can put -1 over here. We can put -1 over here. Then we have 7. So next greater of 7 to right of it, it's -1. Nothing is there. Nothing is there. Okay, so let me take, this was example 1. Let me take another example as well. So we have 10, 7, 4, 2, 9, 10, 11, 3, 2. Okay, so what's the next right to the right of 10? It's 11, right? Just greater element on the right of 10. It's 11. Just greater element on the right of 7. It's 9. It's 9. Just greater element to the right of 4. 9 again. To the right of 2. 9. Just to the right of 9. It's 10. Just to the right of 10. 11. Just to the right of 11. Nothing. To the right of 3. Nothing. To the right of 2. Nothing. Okay? Okay, cool. See, if you are implementing any question, you can use STL in C++ or collections in Java. You don't have to implement push pop functions on your own. That's just for the sake of, if let's say your interviewer asks you. That's it. Okay, that's it. Cool. So if the question is clear, please tell me that how can we attempt it. At least give me the brute force approach. At least give me the brute force approach. So you will agree with me that brute force is nothing. So brute force is using 2 loops. So you can basically, let me actually write the code for it as well. So the brute force look like that. You can have an answer variable, answer array. Then you can iterate through all the elements from 0 to n-1. Then for those elements, you can again iterate from. So, okay, first you can initialize your result to -1 if let's say you don't find any element. So you can do for j that goes from I plus 1 to n-1. You can check if a of I is, so a of I is less than a of j, then simply put answer I is equal to aj, okay, and break from here. Take a break from here, because you just have to find just the larger element. You don't have to iterate any further. Okay. Now what do you have to do? Actually, This should be result, and out of this for loop you can set answer I is equal to result. Does that make sense? This is just the brute force approach. Okay, cool. Let's go ahead. So the time complexity of this approach is order of n square, since there are two nested for loops, and the space complexity would be order of n, which we can ignore because that will be just to store the, so basically this is just so we can actually make it order of 1 only, because we anyway have to take an answer array. Answer array we anyway have to take because that's how we are going to return the answer. So the space complexity for this we can assume to be order of 1, right? Cool. Now let's talk about the optimized approach and let's build some intuition for that. Let's see some observation. The first observation is that let's suppose the array elements are 12, 10, 9, 8, 7. Okay? 0, 1, 2, 3, 4. If let's suppose these were the elements, what is going to be the answer for them? What's going to be the answer for 12? Minus 1. Nothing is on right. For this, minus 1. For this, minus 1. Minus 1. Minus 1. Does that make sense? The answer for all of them will be minus 1. Now let's talk about another example. Let's say we have 5, 4, 3, 2 and 10. Now can someone tell me what is going to be the answer for 5 now? For 5 it's going to be 10. For 4 it's going to be 10. 3, 10, 2, 10, 10 minus 1. Does that make sense, guys? Cool. So the thing is that as you can see, when the sequence was in decreasing order, we got minus 1 for them. And here we also had a sequence in decreasing order, but once we got an element which was greater than them, so this element was greater than these elements, so the answer for them became 10. The answer for them became 10. Look at it like this. So let's suppose I have 5, 4, 3, 2, 10. So I start from here. This is 5, then this is 4, this is 3, this is 2. Now 10 came. So once the number came which was out of order and greater than them, so answer for them became 10. Okay, answer for them became 10. Let's look at one more example. We have 9, 6, 5, 4, 8. So this is 9, this is 6, this is 5, 4, then 8 came. So 8 is 8 to whichever element it is greater, it will become the answer to them. That is here. So this is 9, this is 6, this is 5, this is 4, this is 8. So 8 will become the answer for 6, 5 and 4. Okay? So basically now once we have got the answer for them, can I just ignore this and start by finding the answer for these now? Does that make sense? Does that make sense? Okay, giving you some intuition that here we are also ignoring whatever was redundant from the past. The idea here is that we have a monotonic sequence. We have a monotonic sequence over here. Monotonic sequence is when we have a decreasing or increasing sequence. So my point is that I had a decreasing sequence. Once I find an element out of order, so all the elements which are smaller to this will be the answer for them. This will be the answer for them. Okay? Now, so basically, let's say I have elements 11, 4, 3, 2, 10, 12. So I have 11, then I have 4, then I have 3, 2, 11, 4, 3, 2. Now 10 comes. Now 10 comes. So 10 is greater than these numbers. So answer for these will be 10. Answer for these will be 10. Now since we have got the answer for them, we can actually remove this. We can actually remove this, and now it will become such a sequence. It will become such a sequence. Now 12 comes. So this will come over here. Now whatever is smaller than answer to them, 12 will become the answer. So 12 will come over here and 12 will come over here. Now only. So we have got the answer for them. So we will remove it. And now we are just left with 12. We have completely iterated the array. And whatever we are left with, to them the answer will be -1. Okay, so since we are ignoring whatever is redundant to us previously, and since this is a monotonic sequence, therefore stack will help us over here. So let's see the dry run using stack. So intuition was that we had to look at the just past, removing this just past. So whatever answer we had got, we will just ignore them, and now we'll start again from some monotonic sequence like we did over here, over above, right? Okay, so now let us go through the dry run using stack. Then again, if you guys will have some doubt, we will come to those. Okay, so I have 11, put it onto the stack. So 11 has been put onto the stack. Then we have 4, put it onto the stack. Then we have 3, put it on top of stack. Then we have 2, put it on top of stack. Then we have 10. Now this, you can see that this is a decreasing order. This is a decreasing order. Now we found an element out of order. So to whatever elements 10 is greater, the answer for them will become 10. So is 10 greater than 2? Yes. So we found the answer for 2. Answer for 2 is 10. Remove it. Is 10 greater than 3? Yes. We found the answer for 3. The answer for 3 becomes 10. Remove it. Now is 10 greater than 4? Yes. So we found the answer for 4. The answer for 4 becomes 10 and simply remove it. Now is 10 greater than 11? No. So simply push 10 onto the top of stack and move ahead. Now we are at 12. So on top of stack there is 10. 10 is lesser than 12. So answer for 10 will become 12, right? Answer for 10 will become 12. Now, so we are at 12. Is 12 greater than 11? Yes. So answer for 11 becomes 12. Okay? So now nothing is there. Simply insert 12 on top of stack. Now move ahead. So we are done. We are left with no more elements. So whatever is present on top of stack, the answer for them will become -1. So in this case, answer for 12 is -1. Guys, does that make sense? So Anshul says that then in this solution, we need to also store index and stack. Anshul, that's what we are going to do. We actually need to store indexes on top of stack because we actually are trying to find the answer for the previous elements that we are done with. So let me quickly show you a dry run of how we can do this using indexes. Okay. So we are having the stack. We will place 0 over here. Then we will place 1, right? Then we will place 2. Then we will place 3. So basically still the array is in decreasing order. Now we found 10. So this 10 is greater than what is present on top of stack. So basically answer for this. So we will write it like this. S dot top. Okay? Because this is the index. So A of 3 is nothing but 2. So 10 is greater than 2. Answer for this has become 10. Then likewise, answer for this will become 10. Element at index 1 is 4, which is lesser than 10. Answer for this becomes 10. Now 11 is not smaller than 10. So we will simply push the index of 10, which is 4. Then we are here. Now this is 12. 12 is greater than A of S dot top. So we will simply mark the answer of A of 4 as 12. So this is 12. Again, so as we remove it, then A of 0 is lesser than 12. Answer for A of 0, that is 11, will be 12. And now whatever is present on stack, whatever is present in stack, you will simply mark their answer as -1. So you will put -1 here. And the time complexity of this approach is order of n. Since we are putting an element and removing an element just twice, so again order of 2 into n, which is nothing but n. And space complexity in the worst case can be, when let's say the complete array is in decreasing order, it will be order of n. So does that make sense to everyone? Okay guys, so we have actually placed the link to the questions for the next questions. Okay, so hope you guys try it, and guys, this was it. I hope you enjoyed it. Cool. Please try them. See ya. Bye bye.
Hey everyone, in this lesson we will discuss logical view or abstract view of queue data structure. Basically, when we talk about abstraction, we don't go over implementation details. We generally discuss about features and operations. In actual practice, queue is a structure in which whatever goes in first comes out first. So in general, queue is a FIFO structure. Whatever goes first, it should goes out first. So if we want to construct queue as a data structure, then we need to support both insertion as well as deletion in the queue. In queue, as we need to maintain FIFO property, so both removal as well as insertion should happen from different end. It means if insertion happens in the front, then deletion should happen from the end and vice versa. Let's take an example to understand this thing. Let's say this is the snapshot of the queue at some particular time. Let's say this is the snapshot of the queue. And this is the front element of the queue and this is the last element of the queue, or we can say as rear element of the queue. Now, so as we can see here that if we want to make an insertion, it should happen at the end of the queue, which we call as the rear or tail of the queue. Likewise, deletion should happen from the start of the queue, which we call front of the queue. As if I want to delete some element, it should be even because this element entered first into the queue. And if I want to insert some element, it should insert here. So this is the snapshot of a queue at some particular time. Okay, so what we have seen here, queue as a abstract data structure, a list or collection with the restriction that insertion can be performed at one end, that is the rear of the queue, and deletion can be performed at other end, that we can say here as the front of the queue. Let's discuss operations in the queue now. If we want to create a queue, what sort of operations that we need to support? The first operation is insertion, which we call enqueue in the terms of a queue, or we can also say it as push operation. We need to push an element into the queue. And also one other operation that we need to support, that is the dequeue, where we need to remove one element from the queue or pop an element from the queue. Now, if I want to create an interface for the queue, how it will be like? Let's discuss about that. If I want to create an interface for the queue, it will be something like I need to support these functions. The first function is enqueue, which supports insertion. And the second operation is dequeue. And here I am assuming that queue is maintaining integer elements, but it can be of any type. Okay, and the dequeue operation means delete an element from the queue, and where this return type symbolizes the element that I deleted. It solely depends upon the implementation that whether we want to return that element or not. We can keep it as void as well. That depends upon the implementation. Also, what sort of other things that we may need from the queue? That what is the element which is present at the front, or we can say it as peak. Is my queue empty or not? So these sort of operations that I may need in order to implement a queue. So what we can say that in high level terms, these sort of operations that we need to figure out in order to implement queue. And most of the languages has an inbuilt library which provides the interface, which may vary from language to language. And as a developer, we don't need to worry about the implementation details, and we can create a queue data structures with the help of available functions. As we have seen here that the operations can be enqueue, dequeue, front is empty. Now what we can say also as queue as a container which is open from both ends. As we have seen here that we are entering an element from this side and removing an element from this side. So it is actually an open container where element goes in from one end and element removes from other end. Now, let's say we have this operation available in the library. Let's try to simulate queue. Okay, let's say in the starting we have an empty queue and we need to insert an element 2 into the queue. That means as we have a library, so then we can simply call enqueue function of that library and we can insert 2 in our queue. So when we insert 2, it will come from here. Fine. So now, as we know that we need to maintain 2 pointers or 2 variables which keeps track of which is my front element as well as which is my rear element. so that the implementation becomes easy. But so if we have only one element in the queue, then both front and rear pointing to 2. Fine. Now let's say we are inserting one more element into the queue, that is 5, and it will go from the rear side, from this side. Now we need to update our front and rear. Let's say internally the library, it's handling all those things. Now the rear reaches here and front remains here. Now let's say we have one more operation. Let's say somebody asks one more operation to insert 3 into the queue. Then the snapshot of the queue will be something like this, where the rear is pointing here and front is pointing here. Now let's say somebody asked us to dequeue an element, that means delete an element. As we know that deletion occurs from other end, from this opening of the container. So then our front got updated to 5 and the rear will be 3. So now we have done the simulation part and we have seen and the queue in a high level way actually. Now let's discuss some real world examples to understand it better. And it is generally used when there is a shared resource that's supposed to serve some request, and resource can handle one request at one time. In such scenarios, it makes more sense to queue up the request and the request that comes first serves first. Let's consider an example. Let's say we have a printer that is being shared across the network and it can print only one document at a time. When more than one request comes to it, it cannot say that I cannot serve your request. So what printer will do? It will maintain a queue of requests and serves them one by one as long as there is a request in a queue. It will keep picking up the request one by one. Let's say we have a printer and all these computers, they are requesting to the printer for the request to print a document, but the printer can only print one document at a time. So what the printer will do, it will maintain a queue and store all the requests into the queue. And what it will do now, after serving a request, it will pick an element from the front of the queue and serve that request. In this way, it will manage everything. So this is one of the real world scenario where we can use queue. This is good for the introduction part of the queue. In the next lesson, we will see how we can implement queue. Thanks.
Hey everyone, as you can see here that we have already maintained the 8-day streak and we need to maintain a streak. So in today's class, I think we will solve some of the questions of stack and queues. Proceed at that level. Let's solve some questions. Okay, let's solve the very first question. The question is, let's say all 3 questions of this clever stack. Okay, let's start the question. We have been given an array and in that array, we need to find the nearest smaller element gi for every element ai in the array such that the element has an index smaller than I. Okay, let's say we have more boundary, gi is the element aj is j is greater than I. Okay, the basic question is, for each particular element in the array, we need to figure out the nearest smaller element for that particular element in the array. Okay, let's say this is our array. And for 4, as we can see that no element is less than 4 in the left side. So we have g1 is equal to -1. So for 5, as we can see that the minimum most element for 5 in the left side is 4. So our answer will be 4 for this case. Now if I can see for 2, okay, both 4 and 5 are greater than 2. So for 2 as well, I can see that there is no minimum element in the left hand side. So -1 will be for this as well. Now, okay, similarly, okay, now let's try to solve this question. Okay, how I can solve this question? Let's first think. Okay, for each element, if I do in a brute force way, what I need to do, I will just iterate over all the elements in the left hand side and I just figured out whether there is an element which is lesser than that particular element. If I figure out that element, then I found the answer. In that way, I can proceed. Let's first copy this example. Okay, now what we can do, how we can solve this question, let's see. Okay, let's say, let's start from the end. Fine. Okay, let's say in the initially we have an element 8 only. Okay, now as I move ahead, I just found an element 10, and I know that that element is greater than that element. So I haven't find the answer for 8 as well as 10 yet. So what I can do? Okay, now I just figured out 2. Okay, one thing that is clear to me that 2 is smaller than 8 as well as 10. So okay, so one thing for sure that I can say that 2 will be the answer for both 8 and 10. Okay, so what I can do, I can update my answers and I just need this data point only because I already figured out the answer for this. So I just need to maintain 2 only. Now let's say I just go into the other element. I have 5. Okay, if I found 5, when I have 2 to which I need to figure out the answer. For 2, I know that 5 won't be the answer. So I haven't found the answer for 2 as well as 5. Now I figured out 4. Now I figured out 4. I can say that, okay, 4 is lesser than 5. So for 5, 4 definitely will be the answer. For sure. But for 2, it won't be the answer. So after then, I need to store these 2 points. Isn't it? So the way if I will do in that way, I will figure out the answer. So what I just think, okay, I am appending the elements, and as I'm appending the elements, I'm checking. And if I need to check the element, what I'm doing, I am just first checking for the last element and then the second last element, and I'm doing in that way, and I'm able to solve this question. If I'm able to do in that way, then it's easy to solve. So I need some sort of data structure which helps me to maintain this information. And that data structure should be something like where I can add the element in the end such that I can also remove the element which I just added in the end. So it should be last in, last out. And we know that stack is that data structure which provides that sort of thing. So I can use stack here and just try to solve in that way. I am able to achieve because what I am doing, I am adding an element in the stack, and when I just found an element which is lesser, what I am doing, I am just checking with all the elements in this stack, and if I figured out an element which is greater than that element, I'm just removing it to the stack. So only I am adding an element one time into this stack, and I also am removing from this stack only one time. So that means it's kind of order of an algorithm that we just achieved. Okay, let's try to think how we can write code for this question. Okay, let's write the code. Okay, let's try think what are the constraints that we have been given. Okay, we have not been given any constraint, and the thing is, if we haven't find an answer for any element, we need to return -1 for that particular case. Okay, let me first, what I can do, let me first figure out the size. Okay, let me create my answer which is of size n, and let me have the default value as -1 for each particular element in that particular array because we haven't find the answer, and we will follow the algorithm as I discussed here so that we will be able to achieve our solution in order of n time. Okay, let's try to think, okay, how I can do that. We just need to iterate. In the last element, I need to move till the first element. In that way, I need a stack data structure to maintain the information as I just discussed. Why? Okay, so now what I can do if I need to question, okay, one thing I need to be sure that, but what will be the edge case? If my stack is empty, or if I have my element which is at the top of my stack, okay, if I figured out an element, okay, which is greater than my top, then that means I haven't found the answer for both of the elements. So I need this data. So I need to push that element into my stack. If that is the case, if that is greater than, that is element is greater than or equal to my that element, so I need to push that element into my stack. Isn't it? Okay, now I'm done here. So I can no, okay. If there is other case, if the element at my top is greater than AI, if that is the case, then I need to check for how many elements I have found the answer. So let's first just check the edge case, whether my stack is empty or not. While my stack is not empty and my top element in the stack is greater than AI, in that case, what I can do, I know that answer for stack dot top will be equal to AI for sure. है ना? And I can safely remove that element because I just figured out the answer for the topmost element in this stack. Now I need not need this data in the future, so I can safely remove it. By the time this thing gets ended, I can say that okay, now I'm done. Now I can safely add the ith element because I haven't found the answer for ith element yet. And in the end, what I can do, I can return my answer. And let's check once again whether I'm doing in the right direction or not. I am maintaining my answer, and I just created an empty stack, and I'm checking if my stack is empty or if it is greater. So then I need to push that element into this because it's of no use. Otherwise, I need to check if my element is lesser. So that means for that topmost element, I just figured out the answer. So what I need to do, okay, in that way, if I just do in that fashion, I can solve. Okay, that seems like a good approach. Let me test. Okay, it's giving me correct answer. So let's submit. Oh, nice. Nice. We have solved this question. Now let's move to the next question. Okay. What will be my next question? Okay, now the next question is I need to figure out the largest rectangle in the histogram. Okay, that is my question. Let me think. Okay, let me first read the question. We have been given an array of integers a of size n where a represents a histogram. That is, ai denotes height of ith histogram bar and width of each bar is 1. Okay, let's say we have been given this histogram and where the height of first bar is 2 and the height of second bar is 1 and height of third bar is 5 and fourth bar is 6 and so on. And above is histogram and width of each bar is 1. And we have been given heights like that and we need to figure out the largest rectangle in that histogram. Okay, let me think how we can figure out that thing. Okay, if that is the case, this will be my answer. Okay, they are saying this is my answer and the answer will be 5 as my height and 2 as my width. So my answer for this will be 10. Okay, so let me just copy this thing. Let's try to think how I can solve this question. Okay, so the question was we have been given an histogram where the values are 2, 1, 5, 6, 2, 3. Okay, and we have been given histogram like that. Let me first draw the histogram on the paper and then it's more suitable. Okay, 1, 5. Okay, it will be 5 and then 6 and then 2 and then something 3. Fine. So this will be my answer in this case. So what I can think is what can be the brute force way to solve this question. One thing is coming to my mind. I can solve it in a way that, okay, let me take all the contiguous segment to solve this question. Okay, and I can take all the contiguous segment of length 1, then length 2, and just try to find the answer for that contiguous segment. Let's say I just take this contiguous segment of first 3 element, which is 2, 1, and 5. What will be my answer for this contiguous segment? Okay, I know that the width will be equal to 3, but what will be my height in this case? Okay, I can surely say that if I want to build a rectangle, then the height will be the minimum height histogram available in that contiguous length, isn't it? So I can say that the height will be 1. If I do in that way, then I can solve this question. That is fine. Okay. So if I just take in a brute force way, so how much time it will take to me? I need to iterate over every contiguous segment and to iterate over each contiguous segment, I need to take two variables L and R. So it will take order of n square time. And for each contiguous segment, I need to find the minimum most element. So the complexity will go up to n cube. So it doesn't sound me a good solution to solve this question. Can I think something else to make my algorithm better? Okay, let's think what I can do. Okay, let's think. Let's say I have an example, something like this. Okay, let's say this is my example. If I build a histogram, I have 7 here and I have 8. I have something 6. I have again 8 and I have something again like 7. Okay, if I am just considering all the contiguous segment, I will consider this segment as well, and I will consider this segment as well, I will consider this segment as well. I will definitely consider all the segments. If that is the case, that means, but I know that for all these segments, if I did in that segment, 6 is the part of that segment, then my minimum value will always be 6. Okay, can I use this idea to achieve something? Okay, why I am just iterating over all the contiguous segment? Why not that maximum contiguous segment for 6, which will give me the answer? Because in any way, other contiguous segments are waste for me. That's the waste of computation time. If somehow I just figured out for that particular 6, what will be the maximum contiguous segment if I just consider this element? So one thing I can surely say that, okay, if I just consider this element, how much elements I need to take in the right hand side, that I need to consider. Okay, I can consider 8, I can consider 7, but if I have something 5 here, I can't consider that element. Okay, this gives me the idea that what I can do, I can just take the nearest minimum element for a particular element in the right side. Fine, because such that all the elements in between will be greater than 6, and I can consider those elements for this element. And likewise, I can extend my similar approach in the left side as well. So this gives me some idea. If I do in that way, I can solve my problem. Okay, so this gives me the idea what I need to do for each element. For each element, I need to figure out the nearest minimum element in the right hand side as well as in the left hand side. Because I can surely say that this will be the maximum contiguous length for that particular element, which will give me the answers. And if I take any smaller contiguous length for that particular element, they are of no use. And in the previous question, we just solved how to figure out the nearest minimum element for any particular element. And we know that we can solve this using stack in order of n time. We just solved it. Okay, I can use that approach here as well, and I can solve this. And I can solve similar for the right hand side and for the left hand side, and I'm done. That sounds like a good solution. Let's write the code for this now. Okay, let's write the code for this question. Now let's say this is the case. Let's first try to dry run this. Okay, now for 2, I know that the nearest minimum element for 2 in the right hand side is 1, and in the left hand side I don't have any element. Fine, and so I just end up with the contiguous segment of one element only for 2. So that means for 2 my answer will be just 2. Now if I take 1, now for 1 I can see that for 1 5 is greater, 6 is greater, 2 is greater, 3 is greater. So I can pick all the elements for 1 in the right hand side. That is good. And in the left hand side as well, I can pick all the elements. That sounds like a good thing. So I can do like that. If I do in that way, so for 1, length available will be equal to n. So which is 1, 2, 3, 4, 5, 6 in this case. So my answer will be 6. Now for 5, if I do in similar way, I can see that for 5, the minimum length available, 6 is greater than 5. And okay, I found element 2 which is less than 5. So I can only consider these 2 elements for 5. Now if I just think of an element in the left hand side, I can see that 1 is the minimum element for 5. So I can consider only these two elements for 5. So I have a length of 2 for 5. I have a length of 5. So my answer will be 10 if I take 5 as a length. Okay, now if I take 6 as a length, then my area to consider for 6 will be, I can't take this element because this is smaller than 6, and I can't even take this element. So because these two elements are the nearest minimum element for 6. So I just have a one length for 6. So my answer will be equal to 6 only. Okay, now I consider for 2. If I want to consider for 2, okay, 3 is greater than 2, so I can consider that element. Now if I move into the left hand side, I can see that 6 is greater than 2. Okay, nice. And 5 is also greater than 2. Nice. But 1 is smaller than 2. So the nearest minimum element in the left side for 2 will be 1. So I can consider only these two elements for 2. Fine. So the total elements I can consider for 2 will be these 4 elements. So my length will be 4. So my answer for this case will be 8. Now for 3, let's consider what will my length. Okay, for 3, I can say that for 3, there are no elements available in the right hand side, but let's see what are the elements available to me in the left hand side. Okay, 2 is the nearest minimum element for 3 in the left hand side. So that means I have just of length 1 for 3 and answer will be equal to 3. Okay, I have considered all the elements by using that analogy, and I can see that if I want to consider that element, so I can just get the maximum length of 5, maximum length of 2 for 5. So that means it's okay to do like that, and in the end what I can do, I can find the maximum answer out of them, which is 10. So 10 will be my answer. Nice. If I do in that way, I can figure out the answer. Nice. And I can see that 10 is the answer for this question. Nice. So let's try to write a code for this. What will be the simplest code to write the solution for this will be, let's first have a size. Okay, I need two informations for every particular element. What will be the nearest smaller element? For that element in the right hand side, I also need the information, but with the nearest smaller element for that particular element in the left hand side. So I need both the information for any particular element. So let's say I created two vectors. The one of them is storing the smaller in right side. I need that information for all the elements. So I just initialize. I just need the size of n, and what should be the default value? Okay, I know that if for that element I haven't found any element which is lesser than that element in the right hand side, so I can say that, okay, let's just say that, okay, so in that case I may end up end of my list, so I can safely mark it as n, okay, because that seems like a good thing. Okay, now I need one more information which is smaller in the left side. I need that information as well. Okay, if I need that information, so I need this information an element, and in similarly I know that if I move into the left side, I haven't found any element which is lesser than this particular element, so I end up with an index of -1 because something like it goes beyond 0 in the left hand side. So I can pick the default value as -1, which seems like a good thing to me. Okay, now let's fill both of these arrays. How we can fill? So this is quite simple. We need a stack for this, because what we need to do, we need to figure out the nearest most element in the right hand side as well as the left hand side. As we discussed in the previous question, we can easily do this by using stack. Let's say I created a stack. Now let's first solve it for the right side. And let's say I need to iterate. Okay, now how we can do that thing? Let's say I consider the edge case. Let's say my stack is empty. Or the value available at the top of my stack is actually less than or equal to my current element. If that is the case, so I haven't found the answer for my current element yet, as well as for any element which are at this stack, because I just found an element which is greater than the element present at the top of the stack. So I need this information. So I need to push that element into the stack. So that's the only thing that I can do. So I have done. I am done here. So I can continue. Now, if that is not the case, that means what does this means that I am at the top. Okay, I need to first write the edge case. I need to iterate up till my stack is not empty, and my stack top is, if it is greater than AI, that means the ith element, it's basically lesser than the topmost element. So I can say that for the topmost element, ith element will be my answer. So as I'm moving into the right side, so I can update the answer for smaller right side, stack dot top, I can safely update it as I. Now I need not need the information for that particular element, so I can easily safely pop that element from my stack. Nice. So if I do in continue that way, I haven't figured out the answer for I yet, so I need this information. So I need to push that element into the stack. Let's say I just push that element in my stack. Fine. If I do similar way for my left side to populate this array, okay, I just need to apply the similar algorithm for this case as well. So what I can do, I just move into the left side now, and my algorithm will be something like this only. So I can just copy the same algorithm. Okay, so if that is the case, so but instead of left side, now I'm populating my left array for each element. Now, by doing these two operations, we just populated both of my arrays. We now have that information that for each particular element, what will be the nearest smaller element in the right side, as well as we have that information what will be the nearest smaller element for a particular element in the left side. We have both the information. Now, let's calculate the answer. Let's say initialize my answer as 0, because obviously my answer will be bigger than that 0, so I can update my answer for each particular element. Now, okay, what I can do, okay, now what I can do for, let I have an element in consideration, which is element in consideration, let's say it is a of I. Now, what will be my temp answer? That temp answer is basically this answer, which symbolizes that if I take this particular element in consideration, what's the maximum area of rectangle that I can achieve? Okay, let's try to think maximum rectangle area that I can achieve for that particular element. Okay, for that, my length will be, height will be this, and what will be my width? I know that if I need to figure out the width, I need to find the nearest smaller element in the right side as well as in the left side. So for this, that's why I just keep the default value as -1 for left hand side and for right hand side, so that it's easy to compute that thing. So let's say for 2, I have my nearest smaller element in the left side will be -1 and in the right side will be 1. So if I take the whole length will be equal to 3. If I take the whole length, my whole length, that is nearest right side minus of particular that element I, and I take the nearest left side, the particular element I plus 1. So this will be the total length. But in that particular length, I just include the nearest smaller element in the right side as well as for the left side. But I don't need to include these two elements, because these two elements shouldn't be included in the rectangle. So I can safely remove -2 to remove these two elements, and I can update my answer as max of my answer and temp answer. If I do in that way, I can easily achieve my answer and I safely return answer in the end. Let's see. Okay, I just initialize my array and I just keep my smaller right side as n. I just add the default value as n. For the smaller left side, I just did in the similar way. I maintain a stack. Okay, we missed one thing. Okay, what we need to do, because there are many elements. After solving it for the right hand side, for that particular elements, we haven't find any elements in the right side which are smaller than that element. So that element still remain into this stack. So I need to remove all that elements from my stack. So I need to remove, let's say I removed that algorithm from my stack. Okay, so now let's look at the complexity part of it. This is running order of n time, this is running order of n time, and also this is running in order of n time. So the overall complexity will be 3n, which I can safely say it as order of n. Okay, nice. So we just solved this question in order of n time. Nice. That sounds like good thing. Now let's test my thing first. Okay. Let's see the errors. We have an error at 51st line. Okay, I guess the error is okay. It's not nearest. It's smaller. Okay, smaller. And is there anything else? Okay. Okay, this is correct. And you need to push. Okay, now let's test it again. Okay, nice. Okay, everything seems correct to me. Let's submit my code. Let's see. Oh, nice. We solved this question. Nice. So now let's look the other question for today. We have solved both this question. Now let's look into this question. What this question is saying, that we have been given an array of integers. This is a sliding window of size b, which is moving from very left of the array to the very right. And you can see that the blue numbers in the window. Each time the sliding window moves rightwards by one position, and you have to find the maximum for each window. Okay, so the question is, we have been given an array, and in that given array, we have been given a window. We need to figure out the maximum element in that window, and that window is basically a sliding window. So what does it mean? Let me explain you. That let's say we have been given a window of size 3. So in the starting, let's say we consider the first 3 element of the window, and we figure out the maximum, and the maximum value for these particular 3 elements obviously will be equal to 3. As you can see that 1, 3 and minus 1, the maximum element for this will be 3. Nice. So now let's look at the other thing. Okay, now for if I just take the other next window for this particular case, the next window will be 3, minus 1 and minus 3. Nice. So if I take this window, and then I can see that the maximum for this window will be equal to 3. Nice. If I take the next other window, then I can say that the maximum for this window, it's equal to 5. Okay. And for this window, if I go in a similar fashion, I can see that, okay, the maximum is 5. And for other window, I can see that the maximum value is 6. If I go in that way, if I take the last window, the maximum value is 7. Okay, so this is my question. How I can solve this question? Okay, let's think. Okay, let me move to here. Now, how we can solve this question? Let's see. Okay, we have been given as some array. Let's say we have been given array. Let's say we take the random array now. 4, 7, 8, 3, 2, 5, and we have been given b as 4. Let's say this is given to us, and we need to figure out the maximum element in each window of length 4. So the first window will be 4, 7, 8, 3. So the maximum value for this window will be equal to 8. Nice. Now the next window will be this, and again the maximum value is 8. Okay, the next window is this, and the maximum value is 8 again. Okay, how I can solve this question? Let me first think. Okay, I need to consider all the windows. So the brute force way will be, I maintain a window and I just keep one start and end, which is referencing my current window, and I just figure out the maximum element in that particular window and I will get an answer. That's the thing that I can do, and I will achieve the and I can solve it. But now let's look at the time complexity to solve this question. Okay, if I maintain one window, that means, what does it mean? It means if I need to find the maximum, okay, one way is what I can do. I can just find the maximum. I do the iteration from start to end, but this will lead to other order of n time, and how many updation that I need to do for start end, as there are only order of n windows. As we can see that the first window is of 4 element, then the next window of this 4, and the next window of this 4. So there are only 3 windows, and that's of order basically n. So the overall complexity will be order of n square. Can we improve this algorithm? Is there any way to improve this algorithm? Okay, the one way that we can do to improve our algorithm is, what I can do, I can maintain some sort of structure that we know, and that will tell me the maximum element within a given range. Within a given range, I can do something like that, and maybe that will solve my question. But if I need to maintain that structure, we already know that the segment tree provides that sort of flexibility that gives us the maximum value in a particular range. Okay, and this will solve my problem in order of n to order of log n. If you can use something like that, but even then my complexity will be n log n. Can I improve further if I want to solve this? Let's see. Maybe we can improve it further. Okay, let's say we have been given an example 4, 7, 8, 3, 2, 5. Okay, what we can do? Okay, what I can see here that, okay, let's say the window size is 3. Let's say the window size is 3 in this question. But I can say that, first of all, let me consider the first 3 elements of this window, which are 4, 7, 8. Okay, I just figured out one thing, that if I have only one element, I can store this information. Now I encountered an element which is greater than that element. If that particular element is greater than that particular element, so I can say that this element won't be the answer in any of the window. Why? Because I just found an element which is greater than this element and has a greater index as well. So that means if there is a chance that I will just need to remove an element, that will be the element of lesser index, obviously, for sure. And if I just figure out an element which is greater than this, so that's of greater use than this. So I don't need this information. So I can safely remove this information, and I can keep this information only. Now, in the similar way, if I figured out 8, okay, I can remove this information as well in a similar way, and I can just store the information 8 only to solve my answer. Okay, if I do in this way, I can solve this question. Okay, let's see. Now my answer is 8 for this. Now, okay, now let's say I now come at 3. If we figure out an element which is lesser than this element, okay, but I can't say anything now. I can't say anything now because there may be a possibility, because it has a larger index, there may be a possibility that for some other window, this will be my answer. So I need to store this data as well. So that means we are coming up with some algorithm. If we are figuring out an element which is greater than any particular element, if that is the case, so we can safely remove the element which is at the end of my some data structure. And if I figure out an element which is smaller than that element, so I just need to append that element in the end. Nice. But one thing we also need to show that if we go in some other window, we need to remove the elements which are not in that window. And as I am just adding all the elements in the increasing order of index in that data structure, in some data structure, so I can just check whether the first element is of previous window or the current window. If it doesn't belong to the current window, I can safely remove that element. So, okay, so one thing that I'm sure that I need, if I want to solve this question by using this algorithm, I need a data structure which will help me in adding in the end, also removing in the end, and also allows me the ability to remove from the front. Okay, and all those operations should be as efficient as possible if I want to make my algorithm faster. So what data structure that comes to my mind? Okay, can I use stack? If I use stack, then these two operations will perform in a good way, but not this. Okay, so what sort of data structure I can use now? Okay, can I use queue? If I use queue, I can do this operation and this operation, but I need to sacrifice over here. Okay, then what other data structure that I can use? If I'm using some complex data structure, then the complexity will be log of n. And we already know that we just build a segment rather than that data structure that will already solve us our problem in loader of log n. So we need some sort of data structure. Okay, one thing that comes to my mind, why don't we use the doubly linked list? In the doubly linked list, we can add, and we have both the pointers head and tail. We can just add the element, and then we can easily remove the element from the and in order of one time, and add that element in order of one time. And similarly, what we can do this thing in the front as well. If we follow this approach, we make our algorithm efficient. Nice. So in C++, we have this doubly linked list in a form of Dequeue. So we can use Dequeue in our case and we can solve this question. Nice. So now let's try to look at the example and we'll solve this question again. We have elements 4, 7, 8, 3, 2, 5. Okay, if that is true, now let's try to think. Okay, I have a window of 3 elements. Let's say I maintain a Dequeue where I just, if I have a first element, I just put it and I figure out the second element. If it is greater, so 4 is of no use, I can remove that element. So I can put 7, and if of no use, I can remove that element. I can put 8. Now I just end up with the window. What will my answer? It will always be the first element in the Dequeue, isn't it? Because the way we are just storing the data, the first element of that window will always give me the answer. So if we do in that way, we can just get the things done, man. That's cool. We can do in that way. Cool. So now if I want to consider a next window, it will be something this. Okay, now let's see what is the index of 8. Index of 8 is 2, but in the current it belongs to the current window, so I not need to remove that element. So what I can do, I can just add 3 here because I need to add 3 because it is lesser than this element and this element can be the answer for other windows. So I need to add 3. Now I am at, okay, I just add 3 and the answer will be again 8. And similarly, if I do it that way, I will find the answer. Now let's try to write the code for this. Figure out everything what is required and we just figure out the algorithm to solve this question. Okay, how we will write the code? One thing is clear to you, one thing is clear to us that, okay, let's say first take the size. We need a data structure like Dequeue, and let's say it's Dequeue. Okay, now I need to iterate over my link, over my array. Okay, let's first do the parts. Let's say first cover the edge cases. If my Dequeue is empty, and or if I have an element in the end of my Dequeue which is basically greater than my current element. In that case, what we need to do? We just figured out in that case, we may need this information. So in that case, we can add this element in the end, and that will help me to solve this question. Now, if that is not the case, what we can do, we can check while, okay, my Dequeue is not empty, and we are getting, okay, we need to add 4 as well. What we can do, if my element in the back, they are lesser or equal to my AI, because I just found an element of greater index and it is greater than the last element of my Dequeue. So that means I don't need that last element in my data structure. So I can safely remove that element. Okay, I can do in that way. So in the end, I need that ith element. So I need to add this element in the end. So I am done. But I need to remove all the elements which are not belong to my current window. As we can see that, okay, my next window will start when I becomes greater than or equal to b. So what we need to do in that case, If that is the case, okay, let me first initialize my answer as well. Okay, and so that means if I just end up with an index greater than equal to b, what does it mean? It means that we just completed our one window. So I can add the answer for that window in my answer vector, which will be the front of my Dequeue, as I already discussed why it is, isn't it? So it will be my front. Okay. Now what I can do, if that is the case, now what I need to do, I need to check whether the first element of my data structure is in the current window or not. So for that, first I need to check the base case. If my DQ is not empty, otherwise it will give us the segmentation fault. And if my DQ is not empty, and we can say that the element, okay, the index of the element in the front should be, if it is, okay, if it is the first element, it's the zeroth element. If I'm at the second window, then the index, if the index is 0, then I can safely remove that element. So the index will be I minus pi, because if I at the next window, my I will be b and b minus b will be 0. If I'm at the next window, my I will be b plus 1. So if in the front I have the element which is having index 1, so I can safely remove that element. So if I do it that way, I can easily solve this problem. So if I do it that way, what I can do, I need to remove my element from the front. Okay, if I do in that way, I'm done. Nice. But okay, but what about the last element? What about the last element? When I'm at the last element, I haven't updated the answer for my last element. So I need to update it here. Let's say, okay, that will be, my answer will be pq dot front. Okay, I just don't need to add the answer dot front. It will be the element for that. So I need A for that case, A for that case as well. If I do in that way, I think this should work. I need maintain DQ, I maintain vector. When I do in that way, I'm pushing my answer. I'm considering all the cases. Now let's test. Oh, I need to return answer as well for sure. In that way. Okay, nice. Correct answer. Now let's submit the code. Nice, we solved this question. Now we are already ahead of our streak. We completed the 2-day streak in a really good way. Okay, nice. So this is all about today's lecture. Thank you guys.
Hi everyone, this is Dequeue. Welcome back to Scalar. In this video, we are going to talk about queue data structure completely. We'll be talking about different aspects of a queue data structure, how a queue is built, what is the basic functionality of a queue, what are the different applications of a queue. We'll see how we'll build a queue using an array. We'll see how we'll build a queue using a linked list. We'll also go through QSTL, that is how we can use the standard template library to use our queue library in our questions. We'll talk about different applications, different questions of queues. Like, this is going to be an extensive 4 to 5 hours course that will take you deep dive into queues. We'll solve problems from basics to medium level to very hard problems that involve some applications of BFS. So make sure you watch this course till the very end and gain whatsoever you can get out of queues as a topic. Along with that, if you wish that you're liking this content and you want more such type of content, you can subscribe to this channel, like this video, and now let's get started. Hi everyone, this is Dequeue. So in this entire episode, we are going to discuss about queue as a data structure, how queue is important, what kind of problems we can solve using queue, and why we have switched from, like, earlier we have started arrays. You might have studied linked lists. From linked list we moved on to stacks, and finally now we are discussing queues. So all these data structures, like be it arrays, be it linked lists, be it stacks, so these are known as linear data structure. What do you mean by linear data structure? Linear data structure is a data structure in which the elements are stored in a linear fashion. Let's say we were storing elements in array. So how we're storing elements in an array? So let's say we have an array
of size 5 and we were storing numbers, let's say 1 2 3 4 5, and different operations were performed on array. Let's say we need to insert a new element in array, we need to delete an element from array. So we have seen millions of operations that have been performed on arrays. Apart from that, we have also seen linked lists. We have talked about how a linked list is made. There is one node, it has a particular pointer, this is storing the address of another node, and so on. In this way, we were basically discussing how linked list, and we were talking about advantages of linked list over array. Then we moved upon to stack. So stack is a particular peculiar data structure in which elements are arranged in a particular form. Like we called stack as a lifo data structure. What do you mean by lifo data structure? It means last in and first out data structure. So last in first out stands for, like, let's say we are inserting an element at the top, and that is the element that will be removed first. So the element which is being added at the last, it will be removed at the first. So that element is particularly, we used to call it as that this element is a part of stack. So we have studied all these data structures and now we are discussing about queue. So starting with the topic queue, let me just give you a real life example of queue. Let's suppose you are into a movie theater. So what happens in a movie theater? Let's say you are in a PVR. So you and a group of your friends, let's say 3 friends are going to PVR, and you want to purchase the movie tickets on the movie counter. Let's say this is the movie counter, and as soon as you reach the movie center, you see that there is a long queue of people. Let's say first person is standing here, second person is standing here, third person is standing here, fourth person is standing here, and they are standing in a queue. What do I mean by a queue? Is like first person is the one who came first and he stood here, then the second person came here, then the third person came here, then the fourth person came here, and here you came. Like this is A. Let's say you are coming after fourth. So how the movie ticket counter is going to resolve the movie ticket distribution? It's like, firstly, the person who reached the movie counter first will be getting his ticket at the first and he will be going. Then the second person will be going, then the third person will be going, and then the fourth person will be going, and then your turn will finally come and you will get the movie ticket. So what actually is happening? Let's say this is a form of a structure in which we have had these many elements like 1, 2, 3, 4 and 5. So first element to be processed from this particular data structure is this. Like this will be removed first, and let's say we have to add another element, it will be added at this ending. This is known as the rear end. Let's say I'm adding 6, so this particular end is known as the rear end, and this particular end is known as the front end. So this will be removed. Next, after first, who will be given a chance? Second will be removed, then third, then fourth, and if we need to add an element, it will be added at the rear end or at the end of that particular array. So what we can say is stack, we called stack as a LIFO data structure, that is last in first out data structure. For queues, what we are seeing here is the person who is coming at the first is going out at the first. Like if you are coming to purchase the movie ticket and you are the first one in the row, so you will be getting the movie ticket at the earliest. So queue follows the property of FIFO data structure. That means FIFO stands for first in first out data structure. Like I hope the things should be clear till here. So if we go by a formal definition of queue, so you can say that a queue is an ordered list in which insertions are done at one end, that we called as rear end, and deletions are done from another end, that is the front end. So the first element to be inserted is the first one to be deleted, hence we call this as a FIFO data structure. Like I have told you a very real life example of how a movie counter or a movie ticket counter works, right? But how are we going to use this particular concept of queues While programming, like what's the use of queue in programming? Is it something that we should study? Why we should study? Let me just give you one more example. So you all might have at some point of time used a printer, right? Printer, it's used to print. It is connected to our computer. We give a command and our pages are printed. We supply the pages and we get a printout from that particular printer. So let's say I have 6 pages to be printed, right? So you give a command for 6 pages to be printed. So what you will see is, firstly, the page which is there at the front, like the first page of your notebook out of 6 pages, that will be printed. Then it will move on to your second page. Then it will move on to your third page. Then it will move on to your fourth page, then fifth, and then sixth. So isn't this structure similar to what we represent a queue as? The page which is at the front will be processed first and we'll be getting the printout of the first page. Right? So how this would have been programmed? So during, well, like while programming, writing the algorithm, like how the scheduling is being done, so there might be a use case of queue, or like this was something that was make that would have helped you to understand how we are actually using queues in our programming, right? So apart from that, queue, we call queue as an abstract data type, because we'll create our queue from the very scratch, and after we have created queue from the very scratch, we can use the queue to solve different problems. So we'll create queue, we'll perform different operations. Like in stack, you have seen that we have performed different operations. Like if you remember from stack, so like this is a stack, so we can push an element, that is adding an element, so we call that operation as a push operation. Next, we have seen if we want to remove an element from the stack, we call that operation as a pop operation, right? So we have seen these particular operation, push and pop. Like like to get the top element from the stack, we use a function named as top. So similar to these functions like push and pop, what we have in queue is there is something known as enqueue, that is to add an element in a queue, and something known as dequeue. Enqueue stands for adding an element and dequeue stands for deleting an element. So how these NQ and DQ operations are performed, there are certain other operations that we'll see that are required for queue. Like we'll talk about these operations in detail. We'll also talk about NQ and DQ in detail going forward in this particular lecture. But I hope this much theory is clear to you. And like if you haven't, like if there is something that is still lagging, I would request you to watch this video till again till here, and you probably most of the things will be clear to you, right? So this is something known as a queue, or this is something known as a queue as an abstract data type. So now I hope you all are aware of what a queue is, what all are the operations on queue. So now let's deep dive into how a queue is made, how a queue is formed, how we'll write the basic structure of queue. But before understanding a queue, let's see how the container for queue is made, right? So before queue, we have already studied arrays and we have already studied linked lists, right? So to make the container of queue, container of the form, let's say this, we can either use an array or we can use a linked list. Like both ways are possible. An array is also possible and a linked list is also possible. So first, let us deep dive into how an array can be used to form a queue. Like all the functions that we have discussed previously, like enqueue, dequeue, front, is empty, get size. So all these functions we are going to understand in detail, and we are going to write the code for each one of them so that we can better understand how we can use an array to make these particular, to implement these particular functionality. So let us just take an array. Let's take an array. Let's say this is an array. Let me name this array as a data array, right? And let's give the size to our array. Let's say it's of size 5. It is given by the user itself. So let's say we have an array of size 5. We can index it. So it has indexing from 0 to 4, and we are going to implement our queue using this particular array. Now let's suppose what I have told you about enqueue operation is like when we do an enqueue operation, let's say I'm doing enqueue 100. So when I'm doing an enqueue 100, it goes and places 100 at this position, right? Now let's say I'm doing an enqueue 200. So it goes and places 200 at this particular location. The user explicitly doesn't knows or explicitly doesn't provide this information that where to add the next element, because this is the functionality of the queue that automatically if we are adding a new element, it is to be added from this end. This end was called as rear end, right? So automatically if you're enqueuing a particular element, so it will automatically be added at the rear end, right? So what will be the value of front? Let's say I'm doing a front operation. I'm calling a front function. So front is a function that gives us the frontmost element of this queue. So this is a queue. The frontmost element is this. So front will get the output as 100. Let's say I do a dequeue. So if I'm doing a dequeue, the front element or the element from the front end will be removed and we'll get 100 at the output, and also 100 is removed. Similarly, if I do a dequeue again, it will again give the output as 200 and 200 is removed. But if we are to implement everything on our own, so we need to specify na, ki how insertions and deletions are to be performed in this particular array. So to perform those particular operations, I will be needing something. So I'll be needing different pointers. Let's say I'll be needing a first index, that is next index, that will store the index on which I'll enqueue a new element, right? Now let's suppose, let me just erase this. So now let's say I am doing an enqueue 100. So initially next index is the pointer that is used to get the value of the next index, at which particular index we are going to add the new element in our queue. So if I'm doing enqueue 100, like our queue is empty, as soon as our queue is empty, the initial value of next index is 0. Initially we have made the next index as 0. Now I have written a particular function, or I am performing a particular function, that is enqueue 100. So I'll be changing the value of next index from 0 to 1 and I'll be adding 100 here. Is it simple? Yeah. So I'll be again doing, let's say, enqueue 200. Now what will happen? The value of next index goes from 1 to 2 and 200 is added here. So we are keeping a check, we are keeping a value that helps us know where to add a particular new element, right? I hope this is clear. Also, let's say I'm doing one more enqueue operation, enqueue 300, 2 will be increased to 3 and 300 will be added here. I hope this is fine. So apart from enqueue operations, there are other different operations. Let's say there is a front operation. If I call front, so what I'm supposed to give back is, I'm supposed to give back the element which is present at the front end. So to get the element which is present at the front end, how we'll get that? So let me keep one more index. Let me just name it as first index. So what will be the initial value of first index? Let's say our queue is empty. If our queue is empty, what will be the value of front? So there will be no value of front, right? That means we'll initialize the front index by -1 because we will be accessing the element which is present at the front. So this first index, initially it is -1. As soon as I write this enqueue 100, that means I am adding one particular element in my data array or in my queue. So the value of next index increases. Also, along with that, the value of first index increases from -1 to 0. And this only happens when we are adding the first element to the queue, right? I hope this much is clear. So let us discuss about a dequeue operation also. So when I say dequeue, so what will happen during a dequeue? the element from the front end will be deleted. So if the element from the front end is to be deleted, we'll be getting the output as 100 and 100 is to be deleted. So what happens in this case is the value of first index also moves from 0 to 1. It increases by 1. We'll do first index increase by 1 position if we are doing a Dequeue, right? Now first index goes on to here because 100 is already removed. Now again if I'm doing a Dequeue, so if I'm doing a Dequeue, 200 is again removed. If 200 is removed and 200 will be deleted, the value of first index becomes 2. Now 200 is deleted and the value of first index becomes 2. So in this way these operations work. Apart from that, we can also have let's say one more variable by the name of size. So what does this size represent? So this size represents the size of our queue or size of our queue at any point of time. So what will we do by this particular size variable is, as soon as we add a new element to our array, we'll do size plus plus. As soon as we delete a new element, that is will dequeue, will do size minus minus. So the value of size will also be helpful to us going forward. I hope this much is clear. Now let's just erase it and write it again neatly so that you can have a better understanding. So what we initially had, we had a data array. We made this data array of the form this. So we have the size of the data array as 5 and we were performing certain operations. Now we know that we have different variables, that is next index, first index and size. So we have these three factors, these 3 pointers that can help us navigate through this queue, that can help us to solve and understand different parameters of the queue, right? So when I say different parameters of the queue, so let's say I'm doing an NQ, let's say NQ 100. So initially the value of next index is 0, first index is -1, size is 0, right? So I'm doing NQ 100. So what will this operation do is 100 will be placed at the 0th position. The value of next index will increase to 1. First index will also increase to 0 and size will be size plus plus and size will become 1. Let's say I'm doing an NQ 200. So what will happen? 200 will be placed here. Next index becomes 2. First index remains the same. First index is still 100 and size becomes plus plus, that is size becomes 2. Now let's say I am doing a front operation. So front function, what front functions gives? Front function gives the element which is present at the first index. So we'll check what is the first index. The element present at the first index, that is the 0th location, is 100. So we'll output 100. That's it. Next we'll check, we'll do Dequeue. So what does Dequeue gives? Dequeue is the function that will remove the element that is present at the first location, whether that is present at the front end. So this element will be removed. So 100 will be removed and 100 will be given as the output. What else will happen? First index, the value of first index will be increased. The value of first index becomes 1 in this case. So first index moves to here and size will decrease by 1 and size will become 1. Right? I hope I'm clear till here. What will be the value of size? If we call our size operator or get size of function, so we'll simply get the value as 1 because we'll return this size variable. We'll check is empty. Is our queue empty or not? So how we can check that? If the value of size at any point becomes equal to 0, we can say that our queue is empty. So in this way we are going to perform all these operations, and in between there might be some challenges, there might be some constraints that can help us understand how we can make our approach a little better. So let us take another scenario. So this scenario will help us understand one more use case or one more new functionality, new feature, how we can implement our queue, right? So let's say again I'm taking this data array I'm taking again. Let's say it's again of size 5, right? And I am again adding, let's say this time I have this next index, I have this first index, and I have this value as 10, this value as 20, this value as 30, this value as 40, right? And let's say I perform, so at this particular point of time, what will be the value of next index? The value of next index initially would be 0. When we add 10, it becomes 1. When we add 20, it becomes 2, 3, 4, 5. So it will be now 5 in this case. What will be the value of first index? The value of first index is still, initially it was -1. As soon as we added 10, it becomes 0. What will be the value of size? Size in this case would be 1, 2, 3, 4. Well, 4 NK operations we have done. So size will be 4 in this case up till this particular situation. Let's say I perform a dequeue operation, and after doing a dequeue operation, this value is removed. So we'll get the output as 10, and this value is removed. The value of first index becomes 1, size becomes 3, right? I want to do an NQ. Like let's say I'm doing an NQ 50. If I'm doing an NQ 50, 50 will be added here. The value of next index becomes, what will be the value of next index? Next index will become 5, and it was initially 4. Now it becomes 5, and the value of first index becomes, it remains the same. The value of size becomes 4 again, right? Again, let's say I'm doing a dequeue operation. So if I'm doing a dequeue operation, the number that is present at the first location, it is deleted. That the value present at the first index is deleted, and we get 20 as the output. First index becomes 2, size becomes 3 again. Now let's say I again want to do an NQ. So for doing an NQ operation, let's say I want to add 60. So now I will be inserting this 60 on the next index value. So next index value here is 5, but I don't have 5 in my array. The size is full, the capacity is not there. So, but still what I can see is there are 2 spaces that are empty in my queue, but I'm still not able to add a new element, even if 2 places are already empty, because we have removed those elements. So what to do in this particular case? Let's say we can solve this particular problem in this way. Let's say now I have this particular array. So these 2 spaces are empty, and here I have 30, 40 and 50. So what if I shift this 30 here, 40 here and 50 here? Now I'll have these 2 spaces empty. So it will look something like this. It will look something like 30, 40, 50 and 2 spaces are empty, and if I'll be performing NQ 60, 60 will be added here, and 7, well, if I'm doing one more NQ operation, 70 will be added here, and it goes on like this. But do you think it's a feasible operation? Like I am moving all the elements again and again in real time to these particular places so as to support this particular approach. We can do something better, a little more better than this particular approach. Let us try to think a little more again. So you have seen we again are facing a problem that we can't shift the numbers each time. So what we'll have to do in this case is, let me take this example once again. We have this data array, and inside this data array I have 10, 20, 30, 40 and 50. I have this next index, I have this first index, I have this size, and I have 10 and 20 already removed. The value of like the indexes are 0, 1, 2, 3 and 4. Now what I want to do is, like, what will be the value of next index in this case is, next index supposedly it goes on to 5, which is not possible. So I am stuck in this particular situation. The value of first index is 2 because first index has increased and it is here now. The value of size is 3 as of now. Now still the size is 3, but the capacity of our queue is 5. The capacity is the same. Capacity is a constant number and it will remain the same throughout. But the size is 3. Still we have 2 places remaining, but we are not able to add any new element in our queue. So what we'll do in this case is, let's say I'm doing an NQ operation. I'm doing an NQ 60. So I want to add 60 in my array. So what I was initially supposed to do, I was initially supposed to add this particular 60 on the next index variable. So I was to add this on fifth index, but fifth index is not available. So what I will do is, rather than simply doing next index is equal to next index plus plus, rather than simply increasing the value of next index as soon as NQ operation is happening, what I will do is I will do next index is equal to next index plus 1 mod capacity, right? So after 4, like as soon as I reach 4, rather than moving from 4 to 5, what will happen is it will be 4 plus 1. So 4 plus 1 mod capacity is 5, so 4, that is 5 mod 5, it goes on to 0. So after fourth location of, like after the value of next index become 4, it reaches to 0 rather than going to 5. Now it goes from 4 to 0, and as soon as the value of next index becomes 0, we'll add the 60 at this particular position and we are done. Now again, let's say I'm doing NQ70. What will happen? 70 will be added on the next index location. Now what will be the value of next index? So now it is 0, so it will become, according to this new formula, 0 plus 1 mod 5. So that is 1 mod 5, it's equal to 1. So the value of next index is 1. R70 will be added here and we are done. At this position, the value of size becomes equal to capacity. The value of size is 4, then it became 5. So when 5 is equal to 5, that is size becomes equal to capacity, we say that our queue is full. So this is how we will be proceeding with our NQ DQ operations, with our getting the front element, getting the size, getting the isEmpty function. So all these functions that we have written, now we are going to write the code for the same, and I hope you will be as excited as me for writing the code so that we can build upon this particular approach in the form of code. So we'll be writing the code particularly in C++ on the interview bit IDE. So let's move upon to the code editor. So now as you can see that we are on our IDE to write the code for our queue to that we are creating using an array. So for that I'll be creating a class, let's say class queue array. Queue, let's say I name it as queue using array, right? So what will happen in this class is, so I'll create all the data members of this class that we have initially used. So the first thing that was there in this, like the elements that we were using for this particular queue were, like we need a data array, right? We also need something known as a next index variable. We need something known as a first index variable. We need something known as size, capacity. So these are the operations. This is an array. So initially, rather than specifying any type of array, like which kind of elements will it contain, whether it will contain integer data, whether it will contain character data, so we'll be simply using a template. That is, we'll initialize this data member as, let's say, t star data. So we'll be initializing our array. Like generally what we do is, like for example, if it's an integer array, we initialize it as int star array. So now we are initializing it as t star array. So t here represents a template. We'll specifically initialize this template also here, right? So it is initialized as something like template type name, right? So we have this t star array, we have int next index, we have int first index, I need size, I need int capacity, right? So these are the data members that I have created. Now let me just create the constructor that is queue using array. So this constructor will take, like initially when we are initializing our array, we'll just specify the size of the array. So the input parameter for this constructor will be int s and will initialize all the data members of our array. Constructor is basically used to initialize. So data array will be initialized as new t of size s, right? Next index value becomes, initially what was the value of next index? We gave the value of next index as 0. First index value was given as -1. Size initially is 0 and capacity is equal to the size that we are specifying for our queue, right? So we have successfully initialized our constructor. Now we will start writing some functions that we have already discussed. So the first function that we are going to write today is enqueue operation. So what will be the return type of enqueue operation? The return type will be simply void, right? Because we are just adding a new element into our array. So we'll an enqueue operation. So we'll write void enqueue, and inside this enqueue will again provide the element that we want to add in our array. So the parameter input argument will be t element. So what exactly is going to happen in this enqueue array? Let me just take you back to what we discussed. Let's just erase this, right? So what we were discussing is, like, as soon as we enqueue a particular number in this array, we had this particular array which we used to make our queue. When we were, let's say, adding 10, so the value of what we were doing is we were putting the new element at the next index position. Like inside our data array at the next index location, I'll be putting the new element. That's one thing. And what else I was doing, I was increasing the value of next index. How I was increasing the value of next index plus plus. No, we saw that next index plus plus might give us some problems. So how we increase the value of next index value was increased, and we wrote it as next index plus 1 mod capacity. And I hope all of you know why we have done this particular thing, right? Why we have not written just next index plus plus, but next index plus 1 mod capacity, right? Anything else that we need to do in this particular thing? And like you can think of, we had a size variable. We used to do size plus plus also as soon as we enqueue something. So this is the third thing that we are going to write. And also, like, initially the value of first index is -1, but as soon as we add a new element, that's the first element in our queue, so we'll be initializing this. So we'll be updating this first index also. So how we are going to do all these things that I have mentioned? Let's just start writing with this enqueue operation. So what exactly I'm going to do in this enqueue operation is, firstly, I'll go to the data array. I'll see what is there at next index. At next index, I'll put element, right? And I'll do next index is equal to next index plus 1 mod capacity, right? And also I'll do size plus plus. Is there something that we are missing? The first index operation, right? So I'll put a check, like whenever, like if the value of first index is equal to -1, then only I'll do first index updation to 0. In all other cases, I'll not be specifically updating this from -1 to 0. So this is the only case when we find out that the first index is -1, that means our queue is empty and I am just putting out the first element, so I'll need to update the value of first index. What else we can do? Anything else that you think we are missing at any point of time? We also discussed one thing, if you remember. So what happens if the size of our array is equal to capacity? If size is already equal to capacity, we have no place in our array. Like this is 10, 20, 30, 40 and 50. So now if I want to add 60, there's no space. So let me just cover this edge case as well. Like if the value of size is equal to capacity, I'll put out a message that is my queue is full, and I will simply return without doing anything. I hope this is a good NQ function. This is a good NQ function that we have written. Now let's move up on to another function that we are discussing. So there is a function that is a very simple function. Let's say size, right? So what will be int get size? Let me name this function as get size. So if I simply want to get the size of the queue at any particular point of time, what I'll do, I'll simply go and I'll simply return size. Is that fine? Yes, it's absolutely fine. There's one more operation that we have discussed, that was is empty. So what's the best way to check is empty function? So is empty will return, like it will return whether it's empty or not. So we'll have the return type as boolean return type. Boolean return type will tell us the value will be true if the queue is empty, the value will be false if the queue is not empty. So I'll simply write this operation and I'll return size equal to 0. When I say size equal to 0, what does this statement means? How this statement will give the correct answer? So in any case, when our size becomes equal to 0, what does this statement mean? This statement will be true only if our queue is empty. And whenever our queue is empty, we'll simply return this through this particular function, that is empty. Right? I hope this is clear to everyone. So there is one more function, that is the function that we were discussing, that is front. So what will be the return type of this front function? So let's just discuss a little about front function. So what we'll be doing in this front function is we'll make the return type for this front, because it's again of t type, so the return type will be t, and inside this front what will simply return, will return the element which is present at the first index. The element which is present here will simply return the element present at the first index. So what I'll do is I'll return data of first index. Anything else that I need to do in this particular function is, let's put one more check. That check will help us understand if at any case our queue is empty. So I'll check if is empty. If our queue is already empty, that means we'll see out queue is empty, and I'll return, let's say I'll return 0. Why I'm returning 0? Because I have a particular return type, so I simply can't return nothing. I'll have to return something. Let's say we are returning 0. So our front function is also done. So one function that is left is a dequeue function. So what we'll be doing in this dequeue function is, so what does the dequeue function does? So dequeue function basically, whenever I'll call a dequeue operation, it will simply remove this element that is present at the first index, and it will increase the value of first index to first index plus plus. Along with that, there'll be certain other things happening. We'll get this 10 as the output, so I'll be having a return type again t, because I want to output that element also as soon as I am removing that particular element, right? So think again, what will this function work again this time also? Let me just erase this. So this time, like if I'm writing, like if I'm simply increasing the value of first index, so first index will also be increased using first index plus 1 mod capacity. I want you people to think on this. I've already explained how this thing works and what is the meaning of this particular thing. So I've already explained it in the case when we were increasing the value of next index, but during the dequeue operation, the value of first index, rather than doing it as first index plus plus, I will be doing it as first index is equal to first index plus 1 mod capacity. Try to think upon this particular approach on your own once again, and still you people, if you are facing any doubts, do comment in the comment section that you are not clear with this thing. I'll try to explain it to you once again, or in the comment section only, but I want you people to think on your own once, so that you have a little more clarity on this particular topic. Let's just move on to writing the code for dequeue operation. So when I say t of dequeue, So what will happen is in this particular thing is simply I'll store this value of the value present at the first index. So let's say I'm storing it as t result. So t result will give me data of first index, right? Along with that, I'll do first index is equal to first index plus 1 mod capacity, right? What else we were doing in this is, let's say I'm removing this particular element from my queue. I was reducing the size, so the size will become size minus minus, and we'll simply return this result. So is it done? Any edge case? Let's say in this also I'm putting a check for this empty condition. Once again, the same check in front that we made. Let me just copy and paste the same code so that we don't waste time. So yeah, so I'm writing if is empty, like if the queue is empty, we'll simply output queue is empty and will return 0. I think I am done with the code for our particular question. Let's just try writing out the functions, try executing it a little so that we can have a better clarity. Let me just erase it once. So inside this main function, what I'll do is I'll create queue using array. Let me just initialize the queue as queue, and I need to specify the size. So what will be the size? Let's say the size is 5. Along with that, I need to specify what is the type of data. So it is integer data because we have templated it. So that's why I'm putting this as integer. I would have put it, I could have written here char also if my queue was having character elements, right? So now queue of 5 elements is created. What I'll do is I'll enqueue nqueue nq1. Let me just copy and paste this several number of times. 1 is added, 2, 3, 4 and 5. I have these 5 elements in this enqueue operation in this queue. Let's say after this I just check on cout of queue dot front. So what would be the front element that we are expecting here in this case is, so I'll be expecting out 1 in this case. Let me just do cout queue dot dequeue. So it will again give me the same, that is output will be 1. Let me just see out the size now. Queue dot size, get size, the function name was get size. So the size now will be 4. So let's just let me just go through if there is any mistake. There might be some typing error or so. Let me just go through the code once. If for all it is correct, then we'll try running it so that it so that we can check upon whether it is working or not. Hopefully it should be correct. Let's just try running it on the ID. So there is the class we haven't ended with the semicolon. Yeah, so exactly our code is running. The output for first is 1, the output for second is 1. Like we were removing the front element is 1, so output is 1. Then we are dequeuing front element, the front element becomes 1 again, and 1 is removed from the queue. I'm doing cout queue dot get size. So get size is giving me the 4 values because 1 is already removed. Now if I'll again do queue dot dequeue, let's say what happens. I'm again copying and pasting this 2 more times, right? So this should give us 2 and 3 as the output. So it will become 1 1 4 2 3. Let's see if it goes well. So we have the output 1 1 4 2 3. Now let's check the size also once again. So the output should be 2. Yeah, so the output we are getting is 2. So we have successfully written the code for implementing our queue using array. I hope you people have understood this code. Now let's see how we can implement our queue using linked list, right? Hi everyone, so we have already seen how we implemented our queue using array. So similarly, another container that we have for implementing our queue is linked list. So we'll see how we implement our queue using linked list. As you people are already aware how a linked list is formed, we have different nodes and a node contains two parts. First part contains the data that the node possesses and the second part contains the address of the adjoint node, the node that is next to this particular node. Let's say this is node 1, we have node 2, we have node 3. So all these three nodes are connected to each other because in this part of the node the address of second node is stored, in this part of node 2 address of third node is stored, and if this is the last node that we have, then null is stored here, and this node contains the data, this node contains the data. So this is how a linked list is formed. So how we can use this particular concept to make our queue in a much more efficient way, or you can say in another way of making a queue using a linked list. So while making a queue using linked list, we have, let's say for every linked list we'll need to create something known as head. So we'll create a head in this case also. Along with that, as we have already seen in the case of arrays, we need to maintain a size variable. This size variable will tell us what is the current size of our queue, because if we are not maintaining it explicitly what is the size of our queue, we'll have to traverse the entire list each time we want to know the size. So rather than doing that extra work, we can maintain a variable named as size that can help us overcome that limitation, right? So initially what will be the value of head? My head would be null. The size initially of my queue would be 0 if I have no elements. Let's say I want to perform some operations on my linked list. Let's say I am doing enqueue, right? So we have already seen there are different operations in linked list. So if I want to perform an enqueue operation, let's say I'm doing an enqueue10. So what do you mean by this enqueue10? So enqueue10 suggests that I want to add 10 into my queue. Like 10 is the first element of the queue. So what will be the thing that is going behind if we are creating it using linked list? So the first thing that will happen is a new node will create. So how will create a new node? Let's say I'm creating this new node with data 10 and address is null. So this is something that will be created. That's the first thing that will be created when we have an enqueue10. Next thing that will happen is we'll point our head to this new node, right? And size will increase by 1. This is the first step that we will be doing, or that will be having when we are enqueuing one particular element into our empty queue. Let's say I again perform an operation enqueue 20. So when I say enqueue20, so what will happen again? Again, a new node will be created. Let's say a new node created this time is having the data 20 and null in its address pointer. So what is going to happen this time is I'll make the address pointer of my previous node point to this new node, right? And this size is going to be increased to 2. So now I have 2 elements in my queue and the size will increase to 2 correspondingly. So now my queue looks something like 10, 20 and null. This is something that I have in my queue. Let's say I do an enqueue30. What will happen? I'll create a new node with data 30 and null. The address of the previous node will start pointing to this 30 and will name this new node. What will happen is this 20 will start pointing to the new node 30 and 30 will start pointing to null. So we'll have our queue of something like 10, 20, 30, null. So everything is all right, right? Do you feel that if there is anything that is missing or that is lagging? Let's take a scenario. So what will happen in this particular scenario is, so now let's say at one particular point of time, I want to know what is the front of my queue. So what I'll have to return if I want to know the front of my queue? Simply the node which is present at the head. So what I'll do is I'll simply return heads data, like the node which is present at the first. So I'll return that. So that is basically the front of my queue. This is standing at the first position in the queue. So if there is an operation by the name of front, we'll simply return heads data. That will give us front, right? Also, one thing more, let's say I again want to do an NQ, right? So if I'm doing this NQ again, what will, like, I'll be given only the head of the linked list, right? So only the head of the linked list. For adding 40 to my linked list, I'll have to traverse from this 10 to 30 again, right? Each time I'm adding a new node into my queue or into my, let's say, linked list, so I'll have to traverse the entire linked list up till end. Like I'll go on to 10, then I'll move on to 20, then I'll move on to 30, and I'll see there's null in the address of 30, so I'll simply put 40 in the address location of 30. I'll create a new node with the address, with the data 40 and address as null, and I'll do it something like this. But don't you think it's much of work that we are doing? Rather than doing this, I will prefer making something that is known as a tail pointer. Along with head, I'll maintain a tail pointer. So tail pointer will be the pointer that will be pointing to the last node of my linked list. So we'll have a pointer for the head also, and we'll have the pointer for the tail also. The pointer for the head will be giving us the front element of the queue, and the pointer at the tail will help us to know the rear element of our queue. So how the things will change if we are making a head and a tail pointer along with the size pointer. Now you might be clear. Now we have three things. While making our queue that we need to make. Earlier we were having only our head and our size, but now we have introduced something known as a tail, right? So what will happen in this particular tail pointer is that we will see in the next part. So now you can see that let's consider another scenario. Now you know that we have three things. First is tail, next is head, and next is size. So now I have these three things through which I can define my queue using a linked list. Now again, I do an NQ operation, right? Like let's say I do an NQ10. What will happen? Again, a new node will be created. Let's say a new node will be created in this way with the data 10 and address pointer as null. This is the new node, right? What initially head and tail both are pointing to null. Size is 0. So as soon as I NQ a new element in my queue, the value of null changes to the head. The value of head pointer starts pointing to this new node. The value of tail pointer also starts pointing to this new node, and the value of size increases by 1. Now this is my first element in the queue. Now let's say I'm doing an NQ20. So what will happen in this case? I'll create another node with the data 20 and address pointer as null. So what will happen in this case is I'll start pointing my tail to this new node, and this address will be pointing to the address of this new node. So now I have a particular pointer that can give me the last element or the rear element of the queue at the first hand. So the size will increase to 2. Similarly, if we are doing NQ operation, let's say 10 times, what I'll have to do is rather than traversing over the entire list, I'll just point my tail pointer to the new node, and tails next will be I'll do tails next will be equal to new node, and tail will be equal to new node. Like this is the basic terminology that we'll be using when we'll be creating our linked list using our queue using linked list. So apart from that, like we have seen NQ operation, we have seen a front operation that gives the front element of our linked list. Also we'll see some more operations like get size. So get size at any point will return the size of my queue, so that will just need to return the size variable. Also there is something known as is empty. So is empty will tell us whether our queue is empty or not. We'll check if size equal to 0, then the queue is empty, else it is not. There's one more operation, that is dequeue. So what happens in a dequeue is how we can delete a particular element. Let's say we have 10, 20, 30 null. My head is pointing to this, my tail is pointing to this, size is 3. So this is a scenario. Now I call a dequeue operation. what happens in a dequeue operation is the element which is present at the front that we are going to delete, because it's a FIFO data structure. FIFO stands for first in, first out. The person who is standing at the first in the queue will be removed first, or he will be getting the movie ticket first. So now we have this particular queue. So what will happen is we'll remove this particular element, we'll store it in a temp variable. Its data will store it in the temp variable, and will return, dequeue will return first thing the data of our front element. Along with that, we'll store it in a temp variable. We'll start pointing our head to the next of our current head, and we'll delete this node. So in this way, we are going to perform a dequeue operation on our queue using a linked list. I hope the things are clear, a bit more clear. You will get a little more clarity when we'll try to code this on our own. So yeah, this is a brief about how we can implement our queue using linked list. Now we'll move on to the code part. So first we'll try to understand the structure of our code, then we'll try to code, right? So what all things are required to proceed with the code of our queue using a linked list? So firstly, we need to create a node. So how this node will be created? We'll simply create a class node, and it will be similar to what we generally create in a linked list. We'll create public data members like t data. Why I'm taking t? Because again, it's a templated data. It can be anything. It can be int, it can be char, or it can be anything else. Next is we'll create a node of the type node star next, that will contain the address of our current node, of our next node. Now I'll create a constructor that will store the address, so that will help us initialize our data members. So we'll point this data to data, and currently, like, initializing next is equal to none. So this is how we'll create our class node for making our linked list. Like, node will have first data member, that is data. Like, this is our node that we want to create. It has two members. First is this will be data, and this will be next. So initializing it will point out this data to data. This is a pointer that is used to store the address of our current object. So this will be storing the address of our current node. This data will point to data that we are supplying, and next will point to null initially. So this is the initialization of the node that we want, and we will be creating different functions. So we'll create our class queue also. So when I say I create a class queue, what all different data members we can think of in a class queue? So as I've already mentioned, we have three data members. That is, I'll create a node of node head, I'll create a node tail, and I'll create int size. So these are three data members that we'll have in our queue class, and then we'll make our public functions. What all public functions that we have discussed? We'll create something known as, we'll create a constructor again to initialize different objects of our queue. We'll write int get size, that will give us the size of our queue. We'll write bool is empty. We'll check if our queue is empty or not. We'll write void enqueue, and we'll pass on one element of type t. We'll return front element, and we'll dequeue our element of the queue. So these are the functions that we're going to create. Now let's move on to the code to see how we code this particular functionality, right? So we are on the ID. We'll be starting to code our queue using linked list. So firstly, as I've already mentioned, we'll create our node. So we'll create a class node. So inside this class node, I'll have public data members. So which public data members I'll have? I'll have data. Along with that, I'll have next pointer that will point to the address of our next node. So as I've created t, that is a templated data, I'll need to specify, like, now we know how to create a template type name t, right? Along with that, we'll have a node t of data, and we'll initialize this data equals to data, and next will be initially pointing to null. So this is basically how we have created our node class. Now we'll create our class queue, and then we'll try to dry run it and see how this works. So we'll have a public function. So what is there in this public? Like we'll have three public data members. So first is node head. We'll also have node tail. I've explained why we need tail pointer, and we'll have int size that will have the size of our queue at any point of time. Now we'll create a public functions. Firstly, we'll create our constructor queue that will initialize different data members of our queue. So we'll point our head to null, we'll point our tail to null. Initially both of them are null, and size is equal to 0. This is something that we have to initialize in our constructor, because initially there's no element on our queue. Our head will also be pointing to null, our tail will also be pointing to null, and the size of the queue is going to be 0. We'll next create int get size function. Int get size will give us, we'll simply return size. Next, apart from that, what all things which all functions we have discussed, one was get size, we'll simply return the size. We'll check, we'll create is empty function. So is empty function will tell us whether our queue is empty or not. What we'll do in this case is we'll return size is equal to 0. If the size of our queue at any point is 0, then like we'll check on, like if this condition is true, that size equal to 0 is true, then we'll return true to our bool is empty function, and if it is false, then we'll simply return false bool is empty. Next, that is something very important that we have discussed also. It's enqueue. Yeah, it's enqueue function will pass on our element that we need to add in our queue. So what happens in this enqueue function is, like as I've already mentioned, what we'll be doing in this case is, let me just explain you a little more. Yeah, so in this enqueue function, we'll have firstly what we'll do is we'll create a new node with the data as element. This is something that we're going to do in our enqueue function. Next, what we'll do is, if our queue is empty, like in the beginning our queue is empty, then we'll simply point our head to new node and our tail also to new node. Whereas in other cases, we'll simply move on this head pointer, and we'll try to see how it goes and how we are able to write this enqueue operation, right? So let me just start writing in the code for this particular function. So what happens actually is, we'll create a new node, that is node t star new node, and inside this new node, like we'll initialize it dynamically. Right, what next I need to do is, tails next will be pointing to new node, and we'll make this tail equal to new node. These are the three steps, these are the steps that we were doing each time, and we'll do our size plus plus. But do you think it is all right? Are we missing the case? Yes, we are missing the case when head or tail both are null. So that means our queue is not yet formed. So for that case, we need to initialize our both head and tail to our new node, and things will work in that manner. Let's do that. So what we'll do is, we'll put this particular condition, we'll put this edge case. If at all our head is equal to null, then what we are going to do is, we are going to make our head is equal to new node, tail is also equal to new node, right? And this condition we can put in else, like if our head is not equal to null, then we'll move on to doing this particular operation. And in both the cases, we need to increase the size of our new node. So in this way, hopefully our enqueue operation will be working. Let's see how we will be writing our front function. So t front, it will be returning us the front element of our queue, that is the element that which is present at the top. Let's say this is our queue. We have three elements, 10, 20 and 30. So for front, it will simply return the data of the head. But do we need to check anything? Yes, we need to check if at all our queue is empty or not. If at all our queue is empty, then we can't access heads data and we'll move on to a segmentation error. So before just checking upon the heads data, I'll put this condition: if is empty, if our queue is empty, then we'll simply return, let's say 0. Else, in all cases, we'll return our heads data. Right? I hope this is also clear. Next is dequeue function. So what happens in dequeue function is we need to remove the element which is present at the head node. So try thinking on what we will be doing in this particular cases. I'll try to show you with a help of an example, right? So make sure you check this example out. So what we are going to do in this case is we'll be having a dequeue operation. So what happens in a dequeue operation is, let's say we have this particular queue, 10, 20, 30 and null. So for dequeue operation, this head is to be removed. So when this head is to be removed, so we're discussing about the dequeue operation. Dequeue operation will have the return type as t because we'll return the element which we need to dequeue. So what happens in a dequeue operation is, let's say we have this particular queue with the first element as 10, then 20, then 30. And the last element 30 is pointing to the null. When we apply a dequeue operation, we'll need to return the element which is present at the front, that is element 10. So we need to return this 10. Along with that, we need to remove this 10 from our queue. So now consider a case, our head is pointing to this, our tail is pointing to this, and we have size as 3 currently. So what actually I want to do is, I will be returning heads data, right? And I'll be making this head to point to this 20 and then deleting this particular node temp. I'll make a temporary node and I'll store the data of the head, and I'll store the node head in the temporary data, and I'll make the head point to the next node. So in this way, I'll be able to remove this particular node from the queue. Along with that, we'll return the data of this node and we'll reduce the size by 1. The size will be 2. So let's try to code and see how we will be writing this particular part. So you can see that will be, firstly, we'll maintain an answer variable that will contain heads data. This is something that we are going to return at the end. So that's why I'm saving it in the priorly, because once we delete the node, we'll not have this data with us anymore. We'll write node t and we'll create a temporary variable in which will point to our current head. Then we'll make our head point to heads next. We'll delete the temporary node so that the data is free, the memory is free now, right? And we'll do size minus minus. At the end, what we need to return is, we need to return this answer. And I hope our dequeue operation is also done. Till then, let me just erase this, right? So now let's go on to the main part and try to see if our function, if our the code that we have written is running or not. What exactly I have to do is, I'll create my queue, let's say of integer variables. Let's name it as queue, and I'll perform certain enqueue operations. I'll do enqueue 10. So let's say I'm doing enqueue 20, enqueue 30, enqueue 40 and enqueue 50. And let's see different results. Like firstly, I want to have queue.front. Then I want to have queue.dequeue, cout, queue.dequeue again, cout get size. So let's see what we are expecting in these results, and let me just go walk over through the code if everything is all right. Let me just change the header file. T node T data next. I think it is correct. We'll see if there is any compilation error or so. But like what exactly the output that we're expecting in this case is q.front will be giving us 10, then q.dequeue will be giving us 10 again, then q.dequeue will be giving us 20. Then we have already removed two elements from an array, the size will become 3. So the output that I'm expecting out of this is 10, 10, 20 and 3. Let's see and run if it's working all right. There is some more compilation error. It's basically the T. Okay, get size function. So the mistake that we were doing is like we were not able to we were not initializing these as pointers. Now we are initializing them as pointer, and we'll try to run. We'll see that we are getting the exact output that we were expecting, that is 10, 10, 20 and 3. I hope this code is clear to you, and do try to make sure that you write this code on your own, you try to dry run so that you can get a better understanding on how to implement a queue using a linked list. Next, we'll move on to how a queue STL works, that is standard template library. What all functions are there in standard template library that we will not have to create all these functions again and again when we are performing different questions, different applications on queues. See you in another video. So now we've already seen how to implement a queue internally using an array as and a linked list. So now I hope each and everything is clear to you and you have implemented it yourself as well. Now I'm going to talk about QSTL, that is a standard template library. Like it's basically a library for that stores all the functions that we have already made, so that we can use it as and when required without having the need to make all the functions again and again. So this standard template library contains a library of queue, that is we can include it using hash include queue. It has certain functions that are similar to what we have discussed using arrays. We have made using arrays, so we'll try to solve certain problems using QSTL going forward. So the functions that we have discussed earlier are like we have discussed enqueue operation. It was taking an element t. So in STL, corresponding to this enqueue function, we have push operation, that is void push t element. Then we have also discussed t front, that was giving us the front element of the queue. Similar to that, we have front element in QSTL. We have t dequeue in our previous methods, and in STL we have void pop. So it is basically used to pop an element from the queue. We have also discussed about int get size. So rather than int get size, here we have the function known as int size. And the last function is bool is empty, that we have discussed. Corresponding to this, here we have bool empty. So we'll try to see how all these functions are implemented using QSTL and how we can solve certain problems using QSTL. But let's just move up on to the code part and then we'll discuss, right? So here, like first thing that we're going to do is we are going to add a queue class, a queue library, hash include queue. Now we'll simply, let's say, make a queue using STL, that is queue of integers queue, and we'll push the elements, that is, let's say I'm pushing 100. Similarly, along with 100, I'll push, let's say, 200, 300, 400, 500 and 600. So let's say I have pushed 6 elements in my queue, that is queue, and I am looking forward to output certain things, that is queue dot front, that will give me the front element of the queue. I am doing then queue dot pop. This will remove the topmost element from the queue. I'm again doing queue dot front. That will again give the new front element of the queue after removing one. I want to get the size of the queue dot size, and I want to check if my queue is empty or not. So what output I'm expecting is, let's see, try to run and see if there's any error. So now you can see I have this particular output that is coming. I have 100, 200, 5 and 0. Let's see if this is true or not. So when I say it's 100, so initially the first element of our array is 100, so that's why we are getting the output corresponding to this as 100. Then we are making queue dot pop. So from our queue that was initially like this, I am popping the topmost element, frontmost element. Now 100 is removed. Now my head is pointing to this. Now I'm doing queue dot front. Again, the front element is 200. I'll be getting 200 corresponding to this. Then I'm doing queue dot size. What is the size? 1, 2, 3, 4 and 5. So the size comes out to be 5. Queue dot empty. Whether it's empty or not, I'll get 0 or 1. If it is 1, that means the queue is empty. If it is 0, that means the queue is not empty. So we are getting 0. That suggests that queue is not empty. So in this way QSTL works, and further discussion of queue we are going to do using different practice problems. So next we'll be discussing some important problems of queues that are very, very important from the point of view of interviews. So make sure you watch till then. So now, as we have discussed what a queue is, how to build a queue, what is QSTL, how to build it using arrays and linked list. Now moving upon to further practice problems, different problems that can be solved using queues. So picking up very basic question, very important question from the point of view of interviews, that is how you can implement a queue using stacks. So we are going to discuss this very important problem. We'll try to see how we can improve upon the efficiency of this program. We'll discuss one approach, then we'll discuss some more approaches. Let's say how we'll be solving this particular problem. Consider two stacks. Like, we'll try solving it using two stacks. We have stack S1 and we have stack S2. So this is our stack S1 and this is our stack S2. And consider that, like, you people are already familiar of what a queue is and what a stack is. Queue is basically, as I've already discussed in very detail, that queue is FIFO data structure and stack is a LIFO data structure. From LIFO I mean last in first out. For example, this is a stack. The element is entered from here and it leaves from here. The element which is entered at the last will be getting a priority to move out at the first. Whereas in queue what happens is, it's another way. We have front end, we have rear end. Elements are added from the rear end and elements are removed from the front end. So we have to implement this particular data structure using our stacks. Now let's say we have these two stacks S1 and S2. With the help of these two stacks S1 and S2, I'm going to implement my queue so that it has the same functionality of FIFO data structure. How we can convert this LIFO property into FIFO property using these stacks. Let's say I have these two stacks S1 and S2, and there is a certain algorithm or the steps that we are going to use for solving this particular problem. Let me just write down those steps once so that we can discuss upon them with an example, right? So the first step is moving elements from S1 to S2, then pushing element X to S1, then third step, moving elements again from S2 to S1. So these three steps can help us solve this particular problem, and they can help us convert our property of LIFO of stacks to our queue. So let's say we have I have to push, like, the first operation that I need to perform is I want to push 1. When I'm pushing 1, what is the first step that I should go through? Moving elements from S1 to S2. Now currently our S1 is empty, S2 is also empty, so there's no element in S1, so I'll have to move nothing to S2. Now pushing X to S1. So X is this element, like I'm pushing 1 to my first stack, so I'll simply add 1 to this stack. right? Done. First step is done, second step is done. Now moving elements from S2 to S1. Like, are there any elements present in S2? No, there are no elements present in S2, so I'll not move anything, and our push 1 is successful, right? Similarly, let me do a push 2. So when I'm doing a push 2, first step is moving elements from S1 to S2. So S1 I have 1, so I'll be moving this 1 from S1 to S2. That's done. Pushing X to S1, like now X is 2, I'll be pushing this 2 to my S1. That's done. Now moving elements from S2 to S1. Again, I'm moving the elements that are present in S2 to S1. So what I'll be doing is I'll be moving this 1 from S2 to S1, and we are done. These two operations we have performed. We have performed two push operations. Now all the functionalities that we have seen in a queue, are they being justified by this approach? Let me just let's just try upon one more push operation, and then we'll see how other functions are there. Like, I'm pushing 3. So the first step is moving elements from S1 to S2. So all the elements present in S1 will be moved to S2. Let me move them. So firstly 1 is moved. Now 1 is written here. Now after 1, 2 is moved. Now 2 is written here. Now pushing X to S1. This time X is 3. So I'll be pushing 3 in S1. Then again moving elements of S2 to S1. Moving elements of S2 again back to S1. So I'll be moving this 2 first. 2 is here. Now I'll be moving this 1. 1 is here. And we have successfully made this particular movement. And now let's see how it goes. So according to our queue property, if I'm pushing 1, 2, 3, so the elements in our queue should be something like this. Element 1, element 2, element 3. So the element which is pushed at the first, like it is the front end, it is the rear end. Elements are added from here, moved from here. So this should be my actual queue. Let's see if this stack is actually solving my problem and it's helping me work out in a way that I want, right? So now different other properties of stack. Let's say if I want the top element of my queue. So to get the top element of my queue, that is the front element of the queue. So to get the front element of the queue, what I'll do is I'll simply do top. Like this is top in stack. Let's say to get the front element of our queue, I'll simply need to do the top of S1. So if I do top of S1, I'll get 1. That's the front element, and that's done. If I want to perform a pop operation, so what I need to do is I'll simply need to pop from S1. If I'll pop from S1, 1 will be removed from this and I'll get 1 as the output. Similarly, if I was to perform this on a queue, 1 will be removed from here and my head will move to 2. So front is also working, pop is also working, push we have seen, and all other functions will be performed in a similar manner. But now let's see what time complexity are we using while solving this particular approach. Let's say the time complexity is, because we have to, for each operation, we'll have to move the elements from one stack to another. So the time complexity that is taking it is O of n. Space complexity, what's the space complexity? We are using 2 stacks, let's say each of n elements. So the time complexity of both of them becomes n plus n, that is equal to O of 2n. Like we can take it as O of n only. So in this case, the space complexity and the time complexity both are of the order of n. So this is something that we need to work upon, how we can improve upon this O of n approach to something efficient, like little more efficient than this. Let's see how we can do that. Like this was the approach 1. Like we'll move on to approach 2 and see how that approach can help us make our code more efficient. So when I say approach 2, again we have to perform 2 functions, that is push and pop, right? How we can improve upon the complexities of push and pop. The first thing is, again what we'll be doing is we'll be taking 2 stacks again. This is stack S1, this is stack S2. So let's consider the push operation. I'll just need to push it simply in my stack. For example, I want to add push 1, push 2 and push 3. So for all the push operations, I'll simply push them in my stack 1, that is 1, 2 and 3. Now here, in the case of pop, I need to do something else. Let's just write down what all steps that we are looking forward to perform, and then we'll see how we can explain it using different examples. So for pushing x, what I'll do is I'll simply add x to my s1. I'm simply adding my x to s1, like these are x's 1 2 3. And for pop, let's say I have a pop operation, I'll make a check if at all my s2 is not empty. If my s2 is not empty, what I'll do is I'll take a variable output. Let's say we are having a variable output. In this output, I'll simply put s2 dot top and I'll remove s2 if my s2 is not empty. Else, if my s2 is empty, what I need to do is I will move all the elements from s1 to s2 again and will get the top element of s2 as our output. So let's see how this is done. Like I've written a very non-familiar approach or non-familiar algorithm. So let's see how we can solve it using this. If you people are not able to see this, so else condition I'm writing here again. Else s1 elements of s1 will go to s2 and then will pop s2, and this element will be the popped one element, right? So now let's say push 1. If I'm pushing 1, pushing 2, pushing 3, simply pushes will be adding the elements to s1. When I'm popping, if let's say I call a pop operation after this, now what I see is if s2 is not empty, but in our case s2 is empty, so I'll not move into this if statement, I'll move into this else statement. So what this else statement says that all the elements from s1 should be moved to s2. Now I'm moving all the elements from s1 to s2. Let me just move all the elements from s1 to s2. It's 3, it's 2, and it's 1. So now I have 1 2 3 in my s2 stack, and I simply need to pop s2. So if I pop s2 from here, 1 will be removed, 1 will be removed, and the same would have happened if I have these 3 elements in my queue, that is 1 2 and 3. 1 would have been deleted on popping. I hope this much is clear. Great. Now second time again, let's say I am doing a pop. So if I'm again doing a pop operation, what do I mean to do by this? For pop operation, like I'm saying if s2 is not empty, now this time s2 is not empty, what I'll do is I'll simply pop out the top element of s2, and by storing it in this variable output and returning this output, it can be anything, but now this time simply I'll return s2 stop, right? So this operation is performed in O of 1 time complexity. Push is also performed in O of 1 time complexity. This push is also performed in O of 1 time complexity. This is also performed in O of 1 time complexity. This push is performed, let's say, in O of n time complexity. Another push pop operation is performed in, like 2 is also removed, 2 is also removed. Next is 3. Now again I'll see if s2 is empty or not. s2 is not empty. Again I'll simply pop out s2 stop. 3 will be removed, 3 will be removed, our stack becomes empty, and we have successfully made the functions push and pop for our queue using our stack. Again for this pop also the complexity will be O of 1. So like for most of the operations, let's say like for some operations in pop, there might be the complexity will be O of n, but for most of them, as s2 is not going to be empty in all the cases, it is O of 1. So we can say that amortized complexity in this case for push and pop operation is O of 1, big O of 1. So we have been able to successfully move from O of n complexity to O of 1 time complexity. Now let's see how we can solve this question, how we can solve this particular question using our code. So let's move on to the coding part. Now let's move on to the code part. Inside the code part, like we have a same question where we have to implement queue using 2 stacks. So what we are given is we are given to implement a queue using 2 stacks s1 and s2, and you have to push and pop. You have to create push and pop operations. As we have seen in our second approach, basically push is just we are pushing our element in stack S1. So I'll simply write S1 dot push and I'll mention the element that is X. But what we are doing in pop operation is, like I was checking, the first condition that we were checking is if S2 is not empty. If S2 is not empty, then what we were doing is we were simply let's say I take an input int output variable in which I'll be storing out my answer. I'll be putting out output is equal to S2 stop, right, and then S2 dot pop. So this I am doing, I am simply returning the element which is present at the top of the S2 if S2 is not empty. Now let's move on to else part. Let's say if our S2 is empty. So what we'll be doing in that case is we'll simply move all the elements from S1 to S2 while our S1 is not empty. While our S1 is not empty, what we'll do is we'll simply move all the elements from S1 to S2. So for moving all the elements from S1 to S2, I'll simply push on elements from S1 dot top, and side by side what I'll be doing is I'll be popping out elements from S1 dot pop, right? So all the elements from S1 will be moved to S2. Now I'll again make the same check. If at all our S2 is not empty, then I'll again do the same thing. Output will be equal to S2 stop and S2 dot pop. Else, if our S2 is empty, then what we'll do is we'll output -1 because there's no element that is left. So at the end what we'll do is we'll try to return output and see how it goes. So this is basically the approach that we have discussed. What we are doing in this approach is for push operation we are simply pushing in our element in stack S1. For pop operation we are checking in if our stack 2 is empty. If our stack 2 is not empty, then we are simply returning the top element of stack 2 and popping out that element. Else we are moving all the elements from S1 to S2 until and unless like stack 1 is empty, then we are simply returning the topmost element of stack S2. If there is no element in stack S2, we are outputting -1. This is the approach that I think should work. Let's just try to compile and run if there is any error. So yeah, we are getting the output for the given input. Let me try to submit and see if it goes well. Yes, we have successfully solved this particular problem, and yeah, that's done for this particular problem. Let's move on to our next problem. As now we have already discussed how to implement queue using stacks, so now there is another way around. We'll be discussing in this problem. This is the second problem in which we'll be discussing about how to implement stacks using queue. So we'll see two variants, how we can implement stack using two queues and how we can implement stack using a single queue. So both the variants we are going to see, and these problems are basically made to be done so that you people are more familiar with the concepts of queues, so that you can implement them basic functionality of queues on your own. So when I say stack using two queues, let's take an example so that we can understand the approach, what exactly we are looking forward to. So stack using two queues. So let's say I have this q1 and I have this q2, and I want to push certain elements, so that what happens in a stack is, like, we have a stack of this particular form and we keep on adding elements from the rear end. Like, let's say I'm adding 1 2 3 4, and it's a lifo data structure. The element which is added at the last will be removed first. So 4 is added at the last and 4 will be removed first. So simply, let's say I want to push these 4 elements. Let's say push 4, push 3, push 2 and push 1 in my stack, right? Let's see how we can do this by using these two queues, Q1 and Q2. There are various steps that are involved in the process. Let's say I'm discussing about the steps. So the step 1 is insert the element in Q1. Next, what we'll do is we'll push the remaining elements of Q2 to Q1. And last step is we'll swap the elements of Q1 and Q2. So this is basically done for the push operation. Let's see how it works. Insert the element in Q1. The first step is insert the element. The first statement that I'm going to run is push 4. So 4 will be inserted here according to our algorithm. Now we'll push the remaining elements of Q2 to Q1. As Q2 is already empty, so we don't need to insert or move anything from one queue to another. We'll swap the elements of Q1 and Q2. Now third step is we'll be swapping the elements of Q1 and Q2. Q2 has no element, Q1 has one element. So after swapping, what it becomes is it goes something like this. 4 is here and Q1 is empty. R4 is done. The next element that we are going to do, we are going to push is 3. So what happens to 3 is insert the element in Q1. So I'll insert 3 here. Push the remaining elements of Q2 to Q1. So remaining elements of Q2 are 4 only. So I'll move this 4 to here and 4 will be removed from this queue. Next, swap the elements of Q1 and Q2. If I'll be swapping the elements of Q1 and Q2, both 3, 4 will be moving to Q2. So it will go something like this, right? Now I'm again doing push 2. What happens to 2? 2 goes here. I push the remaining elements of Q2 to Q1. I'll push 3 and 4 to Q1. Now what happens is I want to swap the elements of Q1 and Q2. Swapping the elements of Q1 and Q2, what will be there in Q2? It will be again 2, 3 and 4, and 2, 3, 4 will be removed from here respectively. Now see, our Q2 acts as our new stack. How Q2 acts as a new stack? Like let's say we are to push 4, 3, 2, 1 in our stack. So how will we be pushing them? We'll be pushing them in this form. 4 will be added here, 3 will be added here, 2 will be added here in this way. So the element which is added at the last, let's say we have added 2 at the last, it will be removed first. Now if we are to pop an element from the stack that we're implementing, so we'll simply do pop, and the pop function will remove the firstmost element or the frontmost element of the Q2, and it acts as our stack. So in this way we will be performing our stack operation using two queues, Q1 and Q2. Now if we are to perform the pop operation, we'll simply what we'll do is we'll check upon if our queue is empty or not. If it is empty, then we'll simply output let's say -1. If it is not empty, then we'll simply return the frontmost element of the Q2 to implement our stack. Now let's see this approach in the form of our code. So we are to implement stack using two queues. We have two functions, that is push and pop function respectively. So how will we writing the code for push and pop? It's the same thing that we have done. We have discussed the approach for push, the same thing that we are going to do. The three steps, the first step was we were to insert this element X into our queue Q1. So what I'll do is I'll push this element X in Q1. The next thing after this was to put all the remaining elements of Q2 to Q1. So to put all the remaining elements of Q2 to Q1, we'll run a loop until and unless Q2 is empty. What we are going to do is we are going to add the elements in Q1. What happens after that is we'll remove the elements from Q2.pop. The last thing was we were swapping the elements of Q1 and Q2, right? So I'll simply use a swap function, swap Q1 and Q2, and we are done. So this is how our pop function looks like. It's very, very simple. Now let's talk about the pop operation. Pop operation is also very simple. I'll just put a check if our queue is empty. We'll check upon if our Q2 is empty. Then we'll simply will not do anything. Let's maintain a variable int output. Like we'll put output is equal to -1 if our queue is empty. This is a check that we are putting. Else what we'll do is we'll in this particular output variable we'll put q2.front and then we'll do q2.pop. So in this way our output will be there. We'll return our output, and this is how our code for stack using 2 queues is written. Let's try to compile and run and see how it goes. Let me try to submit. So it's getting submitted. We have successfully solved the problem of making a stack using 2 queues, right? Now we have already seen that how we are implementing a stack using 2 queues, but what if we are asked to implement stack using just single queue? So what we'll do in this case is, let's just do second part, stack using one queue, and we are to implement our stack. Similarly, like we are implementing the function, let's say push 1, push 2, right? So what happens in this is, like, let's say I'm pushing 1, the first element is added in our queue. Now the size of our queue becomes 1. What I'm supposed to do is, I'm supposed to remove size minus 1 elements, that is, I'll pop these size minus 1 elements and push them again. So what will happen in this case is, like after this 1 is added, so size minus 1 is, like, size is 1, so 1 minus 1 is 0, so no element is going to be removed, no 0 element is going to be removed and pushed again. Now I am pushing 2, so when I push 2, what I'm supposed to do is, I will be removing size minus 1 element, that is, now when I add 2 to my queue, the size becomes 2. Now size minus 1 elements, that is this one, is to be removed, is to be popped from this queue, and is to be pushed again into this queue. That is, our queue will look something like this. 2 is here and 1 is added here, right? After this, let's say I am again pushing in my element 3. So when I'm pushing in my element 3, so what I'm supposed to do in this case is, I'm supposed to push this element in my queue. I'm supposed to push 3 in my queue, and now the size becomes 3, so I'm supposed to move size minus 1, that is, the previous 2 elements I'll remove, I'll pop, and I'll push them again. So it becomes something like 2 and 1, right? So now what happens is, this queue, it looks exactly like how a stack will work. Stack was supposed to work like this. I am adding 1, then I am adding 2, then I am adding 3. So last in, first out. 3 is added at the last, 3 will be removed at the first. Similarly, now the queue that we have got, the queue that we have implemented as a stack, if we perform a pop operation on this queue, what we'll get is, we'll get 3 as the output, right? If we perform top, that is the front element that we are getting, we will be getting the front element, that is the element which is at the topmost. So it acts similar to how a stack works, right? Let's just go through the code once on how we are going to implement this particular functionality in our code, right? So the same thing happens, like, let me just open up my code editor. So what happens in this case is, like, I'll not be using 2 queues but a single queue. Let's say I'm using q1. So what is the first step? I'll simply push the element x in my queue q1. Next thing is, I'll calculate the size, int size, it's equal to q1 minus q1's size minus 1, right? After this, what we are going to check, until and unless this size is 0, all the size minus 1 is 0, what I'll do is, I'll keep on pushing and keep on popping. So in the q1 only, I'll push q1 dot front, and side by side I am popping these elements. So this is the code that we are going to write for push. I think it is done. Pop operation will remain the same. Instead of q1, we are just using q2, we are just using q1. So q1 will be replaced everywhere, and I hope this should work. So we have seen that this is working. Stack using 2 queues have been successfully implemented. Now let's move on to our next problem. Hi everyone, if you're liking this course, if you're liking the videos, if you're liking the type of questions that we are discussing, so consider subscribing this channel, because we'll be bringing some more amazing content, some more amazing topics related to data structures, algorithms, related to system design, and more that can help you become a better software developer. So now we're going to talk about something known as a Dequeue. Some people also call it as it's also named as Dequue. Some people also call it as Dequeue. It is implemented using a doubly ended linked list. You can say it is a generalized version of queue data structure that allows insertion and deletion at both ends. Like what was happening in general queue, like queue was something like this. We had this kind of structure, and we were able to add the elements from rear end, and elements were removed from the front end. But what is happening in a Dequeue is everything remains the same. It's just that you can add the elements from the rear. You can also remove the elements from the rear. You can add the elements from front, and you can remove the elements from front. So there are different operations that we will be seeing in this Dequeue operation, that is similar to what we have seen as pushback. This is used to push an element from the back. There is something known as push front, used to push the element at the front. Let's say 2, let's say 3. We are pushing 2 from the back and 3 from the front. Now let's say I am pushing pushback 1, so 1 will be added here. Now pop back and pop front. So pop back and pop back will remove this 1, pop front will remove this 3. We'll have only 2 left. So we'll see the implementation a little bit of how Dequeue works actually, and different other functions. Like if you want to output some of the numbers, which are elements which are there in this Dequeue, we'll be using the functions known as front function. Similar to that, we'll be using back function. There's something known as add function, like the element which is present at second location. So the add suggests second location. So we'll see how it is actually implemented in the code. And yeah, so we are there on our ID. We'll include the header file hash include Dequeue, and we'll create our own Dequeue. Let's say integer variables and Dequeue. I'll add Dequeue dot pushback, let's say 3. Let me just copy paste this. Pushback 2, pushback 1. Let's also try Dequeue dot pushback push front 5, Dequeue dot push front 6. And now let's see if we are getting the correct output. Dequeue dot front. So what I'll be getting at the front, cout Dequeue dot add 3, the number which is present at the third index. Cout Dequeue dot back. Let's see how these actually work. Then we'll see if we are doing the correct thing or not, right? Yeah, so we have got the output as 6, 2 and 1. Let's see how this output 6, 2 and 1 came. Like we were pushing, like the first element that we pushed was 3, 2, 1, 5 and 6, right? So we were getting something like 3, we did a pushback 2, 1, then we push front 5, then we push front 6. So this was the queue that was made. So now when we were accessing the front element, so we should get 6. When we are getting the back element, we should get 1. And when we want add 3, the element which is present at the third location, so let's see if we are getting the correct answer. So we are getting the answer as 6, 2 and 1. So you can see the number which is present at the front is 6, correct. Number which is present at third location, that this is 0, 1, 2, 3. So output is 2, that's correct. And the number which is present at the back, that is 1, it's also correct. So I hope you are clear with the basic functions of Dequeue. Now we'll try to solve some problems that use that has an application of Dequeue, and the problems can be solved in a much easier way. So we'll see the problems related to Dequeue. So let me read out a question for all of you. Now we know the concept of dequeue. So the question goes something like this. So basically I'll be reading out the question. I'll try to explain you what the question suggests. So you are given an array of integers, let's say nums, and there's a sliding window of size k, which is moving from very left to of the array to the very right. You can only see k numbers in the window each time the sliding window moves right by one position. Let's say, what is the question saying? The question's name goes like this. It is known as sliding window maximum. You'll find this question on lead code in the harder level. It's lead code hard question. So the question goes something like, let me explain the question with the help of an example. You have an array named as nums. Inside this array you have, let's say, numbers like 1, 3. I'm taking the same example as that given at lead code so as that you can understand it better. 7. So this is the value of nums, and you are given a value of k equals to 3. So you have to give me an output array that should be something like 3, 3, 5, 5, 6 and 7. So the question goes something like this. What exactly you have to do is, like, this is the array. Inside this array there is a value of k given. You have to check all the sub arrays starting from the first element of the array, and check for all the sub arrays of size k, which is the maximum element. Let's say you have this particular array 1, 3, minus 1, minus 3, 5, 3, 6 and 7. So the first sub array of size 3 is this. So which number comes out to be the maximum? This is, it's 3. So we get the answer as 3. Now the second subarray starts from here. So this is the second subarray. The maximum element among all of them is 3 again. So for this is the third subarray. Maximum element among them is 5. Next, this is the next subarray. It starts from this minus 3. The maximum element among them is 5 again. Now this is the new subarray. The maximum element among them is 6. Now again the maximum element among them is 7. So our output looks something like this, and this is exactly what we have to do in this particular question. So we'll start from 0th position of our array, and we'll go on till the 5th location of our array, like 0, 1, 2, 3, 4, 5, 5th location of our array, and we'll be done. So this is basically what we want to do in this particular question. So let's say this question comes up to you in an interview. So the first approach that you might think of in an interview is the normal brute force approach. So let's try and see how the brute force approach will work in this particular case. So what exactly you have to do is, you have to do nothing. You'll have to start from the 0th index. You'll have to go till this 5th index, and you have to run a for loop. You'll go from this, you'll go until 5th index. Then inside this you will be checking each subarray, like subarray starting from 0th to I plus k minus 1. So I plus k minus 1, that means the subarray of size k, and inside them you will have to find the max number. So the very simple code for this in brute force would be for loop that will be running from 0th location to 5th location for this particular case, and inside that you'll have to go from I to I plus k minus 1. So why I'm saying I plus k minus 1, what does that say? Let's say take the value of I equal to 0. For I equal to 0, it goes from 0 to 0 plus k is 3 minus 1. So it goes from 0 to 2. That is, our first subarray is from 0 to 2. Let's say second subarray, it starts from 1 to 1 plus 3 minus 1. So it goes on like 4 minus 1, it's equal to 3. So our second subarray goes from index 1 to index 3. So inside this we'll find out, we'll calculate our maximum of array of j, or the maximum. So whichsoever element inside that subarray is the maximum, will be getting as the output, and our code will be done. Let's analyze what would be the time complexity in this case. So the time complexity in this case would be like firstly we are running a loop from 0 to fifth location, that is all the elements. So it will be O of n into what is this, we are again running a loop for each of the subarray, that is for k elements of the subarray. So the overall complexity comes out to be O of n into k. That's something that we don't want. It kinds of look like quadratic, hence we need to think upon an efficient solution. So what helps us in this particular state is the data structure that we have discussed recently. Which data structure we have discussed? We have discussed about dequeues, right? So what exactly we'll do is we'll try maintaining a dequeue so that it can so that we can solve this particular question. Like, let's see the approach of a dequeue on how we'll be approaching this particular question. So again, I'll be writing upon the question exactly what the question says. We'll be having the same array, that is 1, 3, minus 1. It was minus 3, I guess. Yeah, minus 3, 5, 3, 6, and 7. So this was the array that was given to us. We'll try to run our approach of dequeue on this particular array, and we'll try to see how we can solve this question better, right? This is the array. These are the array indexes, and we are given the value of k equals to 3. So what exactly we have to do is we'll have to maintain a dequeue. Dequeue, as you people know now, like it's a new form of queue in which we can push at the front, pop from the front, push at the back, pop from the back. So all these 4 operations are possible. It's implemented using a doubly ended queue. I have also shown you how a dequeue works in an STL. So now we'll maintain a dequeue. Let's say I'm maintaining a dequeue. I have this kind of a dequeue, right? So the thing, like basic intuition behind this is like we'll have to maintain a decreasing order of elements. What I mean to say by decreasing order of elements is like you'll have to start calculating from the very first of the array. So we'll go and see for this particular array, like we have the first subarray starting from 0 and it ends at 2, right? So out of this particular array, let's go on to the first index. So first index is 0th index and we have the element as 1. Now as it's the first index, our dequeue is empty. What we'll do is we'll simply add the index of our first element in the dequeue, right? And we'll try if there is any element that is before this and are they maintaining a decreasing order. Like here we'll see if it is maintaining a decreasing order. So what I'll do is I'll check for 1. So there's no element, so I'll put 1 in this decreasing array and see how it goes, right? Subsequently, like that's done. Now we iterate. Well, we will move on to the next element of the array. The next element of the array is 3. The index on which 3 is present is 1. So we'll add 1 here, but before adding 1 here, I'll see what is the value of the element present at 1. So the value of element present at 1 is 3. So if I add 3 in my array, will it be in decreasing order? No, it will not be in decreasing order. If I'll add this, so 3 is anyways bigger than 1, so this doesn't go in the correct way. Hence it will not matter whether this 1 is there in my decreasing decreasing array or not. So I can remove this 1, I can remove this 0, because anyways, like if this is my sub array, so if I have an element which is bigger than 1, so no matter how much I can do, this 1 is not going to matter at all. Matlab, इस array में we'll have, once we have 3, so this 1 has no importance at all when we consider the maximum element that is present in the array. So we'll remove this 0, right, and we'll add this 1 in our array. So now 1 is the element. Now we have removed this 1. We have 3 as the first element of our decreasing sequence, right? That's fine, perfectly fine. Now we move on to the next element. The next element is -1. We'll check in our decreasing sequence whether -1 goes in the decreasing sequence or not. Yes, -1 perfectly goes in the decreasing sequence. -1 is lesser than 3, hence if we put -1 here, our decreasing sequence is maintained. Now we'll check upon, now we can, like if decreasing sequence is maintained, we'll put on the index of this in our dequeue and it goes something like this. Now, a very important point to note at this point is, now our first subarray is over. Like as soon as we reach the second index, our first subarray is over. Now we need to have an output array. Like this is the array that will be storing our output. And how will be generating, how will be calculating that output, we'll see throughout the process. Right now, as soon as we reach the first subarray, like the first subarray is over, now what we'll do is we'll check upon what is the element at the front of this particular dequeue. The element which is present, the index which is present at the front of this dequeue, and the element corresponding to that particular index, will put it in our output array. So here the index that is present at the front of our dequeue is 1 and the corresponding element is 3. So we'll put 3 in our output array, and that's done. Right now we'll go on and see, we'll go on and check for our next array element. So for next array element, we see, when we move from -1 to -3, we'll see if -3 goes with this decreasing sequence. Yes, -3 goes on with this decreasing sequence. If we'll put -3 here, again a decreasing sequence is maintained. If a decreasing sequence is maintained, we'll put the index of -3 in our queue without doing anything, and we are done. Now as soon as we reach 3, right, as soon as we reach the third index, we have one more subarray completed. Earlier we traversed upon first subarray. This is the first subarray. Now second subarray is also done, and if a subarray is completed, what we'll have to do is we'll look again towards the front of our dequeue and see if there is like what element is present, or what index is present. We'll write the element corresponding to that particular index in our output. So now again, 1 is present at the front of the dequeue. Which element is there at the first index? 3 is present at the first index. We'll put 3 in our output array. Clear till here? I hope this much is clear to all. Next thing that we are going to do is we'll move on to the further array elements. When we move on to the further array elements, like we have 2 subarrays completed. After 3, we'll move on to 5. Now tell me one thing. Once we move on to the third subarray, that is this particular subarray. So the first thing that is very important thing is, now we have crossed this, like this element is not going to come in any subarray. We have crossed this element. Now after the second subarray is over, we have crossed this element also. Now this subarray element is not going to come in any further subarray. So if this happens, like this is basically the element which is going out of bounds as soon as we move to our new subarray. So now this is of no value, no significance to us, so we can simply remove this element from our decreasing sequence also, and from our dequeue also. Now we have moved upon to this, and we have removed that element from our decreasing sequence. Right now we have an element 5. Now if we put 5 here, do you think our decreasing sequence is maintained? No, the decreasing sequence is not maintained, so we'll not put 5 here. Instead what we'll do is I'll not put 5 here. I will now I'll check upon in my dequeue whether putting 5 is all right. No, 5 will not help us maintain this decreasing sequence. Rather than that, we'll check upon, now in this particular array, like -3 will be of no significance once 5 comes up. So we'll compare this -3 with 5, as they are not able to maintain the decreasing order. So we'll remove this -3, and we'll remove this third index from our array. Again we'll check with -1. -1 is also smaller than 5. We'll remove the index also, right? So, and we'll put this index in our array, that is 4. Now 5 comes here. We'll start from the again, like we'll start our decreasing sequence once again. 5 is the single element that is present in our decreasing sequence, and 4 is the corresponding index to 5. Now what happens is, now our third subarray is completed. We'll again look forward to what is the index present in our dequeue, and we'll put the corresponding element in our output array. The corresponding element in our output array goes like 5. So we'll have 5 in this output array, and we'll move forward. Right now the next subarray that we are going to see is this subarray. Right now we'll see if how it goes, like whether like the new array element that we have is at fifth index and the element is 3. Now if we put 3, are they maintaining a decreasing sequence? Yes, they're maintaining a decreasing sequence. If they're maintaining a decreasing sequence, what we do is we put that array index into our dequeue. So 5 goes here, and now we have one more subarray completed. What we do once the subarray is completed, we'll look forward to the front of our dequeue. The index corresponding to the front of dequeue is 4, so we'll put the element corresponding to 4 in our output, and that's done. Right now what happens is we'll check upon for another subarray. This subarray this time has sixth element. Now once again, is 6 will 6 help us maintain a decreasing sequence? No. Because why? Because 6 is, first of all, 6 is greater than 5, also greater than 3 also. We'll compare 6 with 3. As 6 is greater than 3, we'll remove 3 from our queue. We'll remove this 5 from our queue also, because 3 was the element that is present at the 5th index. We'll compare 5 and 6. Again we'll remove 5. We'll remove the 4th index corresponding to this also, and we'll put 6 in our queue, dequeue, and we'll again start this decreasing sequence from 6. Right now again our new subarray is completed. We'll look forward to the front of the dequeue. The index present is 6, the element corresponding to 6 is 6, and we have 6 as the output. Now the last subarray for this particular example is this. What happens is, like, we'll see 6 is there. There's the new array element we have is 7. We'll check if 6 and 7 maintain a decreasing sequence. No, they don't maintain a decreasing sequence. We'll remove 6 from here, we'll remove 6 from here, and we'll add 7, and 7th index is added here. Now we'll again, our new subarray is completed. We'll again check from the front of the dequeue whether this goes with the whether this our subarray is completed or not. Now we'll look forward to, from the front of the dequeue, we have this index 7, and the element corresponding to index 7 is 7, so we have 7 at this particular output. So now we are done with this particular question, we are done with this particular example, and we have the output array that is giving us the correct output. So now think on what would be the time complexity in this case. So the time complexity in this case would be O of n plus O of n. We can say that it's close to O of n. Why it is O of n? Because like we are doing two things. As soon as we move to the new subarray, we are removing an element which is out of bound. So it goes on for O of n time complexity, and we are comparing that element with the previous element, and we are correspondingly adding that element to the queue or not. So it also causes O of n time complexity. So overall, if we see, the time complexity comes out to be O of n, which is far better than what we have seen in our brute force approach, right? So this was all about the approach that helped us solve this problem using Dequeue. Now let's move on to the coding part and see if we can submit this problem on LeetCode. So now you can see the same question we have on LeetCode. The question is by the name of sliding window maximum. It's in the hard level. So what we are given is, we are given a vector nums, that's the input array, and we are given a value of k, that is the length of our sliding window, like that's the length of our window. Now what we did in this particular question was, our efficient approach was, we made a dequeue. So of type integer, let's name it as let's say deq. This is the name of our dequeue. We'll also maintain a vector that will contain our output. Let's say we'll name it as vector output, right? So what we have done in this case is, we'll iterate from for int I equals to 0 to I less than nums dot size and I plus plus. We'll iterate. After that, what we are going to do is, we are going to put a check upon the out of bound index. Once we are moving from one subarray to the another subarray, we were checking if that particular element is there in a new subarray or not, like whether the index that is present in the dequeue is there or not. If that is of no significance, we'll simply remove that element from our dequeue. So what happens is, we'll check if at all our dequeue is not empty, because like if it is empty, so we can't remove any element from the dequeue. That's obvious check.
it will give a segmentation error if we'll not put this particular condition. And we'll check if Dequeue's front is equal to I minus k. Why am I writing this I minus k is because let's say you have this particular like this is the array that we have, and like let's say I'm suppose at this particular condition position I, before this there are certain k elements, and this element would be I minus kth element. So we'll check if this is the element which is present at the front. If it is so, we'll remove this, right? So this, if this is I, this will be I minus k. That's why we are checking if this goes like this. What we'll do is we'll simply do a dq dot pop front, and that's done. So this is the condition basically that is used to check if our sub array is going out of bounds, right? Now again there is a second condition that we are checking to compare our elements whether they are maintaining a decreasing order or not. So we'll again check while our dq is empty, until and unless our dq is empty, and nums of dq dot back, the last element will check if at all it is less than or equal to nums of I. So what we are going to do is we are going to dq dot pop back, that is we are going to remove the element from the back of our dq, right? That's done. This is the second condition that we have written. This is basically we are checking that, comparing the elements, right, if they are maintaining a decreasing order or not. The next thing that we are going to do is dq dot push back I, we'll push back the index if both the conditions are not met. Push back I, right? And at the end we will check if at all, like this is the case, like finally we are putting that element which is present at the front of our dq once our sub array is complete. So if I is greater than equal to k minus 1, that is our sub array is complete. So what I'm going to do is in our output vector we'll push back, what will push back, we'll push back nums of the front element that is present, will simply push back the element present at the index dq dot front. ठीक है जी? So I hope this is should be clear, and what will return will simply return output. I hope this should be okay. Let me just see if there is any error. There might be. I'll try to include this class hash include dq. If there is anything else, let's check it once again. I think we are good to go. Let's try to run this, and we are getting the correct answer. Our output is this, expected is this. Let's submit. On submitting, we are getting that this question has been submitted successfully, and that's done. So finally our question is accepted, and now let's move on to another such problem that can be solved using a Dequeue.
So let's discuss another question. Another question that we're going to discuss is basically about interleaving the first half of the queue with the second half. So the question goes something like, although the question seems to be really simple, but there are some operations. Majorly, you'll have to be very good at push and pop operations so as to be able to solve this particular problem. So you will be given a queue of integers. So this is the input. Queue of integers you will be given of even length. Let me read out the question. And you have to rearrange the elements by interleaving the first half of the queue with the second half. You have to rearrange by interleaving first half and second half. Also, there is one condition given, that is use only one auxiliary stack. This is the condition that is given. This is very, very important. So what do I mean to say by this question is, let's take an input. Like this is the input. You have an input 1, 2, 3, and 4. So the output that you will be requiring from this particular question is 1, 3,
2, 4. So how you'll get this output from this particular input is it goes something like, let's say we have this particular, like this is the queue you will be given as input 1, 2, 3, and 4. You divide this queue into two different parts and then take one element from the first queue and take second element from the second queue. So it goes like first element from the first queue is 1, first element from the second queue is 3, first element from the second element from the first queue is 2, next is 4. So you get an output similar to this, right? But there's no possibility that we can divide the queue into two different parts and then take the front portion or the front of both the parts of the queues. So and also we can't use two queues. If we were given a chance to use two queues, what we would have done is we would have created Q1, we would have created Q2. I would have pushed the first two elements here, next two elements here, and I would have done it like one first element like popped from the first queue, then first element popped from the second queue, then second element popped from the first queue, then second element popped from the second queue, and I would have got the answer. But we are not allowed to do this. We are allowed only one auxiliary stack. So what we need to do is we need to go something like this. Let's discuss with that particular example only, then we'll generalize the steps that we have taken while solving this particular problem, right? So we have this particular queue, we are given this queue. Inside this queue we have 1, 2, 3, and 4. So and you can take one stack as per your choice. This is the stack I have taken, right? So initially what you need to do is you need to push the first half of the elements of the queue to stack. So pushing first half of the element of the queue to stack, that means uh, I will be removing this from here, and it will go into the stack like this. Let's say I have the stack named as S. What happens next is you have to enqueue back the stack elements. So these elements are to be enqueued back. So the queue becomes something like this. In this next step, it becomes 3, 4. If I pop this 2 from the stack and add it to the queue, it will go something like this. And then I'll add 1, right? Now my stack again becomes empty. Next step is I will be dequeuing the first half elements of the queue and enqueue them back. So these two elements, first half of the elements, I'll dequeue and I'll enqueue them back. So my queue becomes again something like this. So if I'll dequeue this 3, it will move back, it will be added here. 4, it will move back, it will be added here, and I'll get something of this sort, right? Now again, what I'm supposed to do is I'm supposed to uh, pop back first two elements of the queue and push them into the stack. Now my stack becomes 2, 1, and my queue becomes 3 and 4. Now you can see it's very easy for us to interleave. Now once we are into this condition, we can interleave both of them. What I mean to say by interleave is I'll take one element from the stack and I'll take one element from the queue and I'll simply print. So inside my queue, what I'll do is I will take one element from the stack, one element from the queue, one element from the stack, one element from the queue, and we are done. We get this as our output. So if you have to generalize the steps that we have taken, we can generalize the steps as like we have taken these particular steps. The first thing that we did was we have pushed the first half of the elements of the queue to stack. Second thing is we have enqueued back the stack elements. Next is we have dequeued the first half elements of the queue and enqueued them back. Next is again we push the first half elements to stack, and the last step is we interleave, right? So this was the approach that we followed. Now let's move on to the code and see how the code functions. So now you can see we have written the code for that particular question. What exactly was given is like I have made my own queue by the name of q int q. I have pushed four numbers 1, 2, 3, and 4. Like I'm taking the same example that was given that we have discussed initially. Now calculating the size of this particular queue by q dot size, then calculating half size, that is n by 2. You can just do n by 2 in the question itself. That doesn't make any difference. I have initialized one stack, that is the auxiliary stack that we're going to use. The first step. So the first step basically was to push the first half of the elements of the queue into stack. So first half of the element, like I'm running a loop till half of the size of the queue. Then we are pushing those half elements in the stack, and simultaneously those elements are popped from the queue. Next step was enqueue back the stack elements. Now those until the stack is empty, I'm enqueuing back those stack elements to the same queue. Third step was dequeue the first half elements of the queue and enqueue them back. So I am dequeuing the first half of the elements, like queue front is removed and queue and it's popped. It's added back, pushed back to the queue, and it's popped back. And the next step is pushing the first half elements to the stack. Now again, those first half elements were pushed to the stack. Finally, this step is basically an interleaving step in which I am taking one element from the queue and pushing it of taking one element from the stack and pushing it into the queue, then popping that element from the stack, also pushing one element, take at the same time taking one element out of the queue from the front and pushing it from the back, and again popping that element until and unless this stack is empty. After that, this loop is just to print the queue elements that we have at the end. So let's see what goes with this particular code. Like if I'll run this code, I'm getting the output as 1, 3, 2, and 4. Let's try with some more examples. Let's say I have till 10. If we have this code running till 10, let's see how the output changes, right? So I'm trying to run this. So you can see we have again 1, then 1 to 5 will be separated and 6 to 10 will be separated. 1, then 6, then 2, then 7, then 3, then 8. So we're getting the correct output once again. So this code, I hope this is clear to you. And now let's move on to the next question. Hi everyone, so now we're going to discuss a very interesting problem. So the problem says that the title of this problem is distance of a nearest cell having 1 in binary matrix. So when we say binary matrix, so binary matrix is a matrix that is containing only 0 or 1 as its elements. So the question statement is something like, let me read out the question for you. So it says that given a binary grid means you are given a matrix, find the distance of the nearest one in the grid for each cell. So for each cell, you'll have to find the distance of the nearest one. The distance is calculated as I1 minus I2, the index of that particular point, difference of the index of that particular point from the position at which 1 is present, where I and J are the row numbers and column numbers of the current cell, and I2 and J2 are the row and column number of the nearest cell having the value. So what I mean to say by this particular statement is, let's say you are given an input. Your input is something like, you have an input like 0, 1, 1, and 0. Again, you have 1, 1, 0, 0, 0, 0, 1, and 1. And you're supposed to get an output of this particular form. So the output goes something like 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0. So this is the expected output out of us, and this is the given input. So how we reach from this to this is, let's say we take this element which is present at 0, 0 location. So from this 0, 0 location, what we can see is the nearest cell which is having 1. So the nearest one to this is at what particular distance? So it is at a distance of 1. So we'll replace this by 1, right? So now from this one, what is the nearest one? So this one is already at its own position. So the distance from this one to one is 0 only. So we'll update this to 0. Again, this is 1. So we'll update it to 0. From this 0, if we'll go to this direction, we'll find the nearest one is at a distance of 1. So we'll update it as 1. We'll check for this. 1 is already at its position, we'll mark 0. 1 is already at its position, we'll mark 0. For this particular 0, we can either go to this side or go to this side or go to this side, and we'll get 1 as the output. For this 0, we'll see the distance of this one, we'll get 1 as the output. For this 0, we'll see the distance of this one, we'll get 1 as the output. For this 0 also, we'll see this one, we'll get 1 as the output. For this 1, it's already there, so we'll mark it as 0. 1 is already at its position, so we'll mark it at 0. So this is how this particular question is there. Let me take one more example so that it becomes a little more clearer to you. Let's say you have this particular grid 101, 110, and 100. So now if I want to have an output matrix, so how will that look like? So for this one is at its own location, so we'll have 0 as the output. For this 0, like this one is at first one distance, this one is at one distance, this one is at one distance. So output will be 1. For this one, it will again be 0. For this one, it will again be 0. For this one, it will again be 0. For this 0, it will be 1. Like 1 is at the nearest distance. If you update as 1, for this one, it will be again 0. For this 0, either it can be this one or it can be this one. Both are at the distance of 1. So we'll update it as 1. For this 0, either it can be this one, it is taking 2 steps. So the distance is 2 in this case. Or it can be this 0 and this one. Again, it is 2. So the minimum distance nearest cell that is having 1 is at a distance 2. So we'll update this with 2. So basically, this is something that the question says, and how we are going to solve this using Q is really something very, very interesting, right? So what we'll do is, rather than just thinking upon from a point of view that we'll start from zeros, let me pick up all the ones that are given in that particular question. Let's take one more example. So let's say in this example, you are given a grid of this form: 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0. So for this particular grid, let's say we'll take all the ones that are present in the grid and we'll calculate the minimum distance which is present for a particular 0. Let's say for this particular one, if I want to reach this 0, so I can reach it in 2 steps. Also from this one, if I'm reaching out to all the zeros, I can reach it by 4 steps. So from 2 and 4, the number which is coming out to be minimum, I'll put it at this place. So this place will contain 2, right? So this is something like, this is the intuition that we are going to use behind solving this particular problem. So you can think of on a similar basis, on a similar approach on how we'll solve this particular problem. Let me just take one more example and see how we are making the use of our queues, right? So the question says something like, you are given this example, let's say 101, we have 110 and 100. So the first thing is, you'll have to maintain a queue. So this queue will be holding the indexes of all ones initially, right? So it will be holding the indexes of all the ones initially. So this one, like let's say this is a queue, and it is having the first, like this index is 0 comma 0, this is 0 comma 1, this is 0 comma 2, this is 1 comma 0, 1 comma 1, 1 comma 2, this is 2 comma 0, 2 comma 1, and this is 2 comma 2. So all the 1 indexes, like I'll put 0 comma 0 into my queue, I'll put 0 comma 2 into my queue, I'll put 1 comma 0 into my queue, again I'll put 1 comma 1 into my queue, we'll put 2 comma 0 into my queue, and I am done. So now for each of these ones, what I'll do is I'll make them 0 already. Like I'll make one answer grid. This is my answer grid, and inside this answer grid, all these positions where 1 is present, so they will be marked as 0. So we'll have 0 here, 0 here, 0 here, 0 here, 0 here, right? And rest other places I'll mark them as by int max. So rest other places will be marked by int max. This will also be marked by int max. This will also be marked by int max. This will also be marked by int max. So now what I'm supposed to do is I'll go for each of the location that is present in the queue. That is the initial position of all the ones. So for this particular position in the queue, I will see, like I'll go on to 0 comma 0 position, like this is the first position that I'm looking forward to, and I will see, I'll try to explore then all the nearest possible positions. So from this 0, if I will be moving to this position, like that is not 0, any non-zero position that I'm moving into, so I will check and see that it is at a distance, like we'll add one distance of one if we move from this to this. So we'll see if this int max, like the number that is present at this particular location, is this smaller or is this greater than this new distance. So we'll compare this one with int max. So as I can see, this int max is greater than this one. So as it is minimum, so we'll replace this int max by one, right? As soon as this is done, what I will do is I'll remove this 0 comma 0 from my queue and I'll put the index of the new updated element in the queue. So this new index is 0 comma 1. I'll put it in the queue, right? Now we'll move on to the second index from the queue. It is 0 comma 2. Like this is 0 comma 2. From this 0 comma 2, like this is the position. I can move to this location also. I can move to this location also. Moving here, I will add the distance of 1. So I'll compare this one with already present one. Now 1, is it greater less than 1? No, this condition is false. We'll not do anything for this particular case. We'll check for this thing. Again, it is adding 1. So 1 is lesser than int max. So what I'll do is, again, I'll replace this int max with 1 and I'll add the index of this to my queue. So the index is 1 comma 2. I'll add 1 comma 2 to my queue and I'll remove 0 comma 2. Now I'll check for 1 comma 0. When I'm checking for 1 comma 0, like this is the position, I'll go to the nearest non-zero positions. So the nearest non-zero position is like this is also 0, this is also 0, this is also 0. So I'll not do anything, I'll simply remove it from the queue. Now I'll again check for 1 comma 1. For this particular position, I can go to this non-zero location, I can go to this non-zero location. For going to this non-zero location, I'm adding 1. So if I'm adding 1, I'll compare with the already present one. Since 1 is less than 1, this statement is not true. I'll not do anything for this case. For this particular case, what I'll do is I'll check if, like again I'm adding a distance of 1. I'll check if 1 is less than int max. Yes, 1 is less than int max, so I'll update this with 1. I'll remove this index and I'll add this particular index in my queue. This is 2 comma 1. Right, I hope the things are getting pretty clearer by what I'm trying to say. Then next index is 2 comma 0, so this is 2 comma 0. I'll go and check upwards. No, I'll go and check sideways. I'm again adding 1, but 1 is already present, so we'll compare 1 and 1. It is not lesser than 1, so we'll not do anything. We'll simply remove 2 comma 0. Then comes 1 comma 0 comma 1. So we'll go on to 0 comma 1, like this is the location we'll go on to, and we'll see if like what is the nearest non-zero number. Like if I move from this one to nearest non-zero, like this is also 0, this is also 0, this is also 0, so I'll not do anything. I'll simply remove this from my index. Now I'm going to 1 comma 2. So from this 1 comma 2, I'll see which is the nearest non-zero number. The nearest non-zero number is like this is the nearest non-zero number, and going from this to this number, I'll add 1. So 1 plus 1, I will see 2. So 2 I'll compare with this int max. So 2 is definitely less than this int max. So I'm supposed to replace this int max by 2 and add the index 2 comma 2 in this queue and remove 1 comma 2 from here. Then 2 comma 1, I'll compare this 2 comma 1 from here also. If I compare this 1 and add 1, so it will again be 2. 2 less than 2, which is false. So I don't need to do anything. I'll simply remove 2 comma 1 from my queue. Now 2 comma 2, I'm already present at 2 comma 2, and which is the nearest non-zero number, like 1 and 1. So going there, like from 2, if I go to there, there will be the number 3, but 3 is greater than 1, so I'll not replace them. I'll replace it with I'll not do anything. Again, I'll remove 2 comma 2, and in this way we will be getting the answer of the form 0 1 0 0 0 1 0 1 2, and that is something that we require as the output. This might look a little trickier. The question is a little tricky, but you need to understand what exactly we are going to do. I'll just try to reiterate through what all things we have done. This is basically the classic example of BFS. This is known as breadth first search, and this can be implemented using arrays, oh sorry, queues. So we have implement, we'll try to see how the code works, but before that, just I'll take you through the code on how the code part works. So input, we are given something like this, and we are expected to have an output of this. So how this output is calculated, we'll go and check for each of the non one digits, like we'll go for all the zeros in this binary matrix, and we'll see which is the nearest one and we'll calculate the distance of that nearest one and put it at that place. For this particular 0, the nearest one is present at first location, so I'll put the distance as 1. For this particular, like for all the ones, they're already at their own position, so the nearest distance from 1 to 1 is 0. For all the ones, we'll have 0 as the output. For this particular one, again it is 0. For this 0, this is the nearest one, so I'll get the output as 1. For this 0, uh, I'll again, like, this is done. For this one, it's again 0. For this one, it's again 0. For this 0, I can take it from this also, for this also, from this also. Any one answer is going to be 1. For this 0, I will take from this, it is 1. I'll take for this 0, answer is coming out to be 1. From this, like, 1 is the minimum distance between them. For this 0, again 1 is the minimum distance. For this one, it is 0. For this one, it is 0, and we'll get the answer. So this is the approach. This is the question that we had. So what we are trying to do is, the approach goes something like this. We'll maintain a queue and we'll put the indexes of all the ones in that queue for the first time, right? Then all the zeros that are present. So we'll put int max in place of those zeros, and what we are supposed to do after that is, we'll go and check for each one. From this particular one, I'll traverse all the non-zero locations and see what is the minimum distance that this one can be from all the different locations. So this one can go to this place, this place, this place, this place. It can go to north, it can go to south, it can go to east, it can go to east, it can go to west. So for all the 4 directions, I'll be calculating the distances and I'll update the distance with, on comparing whether it is minimum or not. So I'm comparing like from this 0 position. If I want to move to this, I can add a distance of 1 and I'll compare it with the int max. It is 1 is always less than int max, so I'll update this with 1. Similarly, I'll go from each and every location and we'll have the final output metric something similar to this, right? I hope this approach is clear. Just try and dry run this once on your own, so you will get a better idea on what I'm trying to say. Now we'll move up on to the code part and you will have a little more clarity on what we have discussed in now. So this was the question that we were discussing. It tells us about the distance of the nearest cell having 1. We are given a binary grid, like we took the same example of 0, 1, 1, 0, 1, 1, 0, 0, and 0, 0, 1, 1. The output comes out to be 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0. I've explained you the entire process, how we did, and now let's have a little bit of consideration of how this code is going to work. Let me just show you the code part. So what we are given in this particular question is, we are given a vector of vector. We have to return a vector of vector and we are given the entire grid. So that grid is basically the input grid that is given. Next, I'll create two variables n and m, through which we'll be able to iterate over the entire, we'll find out the size of the number of rows and number of columns of that particular grid. Next, I'll create my own answer vector and I'll initialize initially with all the places with int max, as I've already told you. Then I'll create a queue of the type pair int because it is going to store the index value of that particular grid. All the indexes we are going to store in this particular queue. So that's why it is going to be of the type pair of int and int. Next, this is the for loop that we are running basically to, like, we'll go and iterate over the entire grid and check at which particular position we have 1. For the positions for which we have 1, we'll update them to 0 because we've already seen, and we'll push those indexes into our queue. So now we have all the indexes with which were initially 1 in our queue, and we have made them to 0. That's one thing. Now we are running a while loop until and unless this queue that we have made of indexes is empty. We'll find out and we'll check for each and every position. For each and every position, we'll check out the nearest distance from a non-zero position. So we'll see, we'll take two numbers I and j. I stores the front element, the first element of the queue's front, and the second, basically the index first value. Let's say we have 0, 0 or 0, 1. So 0, 1, in 0, 1, 0 will be stored in I and 1 will be stored in j. Next, we'll check for a particular position in that matrix and we'll see if that position is greater than equal to 0. That this is basically to check if it is not out of bounds. It should not be out of bounds, so we are checking this. It should be greater than equal to 0 or it should be less than equal to n, or lesser than equal to n, so just number of rows and number of columns. And we'll check for each and every location, like we'll check for the top position, the bottom position, the left position, and the right position, basically that I've talked about as north, south, east, and west. we'll compare both of them and we'll see if it is less than the initial present value. If it is less than the initial present value, so we'll simply update that position with that number and we'll put the index of that in our queue. So we'll check for each and everything. We'll check for south, east, north, and west for all these cases, like different cases I have made, like for all the iterations I minus 1 comma j, I and j minus 1, I plus 1 and j, and I and j plus 1. For all of them, we'll push the indexes, corresponding indexes, and after that we'll pop, like if the entire operation is done, we'll pop the index that we have operated upon. At the end, we are going to return this answer. This answer is of the form vector of factor int, and we are done. So I hope this code should be clear. You should be able to write it on your own. There might be a little difficulty while going through it for the very first time, but trust me, once you dry run it on your paper and pen, you'll definitely be able to solve this particular problem. Now let's move on to another problem, and this is something like, this is a very important interview problem with respect to queues. So make sure you don't miss on this problem, and let's move on to another problem. So moving on to the next problem. The next problem states, the name of the next problem is rotting oranges. It's one of the very famous problem and it's one of the favorites in an Amazon interview. Like, I've heard a lot of interview experiences in which this problem has been asked. So listen to this interview problem carefully and see how this goes. So what you are given in this is, you are again given an m cross n grid where each cell can have one of the three values. There can be three values in the grid. It can be 0, 1, or 2. So 0 represents that the cell is empty. We don't have anything in that cell. 1 represents that there is a fresh orange present at that particular place in that grid. And 2 represents that there is a rotten orange that is present at a particular location in a grid. So what happens is, every minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. Matlab, what they are trying to say is, at every minute, like any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. Let's say this is a rotten orange and this is a fresh orange. Like, this is a grid. So if such is the case, so in 1 minute, this rotten orange will again rot this fresh orange. So it will also become rotten. So 1 minute will be passed. This is what they're trying to say. Return, what we need to return is, return the minimum number of minutes that must be elapsed until no cell has a fresh orange. If this is impossible, return -1. So we'll have to tell in what minimum time can all the oranges be rotten. Also, if this is not possible, like in any case, if there is any orange left that we can't rot, so we'll have to tell them ki we'll have to return -1, and this, that means this situation is not possible. So what exactly they're trying to say is, like, let's look at the first example that they have given already. So in this particular example, they are saying that we have a location, we have at minute 0. This means that the orange is rotten. That means 2 is placed here. And these are fresh oranges and these are empty cells. So after 1 minute, so this orange, this rotten orange can rot the oranges in 4 directions: upwards, downwards, leftwards, and rightwards. So upward there is nothing, so it can't rot anything. This is gone. From leftwards also there's no element that can be rotten, so it is gone. So downwards and sidewards. So for downwards, like in the first minute, when it will go in the first minute, this orange will be rotten by the first rotten orange, and this orange which is present at the side will be rotten in the first minute. After 1 minute is done, so we'll move on to the another minute. Now this orange has the capability to rot all the oranges present in the 4 directions. So upward there is nothing, rightward it's already rotten, so it can rot the one which is present at the right and the one which is present at the down location. So in the second minute, this will rot this particular orange and this particular orange. Also, there's a possibility that this rotten orange can move in all the 4 directions. Let's see what will happen. Upward, it's already rotten, nothing to go. Leftwards, there's no place, it is out of bounds, nothing to do. Rightward, it can be rotten by either this or this. If it is rotten by this, then there's no use of this. Downwards, there's no orange, so it can't be. So we will move on to the next. So in the second minute, we have 5 oranges that have been rotten. Now in the next minute, what will happen is, this orange has the capability to rot this particular orange, this orange has the capability to rot all the oranges in the four directions. This has also the capability to rot the oranges in the four directions. From here, there's no possibility, no possibility. This is already rotten and there's no possibility. Now for this orange, it can rot this orange, like this orange can be rotten in the next step. There is no possibility, it's already rotten, already rotten. So in the next minute, in the third minute, this orange becomes rotten and we move ahead. Now in the fourth minute, only one orange is left. This can be rotten by this particular orange in the fourth minute. This is rotten in the fourth minute. And you can see at minute 4, we have all the oranges that are rotten. So we can say the minimum number of minutes that must be elapsed until no cell has a fresh orange. Like in this case, there's no cell that is having a fresh orange. So we can say that the answer of this case would be 4, right? So this is what the question is going to say, and we are trying to, like, we will be given an input grid of the similar kind and we need to solve this particular problem. Let's look at the second test case that they have given. So the second test case is something like they want to uh, have something like 2 1 1 0 1 1 and 1 0 1. So here 2 suggests that it is a rotten orange, 1 suggests that it is a fresh orange, and 0 suggests that the place is empty. So in the first minute, what will happen is this 2 will rot the orange present at this particular location. Upward there is no possibility, sideward there is no possibility, downward there is no possibility. So this will become 2 in the first minute, matlab 1 minute passed. So it will be 2, 2, 1, 1, 1, 0, 1, 0, 1. So again, in the second minute, this 2 has the capability to rot this orange and this orange. It will become 2, 2, 2, 2, 0, 1, 1, 0, 1 in the second minute. Now for third minute, now this orange has the capability to rot this orange, and this has the capability to rot this, and this. But there's no need, uh, again no need, and this can be either be rotten by this or this. In the third minute, we'll have something like 2, 2, 2, 0, 2, 2, 0, 1, 1. Now in the fourth minute, what can happen is this can become something like 2, 2, 2, 0, 2, 2. Now this orange can rot this orange. It will become 2. It is 0 and it is 1. So now there's no possibility that this fresh orange can be rotten. Like no, like even if let's say 10 minutes are passed, 15 minutes, 20 minutes are passed, this orange can't be rotten. At 4 minutes, like even after passing 4 minutes, this orange still remains the same. So there's no possibility that we can have this condition. So we'll simply return the output as -1. This is the second condition that they have given, right? So I hope the question is clear. Now let's move on to our uh, board so that we can understand it a little more better, right? On how we'll be solving this particular problem. So let's say, so now you have understood the question, right? So let me take a grid, a very simple grid, so that the things become easier for you. So we have this particular grid, right? Let's say initially this is the, like, oranges are present at this, and this location, right? We can number them as 0, 1, 2, 3, 0, 1, 2, and 3. So initially we are given this orange and this orange is rotten. So the orange which is present at location 0, comma 0 and which is present at location 0, comma 3 are rotten. So how we'll be solving this particular problem? We'll be using the concept of BFS once again. So in the concept of BFS, we use Q as a data structure. So here comes the application of Q once again, and it's a very, very important problem. You definitely need to check upon how we are solving this particular problem. But before starting with the problem, let's try and maintain a variable count. This count variable will have all the non-empty cells, the total number of non-empty cells in my grid. So total number of non-empty cells is 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 number of non-empty cells in my grid. So in every question of BFS, I need to maintain a queue. So I'll be maintaining this particular queue, right? So this queue will, like, firstly will start this queue, like, during BFS it starts with something, like queue should have something. So what we'll put is we'll put the locations, we'll put the indexes of the oranges which are rotten. So here 0, comma 0 is rotten and 0, comma 3 is rotten. So we'll put 0, comma 0 and we'll put 0, comma 3 in our queue, which is already there. So now we'll closely look at 0, comma 0 and 0, comma 3. So 0, comma 0 is here, 0, comma 3 is here. What can happen is, like, after the passing of 1 minute, this rotten orange can rot the oranges which are present in all of its four directions. That is, it can rot the orange present at the top, it can rot the orange present at the right, orange present at the bottom, orange present at the side. This 0, comma 3 can also rot the orange present at the top, present at the side, present at the bottom, and present at the left. Right. So for this 0, comma 0 location, like top, there's no element, so there's no possibility, it's cancelled. From left side, there's no possibility, it's again cancelled. From right side, there's no orange that can be rotten, again there's no possibility. Downwards, now downwards, there is at that is the orange at location 1, comma 0. It can be rotten by 0, comma 0 in the first minute. Simultaneously, at the same time, for 0, comma 3, top there's nothing, left, right there is nothing, left there is no orange, and downward position, that is 1, comma 3, it can be rotten. So after the passing of first minute, this is rotten and this is rotten, right? So what I'll do is, I'll remove the indexes already present from the queue and I'll add the indexes which are rotten. So indexes which are rotten are 1, comma 0 and 1, comma 3. Now after this, what I'll do is, uh, and like these indexes can be maintained by using the iterators I, comma j. So, this can be the uh, number of rows, this can be the number of columns once we are iterating. This can be the number of rows, this can be the number of columns, right? So now after this, we'll pick up 1, comma 0 and 1, comma 3. When I say 1, comma 0, let me just erase this. Now if I have 1, comma 0 and I have 1, comma 3. So from 1, comma 0, that is this 1, comma 0, I can go to top, right, left, and bottom. Top, that's already rotten, so I don't need to do anything. Right, there's no orange. Left, it's out of bounds, and down it can be rotten. So the answer, we can rot the orange that is present at 2, comma 0 location. From 1, comma 3, similarly 1, comma 3, top there's no possibility, it's already rotten. Right, there's out of bounds. Left, there's no orange. Down, we can do. Down is 2, comma 3. So I have 2, comma 0 and 2, comma 3. So what I'll do is, I'll remove these indexes and I'll add 2, comma 0 and I'll add 2, comma 3. Right, now this is rotten, this is rotten. Now both of these are there. Now let me erase this once again. Now I have the elements 2, comma 0 in my queue and 2, comma 3 in my queue. So now if I have 2, comma 0 and 2, comma 3, again there is a possibility that this 2, comma 0 and 2, comma 3 can uh, rot the elements in all the four directions. This 2, comma 0 in the top direction, there's no possibility. In the right direction, yes, it can rot the orange present at 2, comma 1. In the down direction, there's no possibility because orange is not there. In the left direction, it is out of one. So only 2, comma 1 is there. For 2, comma 3, that is this particular orange. So this particular orange can also go in the four directions: top, down, right, and left. So when I say top, so it's already rotten, there's no need. Left, this is out of bound, there's no need. Right, left, there's no orange. And down, yes, it can be rotten, it is 3, comma 3. So now after this, we'll remove these and we'll add 2, comma 1 and 3, comma 3. So as soon as we are doing all this, like after each step, we'll see if at all the queue is empty or not. So for everything, like initially, let me take a new variable, that is minutes. It is 0. As soon as this has passed, like we remove these two elements from the queue and we add these two elements in the queue, we'll update the value of minutes to +1. Again, second case, we'll remove them. We'll again add the elements in the queue. Queue is not empty, so we'll again increase the value of minutes to 2. Again, we'll add these numbers. We'll remove them. We'll see the queue is not empty. We'll increase the number of minutes to 3. Now we are on a position that we have two more numbers in the queue. We have 3, comma 3 and we have 2, comma 1. So now 3, comma 3, this is 3, comma 3, it is rotten already. So it can rot the top, right, left, and bottom. Top, it's already rotten, no need. Right, out of bound. Down, out of bound. And left, it is empty. So this cannot rot any element, then it's done. Now 2 comma 1, 2 comma 1, it can also rot in the four directions. In the top, there's no orange. In the right, there's no orange. In the down, there's no orange. In the left, there is already rotten. So again, it can also not rot anything. So like we'll remove these elements and we are done. So what next we are going to see is we'll calculate the total number of elements that we have added in the queue. So 2 we have added here, 2 we have added here, 2 we have added here, 2 we have added here. So total number of elements that we have added in our queue is 8. So what we'll see is this minutes that will tell us the minimum time to rot all the oranges if and only if, like we'll return this minutes as answer if and only if this value of count becomes equal to this total number. Like we'll take a new variable total. So once this count becomes equal to total, that is 8 is equal to 8. Like in this particular case we have all the oranges which are rotten. There's no case in which any orange is left fresh. So what we'll do is we'll return this value of minutes. If this would not have been the case, like if count would not have been equal to the total minutes, then what we would have done, we would have returned -1 simply, right? So I hope this question is clear, this approach is clear. You should go through it once again. Might seem a little typical to you, but once you try it on your own on a piece of paper, it will be a little more clear, right? So let's move on to the code part and see how we'll be coding this particular question, right? So we are given orange is rotting. We are given a vector of vector int grid, like that is we are given a matrix. So first thing that we're going to check in this grid is whether this grid is empty or not. If at all this grid is empty, so we'll simply return 0. That is there's no time. That is there are 0 minutes that will be taking to rot all the oranges. Next we'll maintain two variables m and n. Along with that, we'll maintain the variables minutes. This will tell us how many minutes are elapsed for each of the rotting stage. We'll maintain a variable total that will help us to know how many total number of indexes or total number of oranges we are rotting, and we are adding it into the queue. This is the value of count that initially tells us total number of non-empty cells in our queue that we're adding. So I'll create a queue of the type pair int. Why pair int? Because it is showing the indexes, that is the value of I and j uh, for all the indexes of our grid. And we'll name this queue as output queue. We'll run two loops for from I to m, from j to n, like from and the entire grid will traverse this entire grid. We'll check for if at all the value of grid at any point is non-zero. That means we are checking the total number of elements, that is the total number of elements which are present in the queue, that is non-empty elements which are present in our grid. So we'll increase the value of total. So in our example we have already calculated the total number of non-zero, like non-empty cells in the grid, so it comes out to be 8. So we'll check for the same, and if at any point we'll check if the value of grid is equal to 2. That means in the first stage what we did is we initially made all the rotten oranges to be in the queue. So if we'll check if the grid value is equal to 2, we'll push I comma j in the grid and in the queue, so that we have these two elements from where we can start our BFS. Next is this is dx and dy. These are the four directions. What do these four directions suggest? I'll try to explain it with the help of this chart. So like let's say this is in a coordinate system also, if we want to move in this particular direction, so we have 0 comma 1. Any point in this particular line will be of the form 0 comma 1. Any point of the form 1 comma 0 will be of in on this particular line. Any point of the form 0 comma -1 would be of the form this, and we'll have -1 comma 0, right? So we'll see like this will help us to move in all the four directions, that is north, south, west, east and west, whenever we are writing our code. So we'll see, like you will understand it a little later when we'll put them in our code. So what we'll do is we'll check upon until and unless our queue is empty. We'll make a condition for our queue until and unless our queue is empty. The first thing that we're going to see is we are getting the value of k, that is the size of the queue. Why we are maintaining the size of the queue? Because at the end we'll have to check whether our count is equal to total or not. If this doesn't happen, we'll have to return -1. So this count variable tells the total number of elements that are added in the queue, the total number of oranges we have rotten. So it maintains this particular count. So until and unless the size of queue becomes 0, what we'll do is we'll create a variable x, we'll create a variable y. X will store the outputs front first. Outputs like queues like I and jth index, basically. X and y are I and jth index of the elements. And for each I and jth index, what will remove that particular element from the queue. And for each value of I and j, what we'll do is we'll add dx of I and dy of y. That means what we are going to do is like we have seen here. Yes. So we have seen here. So for each value of element that we have added in our queue, 0, comma 0, we are going to check in all the four directions. So for checking in this particular direction, what I need to do is I need to add in the positive right. I need to subtract in the negative down. I need to subtract in the negative left. I need to add in the positive y. So this is something that we're going to do, and this has been implemented using uh, dx and dy, because these are the values. Like we'll add one at, we'll say x plus dx of I, that is dx of 0, the x, and we'll check upon x and y minus y plus 1. So for x and y plus 1, what will be the case? So similar to that, like we'll check for nx, ny, nx, like will these are basically the boundary conditions that the value of nx should not go out of the bounds, and we'll check if at all our grid is not empty. So if it is not empty, then we'll simply continue. If it is well, if it is non-empty, if it is not a fresh orange, then we'll continue. If it, or else we'll make it equal to 2. That means we'll rot that particular orange, and once we have rotten that particular orange, we'll put it into our queue. Finally, we'll push the indexes of them in our queue, and at the end we'll check if at all our queue is not empty. We'll increase the value of minutes, that is for every element, for every rotten like after checking if our queue is not empty, we'll increase the value of minutes like we were increasing in the r in our explanation. So the value of minutes will give us the total number of minimum number of time that is required to rot all the oranges. If at like at the last we'll make a check. If our total equals to count, then we'll return minutes. Else what we'll do is we'll return -1. So this is basically the code. I hope this will be a little more clearer to you. I have given you an idea. Now it's your turn to just go through the code, just go through the question once again and try solving it on your own in any of the preferred language, be it C++ or Java, so that you can solve this problem during your interviews, right? I hope this solution is clear to you, and make sure you dry run it once on your own so that you can get it in a better way. Thank you so much. Let's move on to the next question. So we're going to see yet another question, and it's also a very, very important question. People do miss upon this question. It will be an easy question, but still you need to see upon how we'll be using queues to solve this particular problem. So the question goes something like this. You are given a stream of numbers, you can say you are given non-repeating characters. You have to find the first non-repeating character in a stream using queues. So this is the question that is given to you. So what does this question actually means is, like, you are given a stream of numbers. When I say stream of numbers, stream of characters, that means characters are coming one by one. Like initially in my string, I have A. Let's say A is the first character that is coming up. So the answer corresponding to this A will be A only. Like A is the only element in my string and A is non-repeating, so the answer will be A only. Now I have B added to my string. Like B is the second element which is coming in the string. But still, which will be the first non-repeating character in my string? A. Again, A is not repeating till now, and A is the first element. So the output corresponding to this will also be A only. Now let's say I have the third character, that is A again. Now, as soon as we add another A, we'll see that A is repeated. So now A goes from the picture. Now, which is the first non-repeating character in the stream? So the first non-repeating character in the stream this time will be B. Now, in the next iteration, I'll have A, B, A, C. Let's say I have this particular thing. So again, for this particular case, which is the first non-repeating character? Still B remains the first non-repeating character in the string. So I'll have B as the output again. Let's say I have another C as the output. So the answer corresponding to this will again be B. Let's say I have one more C coming up. The answer corresponding to this is also going to be B. So this is something that I'm looking forward to as an output. So my output should look something like A, B, 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 B. So this, like, let's take one more example. Let's say you have A, B, B, A, B, C, C. So this is the string that you are given. Let's say all the characters are coming one by one. Initially, A was the first element that came. So answer corresponding to A will be A. Next, at this particular point, also the first non-repeating character remains A, so the answer will be A. At this particular point, uh, again the answer still remains A because A is not repeated. At this particular point, now at this particular point, you see, do we have any character which is repeating, which is non-repeating? Now we have two characters A and B, and both are repeating. So at this particular point, we will mark hash, right? Now again B, at this particular point also I have no element which is non-repeating, so I'll mark hash again. At this particular point, C, which is the first non-repeating character, C is the first non-repeating character. At this particular point, all the characters have been repeated once or twice, so I'll again mark hash. So the answer corresponding to this is this. So where we are going to mark this hash, where we don't have any non-repeating character prior to that in the stream. So this is something that the question says, like, and how will we trying to solve this particular problem is, let's see how we'll be solving this particular problem. Yeah. So for this, let's say I have, we'll take the example of this string only, A, B, A, C, C, C. And for this, I'll maintain a frequency array. This frequency array will mark the frequencies of the characters from A, B, C, D till Z. Small letters, small alphabets, small English alphabets. And I'll maintain a queue, right? And I will have one output string that will contain the output answer that I want. So we'll be having three things. So as soon as a character is coming up in the array, in the stream, so let's say firstly A comes up. So what I'll do is I'll go in my frequency array and I'll increase the frequency of A to 1. Now I'll put this, like my queue is empty. I don't have anything. I don't need to compare or do anything. So I'll put this A in my queue. And also the first non-repeating character at this particular point of time is also A. Now the second number comes up. It is B. Now I'll increase the frequency of B here. I'll add B to my queue. And in the output array, what I will do is I will pick up the front element of the queue, right? The element which is present at the front index of the queue, that will be going to the output every time because that has not been repeated yet, right? Now the third case, now A comes up. Now again, as soon as A comes up, what happens? The frequency of A here becomes 2 now. As soon as the frequency of A becomes 2, so what I'll do is if that element is present in my queue, I'll remove that element from the queue, right? Now the element correspond, like, which is the front element in my queue that is present, the front element in the queue that is present is B, so I'll output B, right? Now again I have C, so corresponding to C, I'll mark the frequency of C as 1. I'll put this C in my queue. Corresponding to C again, what I'll see the front element of the queue, the front element of the queue is still B, I'll move B. Again I'll check out C. C is again coming. We'll increase the frequency of C here. As soon as the frequency of C is increased here, I'll remove C from my queue. Again in the output, what I'll see the front of the queue. It is again B. I'll put B. For the next C, I'll again see the frequency here becomes 3. Like, it is not 1. So again, this C is not there in my queue. I'll not do anything. Corresponding to this, I'll check my queue, which is the element which is present at the front of the queue. It is B, and I'm done. So this particular output is what I want. And see, our problem has been solved very quickly by this particular methodology using a queue, because we can push We can push from the rear end and pop from the front end. Here in this question, the requirement was that we need to pop from the front. So basically, we can solve this problem using this particular methodology. Now, let's see how the code of this particular question will work. So for the code of this particular function, for the code of this particular question, I will need to create a queue. I'll create a queue. I'll create a frequency array, and I'll create an output string. So what I will be doing is, as soon as a number comes up, as soon as a character comes up in a string, I will add that to my queue. I'll increase its frequency and I'll see the front of the queue. What will be the front of the queue, and corresponding to that front, I'll add it in my queue. Whether it is to be added in my queue or not, I'll take a decision based upon that. Right? Also, one thing I'll check is until and unless this queue size is empty, like if there is nothing in my queue at that particular point of time, what I will do is I'll see like there's no element which is non-repeating, first non-repeating element. So we'll correspondingly put a hash in the output, right? For that particular case, let's see, it will be more clear once you see the code part. So let's move on to the code part and see how it goes. So let's quickly see this code part. Basically, we have this particular question. We are given a first non-repeating character in a string, and corresponding to that, we'll have to perform the things that we have discussed already. So the first thing that I've told you that we'll be doing in this particular question is we'll be making a queue of the type character, because we are adding characters there. Let me name it as queue. I'll maintain a frequency array, frequency of 26, because there are 26 alphabets in English, 26 letters in English alphabet. So initially this frequency array is 0. I'll maintain a string answer that will initially be empty. Now I'll run a loop. We are given a string a, and corresponding to this, what I'll do is I'll push that element in my queue as soon as it comes. So a of I'll push it in my queue. Next thing is I'll increase the frequency of that particular element corresponding to that. So the frequency goes something like a of I minus 97. Why 97? Because the sky value of a is, well, the first alphabet is 97, so we'll increase it. Now I'll run a while loop and check until and unless the size of my queue is not equal to 0, and also the frequency of q dot front, the the element which is present at the front of my queue, if its frequency is not equal to 1, it is greater than 1, equal to 1. So what I'll do is I'll pop that element from the queue. That was something that we were doing, and after that we will check if the size of the queue is not equal to 0, there is something in my queue, then we'll in answer is the string that we'll be getting as the output. In the answer string, we'll push back the front of the queue, right? I hope these steps would be very very clear to you, because you have already seen what the solution is like. Else what we'll be doing is, else we will simply push back hash, right? When our queue becomes empty, we'll simply push back hash, and let's just try to return this, return answer string, and I hope this should work. Okay, let me just compile and run. So it's a medium level question that is marked upon geeks for geeks. Is it something that we are going wrong with? Q character Q, we are initializing a frequency array, string height of length I plus plus. We are pushing it in the Q frequency of a of I minus 97 plus plus reading, while my Q size is not equal to 0, and my frequency of front, this should be frequency of front minus 97, because again we are checking the sky value is not equal to 1, then q dot pop, q dot size equal to, okay. So I think it should work now. Let me just try it once again. So this, like, we didn't do the subtraction of 97 because we are comparing the sky values, we are storing it in the frequency array. Now we have this particular output corresponding to this. Yes, our output should be this, because corresponding to A, the output should be A. Now A is, once again, now I don't have any element which is non-repeating, so I'll put hash B, so I'll put the B as the answer, and C, we have B, which will be present at the front of a queue. Let me try to submit and see if it goes well. So yes, we have successfully solved this problem, and I hope the solution is clear to you. It's also a trivial problem, but yet it is considered in the medium level, and it is asked by various companies and has been solved using queues. Now let's move on to another question.
Hi everyone, discussing another problem. The another problem that we are going to discuss is finding the count of unvisited indices in an infinite array. The question goes something like finding the count of unvisited indices in an infinite array. So question goes something like, given an array of infinite length, you are given an array whose length is infinite and two integers m and n which are co-prime. You need to find the number of positions that cannot be visited starting from the first position when in a single move from ARR of I you can go to ARR of I plus m and ARR of I plus n. Also, you are given a note that the result is finite. So now you have seen the question. So what it exactly says is, it says that you are given two integers m and n and an infinite array, right? Infinite array. What you are given, the properties of m and n is that m and n both are co-prime. When a number is said to be co-prime, a number is said to be co-prime if it doesn't have any other factor than 1. So they both have 1 as a common factor. Let's say we have 5 and 7. So for 5 and 7 the common factor is 1. So 5 and 7 are co-prime. Let's say 3 and 5. So for 3 and 5 also there's no other common factor than 1. So 3 and 5 are co-prime. So m and n are co-prime numbers, and you are given that you need to find out the number of positions that can't be visited starting from the first position when in a single move you can move. So this is an infinite array that you are given, and you have to tell me the number of positions that cannot be visited using these indexes. Matlab, if I move from array of like from the 0th position, I can move m steps, or I can move n steps, or I can move m plus n steps. So which all indexes will be there in an infinite array which will not be visited? But like, see, if it is an infinite array, so then you might be thinking ki this will to go on in an infinite loop, like we'll be having infinite numbers which will not be visited, or we'll need to run through the entire loop. But no, there is a property, special mathematical property, like if you are good at maths, not good at math, this is something that you need to know for solving this particular problem. Let's say I have a given input. Let me just explain you with the input and output. Let's say m is 2 and n is 5. The output you will get in this case is 2. Why 2? So like from the index 0, the indices that can be visited are, like it can be 0 plus 2, that is 2. It can be 0 plus 2 plus 2. It can be 4. It can be 0 plus 5. Can be 5. 0 plus 2 plus 2 plus 2, we can visit 6 also. Can we visit 7? Yes, we can visit 7. 2 plus 5 is equal to 7. Can we visit 8? Yes, 0 plus 2 plus 2 plus 2 is equal to 8. Can we visit 9? Yes, we can visit 9. 0 plus 2 plus 2 plus 5 is equal to 9. 0 plus 5 plus 5 is equal to 10. So we have done it till here, and we have seen that 1 was not there and 3 was not there. Like apart from that, like you are given this 1 and 3 are not visited, hence the answer comes out to be 2. But from an infinite series, we have just chosen these 10. Why? On what basis? So there comes a property of Frobenius number. So what does this property of Frobenius number tells us? So you need to know this Frobenius property. Let me just read out the exact statement of Frobenius number. So Frobenius number, it will tell you the largest index that can't be obtained using any combination of m or n. It gives the largest number that can't be visited using any combination of m or n, where m and n are co-prime. So there is a formula. I will not go into the depth of formula. So it will give us the largest number in this form. So you can go and search for Frobenius number if you want a detailed explanation proof for this particular property. So you just need to have this result in your mind for solving this particular problem. So Frobenius number, it gives us the largest number that can't be visited using any combination of m or n. Right, so x is equal to m star n, m multiplied by n minus m minus n will give us the largest number which cannot be visiting using the combination. So this makes the problem a finite one, right? So we don't have to traverse over the infinite loop, but we have to look forward till this particular number. After this we don't need to check anything, right? So for our case, like if m is 2, n is 5, so the value of x will be 2 into 5 minus 2 minus 5. It will become 10 minus 2 minus 5. It will be 3. Right, so the largest number that can't be visited using any combination of m or n is 3. So have you got this point? The 3 is the largest number. Also we have seen now 1 and 3 were the only numbers. So 3 is the largest number that can't be visited using any combination of m or n. So using this similar approach, we are going to solve this particular problem. We'll need queues, as we are discussing queues at some point of time. We'll need queues to solve this particular problem. We'll see how we'll solve this. Now you know you have the largest number. What we can do is, if we know that there's a largest number x which can't be visited, so x minus m will also not be visited and x minus n will also not be visited. So we'll push these numbers in our queue and we'll maintain a count, and at the end we'll return this particular value of count so that we can get to our answer. Let me just go through the question once again so that you can understand it in a better way. So what we are given in this question is, we are given two numbers m and n. Both of them are co-prime. Using these two numbers m and n, we need to start traversing our array from traversing our infinite array from 0th index. We can increase by m steps or we can increase by n steps, and we need to find out the places that we cannot visit, the total number of places that cannot be visited in that infinite array. So what we have come up with the solution, we have something known as Frobenius number. So Frobenius number tells us the largest number that can't be visited using any combination of m or n. So using Frobenius number, let me calculate the value of x that will give us the largest number that can't be visited using any combination of m or n. So once we have that largest number, we need to see, like we already know that after that there's no number that we are going to check. We need to check only till the number x. So now we have the value, we know this number. So from this x, we'll have an intuition that x minus m, if x is not visited, there's an obvious way, x minus m also won't be visited. If x minus m would have been visited, so then x would have definitely been visited by that number. So x minus m is also not visited, x minus n is also not visited. At the end, what we'll do is we'll maintain a count for all the numbers that have not been visited and we'll return this count. So let's move on to the code part and see how we'll code this particular question. So now we'll be seeing the code for this particular problem. We have the function name as count unvisited, and we are given the value of m and n. The first thing that we were doing is we were calculating the Frobenius number. Let me just name that Frobenius number as x. The value of Frobenius number is majorly m into n minus m minus n. You can look forward to the explanation of this particular formula online at by searching for what Frobenius number is. Next, what I'll do is I'll maintain a queue of integers and I'll name it as queue. The first thing that I'll do is, in this queue I'll push this value of x. Once I push this value of x in the queue, and I'll maintain a count variable, count is equal to 0. Now I'll run a while loop while my queue is not empty. Until and unless my queue is not empty, what all things I am going to do, I'll check for the current that is present in the queue. So the current element that is present in the queue, I'll mark it as, like, we can get the element from the current, and then we'll remove this particular element, queue.pop. Once I remove this particular element, then I will increase the count. Like, this is the number that can't be visited, so I have the count value as 1 now. Also, what else I have seen is, if at all my current minus m is greater than 0, if at all they are greater than 0, then what I'll do is I'll again push them, queue.push current minus m if my current minus n is greater than 0, I'll q dot push current minus n, right? So this is something that we are going to do, and at the end we'll return the value of count. It will give us the exact value of count that will help us to solve this particular problem. Return the count. So let's see what we have done. We have written this function with variables m and n. We have calculated the value of x, that is the Frobenius number. It gives us the largest index that can't be visited by using m and n. We maintained a queue of integers. We push this x in the queue, and after that we have the value of count initially equal to 0. As soon as we popped out the current element from the queue, we increase the value of count. Then we know that if the current element can't be visited, so current minus m also won't be visited, and current minus n also won't be visited, and after both these cases we'll return the value of count. We'll try to run and see how it goes. So the answer that we're getting is 2. So this is running for the test case 2 and 5. Let me just run it for one more test case, let's say 3 and 7. So for 3 and 7, what will be the answer? So for 3 and 7, the largest number that can't be visited is 7 itself. So yeah, I hope this problem is clear to you. Now let's move on to another problem. Hi everyone, so we are going to discuss one more problem in the series of problems. This one is going to be a little easier problem, as after a lot of problems we are going up with this problem. This problem says a geek prepared n questions for developers hiring challenge of Geeks for Geeks, but the hiring manager wants only one question in the contest. He asked the geek to give the best problem out of n problems. Geek thinks that all the problems are the best and he's confused to choose a single problem. So what he does is, he places all the problems side by side from 1 to n. He takes out the first problem and inserts it at the end, removes the next first problem from the set. He repeats the same process until a single problem remains. The task is to find the single last problem. So this question seems to be very easy. So the approach, that the thing that they want in this particular question is that you should be able to remove a number from the front and add it at the back, and also you should be able to remove a number from the front. So these two properties are very well being sufficed by our queue data structure, right? So we'll see how the question statement and input output statements are given. So seeing that, I can see you have something given as, like, you will be giving the number of test cases t. After that, for each number of test cases you will need to tell which is the last number that will remain, right? So let's just try writing the code for the same and see how it goes. So the first thing is, we need to input the number of test cases, int t, c in t. So t stands for number of test cases. So we'll run these until all the test cases are passed. We'll insert a number n, c in n, and after that we'll make our queue of integers. Let me name it as q. Now I'll run a for loop and I'll insert the numbers from 1 to n, right? So they haven't specified that exact number that you have to, they just told you are specifying numbers from 1 to n, like 1 2 3 4 5. Like if n's value is 5, so I'll have the numbers 1 2 3 4 5 in my queue. So let me make a queue and insert the numbers from 1 to 5. I is equal to 1, say n equal to n I plus plus. After that, what I'm going to do is, I'm going to do q dot push and I. As soon as this is done, what I'll do, I'll create a while loop for queue's size greater than 1. We'll only do if the queue size is greater than 1, because we need the queue at the size 1, right? So what I'm going to do is, I'm going to q dot push. I'm going to push the front element in the queue from the back. So what I'll be pushing, queue's front, and at the same time I'll have to remove that front element. Also, after, like, what happens, what I'm doing is, this is the element, right? So I'm removing this element, I'm adding it at the back, right? This is, I'm pushing the element at the front element is pushed at the back and then it is removed. The next step is I have to remove the second element. To remove this second element, I'll again have to write q dot pop so that it is done. Let me just erase this, right? So again, once I'll write q dot pop, and what we'll do, we'll see out for each test case. What will see out? The front element that is left in the queue, right? So I hope this code goes well and you have understood the problem carefully. It was a very trivial problem. Basically, you should be able to understand the properties of queue. That's more than sufficient. Let me compile and run. Yes, we are getting a certain output. Let's try to submit. So yes, we have successfully submitted the problem and this is also done. So now let's move on to another problem.
Hi everyone. So now we are going to see application of queue in trees. How in tree data structure we can use our queues for BFS. BFS means breadth first search. This is a very important application of queues, and like it would be very difficult to solve this problem of trees without using queues. That is without using breadth first search. So what actually happens in breadth first search is like let's say we have a particular tree. For some of you, you might, if you haven't been introduced to the topic of trees yet, I would advise you to go and check out some of the videos on trees first, then come to this problem on queues. For rest of you who are clear with the basics of tree, how to form a tree, they can have like they can understand it right now, right? Let's say we have this tree data structure and we want to print this tree in a level order fashion. So when I say level order fashion, so what I mean to say is I want to print it like first I want to print 1, then I want to print 2, 3, then I want to print 4, 5, 6, 7. So the output that I want is of this format. It should be 1, 2, 3, 4, 5, 6, 7. So this is the output that I'm looking forward from this particular question, and how queues are going to help. That's our actual main topic. We'll discuss about that, right? So we can think of ways on how we will be solving this particular problem, right? Let's say I want to print this particular question. If I was to go by initial method, so for the identification of a tree, the node that is given to us is a root node. Okay. So from root node, we can access either its left subtree or we can access its right subtree. But if we go to one of the subtrees, let's say if I'm going from root, if I start accessing roots left, okay, then it would be difficult for me to access roots right after that. After I access 1, then let's say I print 2, then after that I can't go back to root. I need to print either 4 or either print 5. That would be very cumbersome if I go by this particular method. So what helps us in this is our queue data structure. So what I will be doing actually is I will be maintaining a queue, right? This is a queue. So what happens in a queue is we add the elements from the rear end and we remove the elements from the front end. So let's say the first element that comes into the picture is the root element. So I add the root into my queue, right? So 1 is added into the queue, right? And I am also maintaining an output array or output factor, you can say, that will store my final answer. So what I will do is I'll first add the root to my queue. I'll push queue 1 to my queue. Then as soon as I'll remove this queue from this one from my queue and I'll add it to the output. Like I'll add this node's data into my output, right? As soon as I remove this from the queue, I'll add both its children in the queue. I'll push them from the back. But I'll before that I'll make a check like whether it's left or right exists or not. So I'll add 2 and 3 simultaneously, right? After this, what I'll do is I'll check for 2. I'll remove 2 from the queue and I'll add it in my output. I'll add the data of this particular node into my output. And as soon as I remove 2, I'll add both of its children in the queue. So 2's children are 4 and 5. I'll add 4 and I will add 5 in my queue. As soon as this is done, what is the next step? I'll remove 3 from my queue. I'll add the data in my output. And as soon as I remove 3, I'll add the children of 3 in my queue. I'll add 6 and 7. Right? Now, next step is I'll remove 4 from my queue. I'll add it in my output and I will check for the left and right node of 4. There's no left and right node of 4, so we'll not do anything. Like we need to make this check whether the left or the right node of that particular node exists or not. Right? So now it is also null. It is also null. So we'll not do anything. We'll simply remove this and add it to the output array. Next is I'll similarly check it for 5. Again, for 5 also it doesn't exist. I'll put it directly into the output, its data. Then I'll check for 6. It also doesn't exist. I'll add it into the output. Then for 7, it also doesn't exist. I'll add it into the output. And we are done. So in this way, basically, the tree data structure, that is queues for BFS, uh, helps us in solving this particular problem that is known as a level order traversal. And it doesn't only helps us in trees but graphs also. There's a method to traverse a graph known as BFS, that is breadth first search. In that method also we are definitely going to see the application of queues. Now let us move on to the code of this particular problem and see how we perform BFS using our queues. So what we're given in this particular question is this is the question that is present on Geeks for Geeks for level order traversal. They have given us a binary tree. They want us to find its level order traversal. Level order traversal is a breadth first search traversal of a tree. Like 1, 3, 2 is there. So first we'll input of output 1, then 3, then 2. For this also it would be 10, 20, 30, 40, and 60. 10, 20, 30, 40, and 60. So this is what they are expecting out of this particular problem. What they have given is they have given us a function signature of this particular format. So function signature looks something like this. If you can see, so we need to code upon this. So the output that they want us is a form of a vector. So we'll take our output array or the output like I told you an out array, but we can take a vector. So it will be, let's say, let's name it as vector int answer. This is something that I'll maintain. Also, I'll check if my node exists or not. Like if the node is only null, then I'll simply return this answer. Like this is an empty vector, right? Next, I'll maintain a queue of integers. Let me name it as queue. And the first thing that I will push in my queue is I'll push this node. Like this is the root. The first thing that I push in my node is push in my queue is the root. After that, I'll check for until and unless my queue is empty. While my queue is not empty, I'll make certain things. I'll take out the front. Let's say node star t is equal to queue's front. Now I've removed that topmost element or the element that I've added in the queue. Then I'll do queue dot pop, that element I've removed from the queue. The next thing that I'm going to do is in this answer vector that I'm going to actually return, I'm going to push back the data of this t, right? Now we are done with this. After this, I need to push the left and the right of this t into my queue. So for that, I'll make a check whether the left of the t exists or not, or the right of the t exists or not. Firstly, what I'll do is if t's left exists, like this statement says that if there is a possibility that t's left exists, like t's left is not equal to null, then what I'm going to do is I'm going to push t's left in my q. Else if p's right exists, then what I'm going to do? I'm going to do q dot push p's right. Okay, जी? Now after everything is done, what next thing I'm going to do is I'm going to do q dot pop. Like we can do it here also, we can do it here also. Let's do it after doing all this. Doesn't make a difference, but let's go with the flow. After this, let me return the answer vector that we have made. I hope this code should work, and let me just try to compile and run this code and see how it goes. So it's ready for evaluation. Okay, so here we have to make, rather than integer, we are adding the uh, elements in the queue which are of the type node star. So rather than making this queue of integer type, I'll have to make it for of node star type. Now I hope it should be fine. So yeah, so for the first input we are getting the output as 132. Let me see and submit if this goes all well. So the code for our level dot reversal is passed and we are done with the problem. Now let's move to another problem. Hi everyone, so there's a question by the name of IPL 2021. So this question basically we'll read the statement and then we'll find out how exactly we'll be able to use Q in this particular question. So they are saying due to the rise of COVID-19 cases in India, this year BCCI decided to organize knockout matches in IPL rather than a league. So today's the match day 2 and it's between the most loved team, Chennai Super Kings, and the most underrated team, Punjab Kings. Stephen Fleming, the head coach of CSK, analyzing the battling stats of Punjab. He has stats of runs scored by all N players in the previous season and he wants to find the maximum score for each and every contiguous sub list of size A to strategize for the game. So what exactly they want us to do is uh, just think upon this problem. We have already done this problem before, which like it's a variation of like it's the same problem that we have already done. So we just need to understand this particular statement and see what they're asking. So in this particular problem, they are given us n, that is the size of this particular the scores that we are getting, and the value of k is 3, and they have given us an array. So what exactly they want us to do is they want us to find maximum subarray sum. Sorry, maximum subarray, the element which is the we have to find the maximum element in a given subarray. So out of this particular subarray of size k, size 3, in this case the answer is 3. For next subarray the answer is 3 again. For next subarray the answer is 4. For next subarray the answer is 5, and in this way it will go on. So I hope you people know this question now. We have solved it using queues. So try submitting this problem on Geeks for Geeks. I hope you will be able to solve this particular problem.
Hi everyone, so the next question that we are going to discuss is basically the question states that you need to reverse the first k elements of a queue. So what exactly you will be given in this particular question is the input will be value of k, n, and a queue of numbers, right? So let's say the value of k is 3, the value of n is 5, and the numbers in the queue are 1, 2, 3, 4, and 5. So now for these 5 numbers, what I need to do exactly is I need to reverse the first k element. Like out of the 5 elements, the first k element, that is the first 3 elements I need to reverse. So if this is the given input, I'm looking forward to an output of this form: 3, 2, 1, 4, and 5. My output should look something like this, right? So how we can do that? and we can solve this in a time complexity of O of n and a space complexity of O of n. That is, we can use an extra space. This is given to us in the question. So the first thing that comes into my mind is like, I'll create a stack. Let's say I create a stack S of integers and I put in the first three elements of my queue. I'll dequeue the first three elements of my queue. I'll pop the first three elements of my queue and I'll push them into my stack. So 1 will go here, 2 will go here, and 3 will go here. 1 was earlier here. So 1 will be removed, 2 will be removed, 3 will be removed. Right? Now my queue will look something like this. Well, if we are planning out a circular queue, so internally, if you have understood queue, so you know now 4 and 5 are at the top positions. Now what you need to do is you need to pull out an element from stack. That is, you need to pop an element from stack and push them back to your queue. All three elements until and unless this stack is empty. So after this step, my queue will become something like this: 4, 5, 3, 2, 1, isn't it? Now last one step that I need to do is I need to pop these n minus k elements. These are n minus k elements. I need to pop them and push them in the same queue. So now if I pop 4 and 5 and I push them back, what I will get? I'll get the output as 3, 2, 1, 4 and 5. So this is exactly what we are looking forward to. This will be our output. Right? So what we did initially, like we were given the question to reverse first k elements of a queue. The input that was given to us is a value of k, the value of n, that is the size of the queue, and a queue of numbers. Let's say I'm taking an example of 3, value of k is 3, value of n is 5, and I am taking a queue. So for this queue, I need to reverse first three elements. After reversing first three elements, the output that I'm expecting is something like 3, 2, 1, 4 and 5. Now next thing that I need to do is I need to create a stack. I'll pull out, that is, I'll pop three elements, that is first k elements from my queue, and I'll push them in my stack. Next thing that I'm going to do is I'll pop these elements from the stack one by one and I will push them back into my queue. So my queue becomes something like 4, 5, 3, 2, 1. And the last step that I want to do is I'll be pulling out, that is, I'll be popping out n minus k elements from my queue and pushing them back once again. So my output becomes something like this. I hope you have understood the approach. Now let's see how to code this particular problem. So you can see the question. The question says you need to reverse the first k elements of the queue. You are given an integer k and a queue of integers. You need to reverse the order of the first k elements of the queue, leaving the other elements in the same relative order. Only you need to follow the standard operations that are allowed on queue in this particular question. That is, you can only use enqueue, dequeue, size and front for this particular question. Right? They have also given the example 5 elements, 3 is the value of k. So you need to reverse 1 to 3 as 3 to 1 and so on. So now let's see what we did in our approach. The first thing that I did in my approach was I created a stack. So let me create a stack here, stack of integers, and let me name it as S. Inside the stack, I'll iterate and I will push the top k elements of my queue. Right? I is less than k and I plus plus s dot push q ka front, right? And at the same time I'll pop that element from my queue. Now we have done the first step. We have made a stack and we have popped out the top k elements of the queue and pushed them into our stack. The next thing that I'm going to do is, while my stack is empty, until and unless my stack is empty, what I'm going to do is I'm going to push the k elements back into my queue. So that will be s dot top. Okay, then I'll be popping those elements from my stack. Now the second step is done. So what is the third step? After that, I need to remove the first n minus k elements from my queue and push them back. I'll pop the first n minus k elements and I'll push them back. So let me just see what is the size of the queue. Let's name it as n. N is equal to queue dot size. We'll use the inbuilt function of size and we'll run a for loop for int I is equal to 1 to I less than n minus k and I plus plus, right? I'll have int x is equal to queue's front and queue will pop and will push this element x into our queue again, right? After everything is done, we need to return back the value of q, and I think we are done with the question. Now let's try to compile and run and see how it goes. Okay, there is a semicolon for this particular question of the output 5 and 3. What I was supposed to get, I was supposed to get the answer as 32145, but there is something wrong with our approach, I guess. Not with our approach. Let me just see. Stack S, we have pushed out elements, queues pop while stack is not empty, q dot push s dot top, then s dot pop, int n is equal to q size, I is equal to it should be starting from 0. Rest everything is fine, I guess. Yeah, so we are getting the correct answer. Let me submit. Yeah, so we have successfully submitted this problem and I hope you have understood the code as well as the problem. Now let's move upon to another problem. So let's discuss another problem. It's a comparatively easier problem, but still you might not strike, the logic might not strike in your mind. So what we need to check in this particular problem is, you need to check if the queue elements are pairwise consecutive. To check if the queue elements are pairwise consecutive. What I mean to say by this is, let's say you are given an example input. You have numbers like 1, 2, 5, 6, 9, 10. So pairwise, like we'll be making their pairs and we'll checking the difference between them. Both of them, the difference is absolute difference between them is 1. Absolute difference between them is 1. Absolute difference between them is 1. So for this particular question, I want to return the value true as my output, right? Let's say you have another input. Let's say 7, 8, 6, 7 and 5, 8. So for this particular question, here 1 holds, but here it is 3. So for this particular case, I need to return a false as the output. So how we'll be solving this particular problem is, like we'll be creating 2 stacks. We need to create 2 stacks. Let's say stack A1 and stack A2. Okay. So first thing is, you need to transfer all the queue elements to stack A1. Secondly, transfer all the stack A1 elements to A2. Now, as you remove, or you can say pop, elements from A2 side by side, check what's the difference between consecutive pairs. Right? If it is 1, like absolute difference is 1, if it is not 1, so then we'll simply return false, else will return true. Now this is one use case. And fourth thing is, like after popping, you need to push the elements in the original queue so that it remains the same. Right, so these are the steps, and let's see how we'll be performing these steps with the help of an example. Right, so we have, let's say, this as the input, 1 2 5 6 9 10. Right, I am creating a stack A1, I'm creating another stack A2, and the first thing that I told you was to pop all the elements from my queue and push them into the stack A1. So it will contain 1 2 5 6 9 and 10. Right, now all the elements of A1 to be moved to A2, it will be 10 9 6 5 2 and 1. Now I'll be popping out two elements at a time, let's say 1 and 2, and I'll be checking out the difference between them. 1 minus 2, it will be absolute of 1 minus 2 is equal to 1. So yes, if it is yes, I'll push them into my queue. Now my queue is empty, right? All the elements have been removed. So let's say this is empty. Now I want to insert 1 and 2. I'll insert 1 and 2. Now I'll go and pop out 5 and 6. I'll find out the difference, it is 1. I'll insert them in my queue. Now I'll go and check out 9 and 10. The difference is again 1. I'll add them into my queue, and we are done. As soon as these three are 1, we are not getting any false, so the answer is going to be true, else the answer is going to be false. Right, so I hope you have understood the problem. What we actually need to do, we need to check if the queue elements are pairwise consecutive or not. Pairwise consecutive ka matlab, like for the pair of 2 2, it should have a minimum difference, it should have a difference of 1. matlab consecutive ka matlab both the numbers are together, like 1 2 5 6 9 10. So input that you are given is 1 2 5 6 9 10, so the difference between them is 1 1 1, so answer you need to return is true. Right, what you need to do in this case is you need to create two stacks, stack A1 and stack A2. Firstly, push all the elements from queue to stack A1. Now push all the elements from A1 to A2. Now as you are removing the elements from A2, check two elements at a time. If the difference between them is 1, if the absolute difference between them is 1, keep on pushing and putting them in the queue again. And as soon as the stack is empty, as soon as the queue is full and you haven't got any fallacy matlab if you haven't got any difference greater than 1 or less than 1, it is not 1, so you should return true, else you should return false if you have got the fallacy. Right, I hope this approach is clear, and now let's see how the code of this particular question looks like. So here's the function signature, that is pairwise consecutive we need to calculate, and we are given an input queue. So how we have made this particular queue is, let's say I've initialized the queue of integers and I've pushed the elements 4 5 minus 2 minus 3 11 10 and 5 and 6, and I'll be checking for pairwise consecutive of q. If it is yes, then if the answer comes out to be true, because the return type is boolean, so if the answer comes out to be true, I'll print yes. If the answer comes out to be false, I'll print no, and I'll print all the elements of the queue side by side. So let's see what we did in our particular approach that we discussed. The first thing was that I was creating two different stacks, stack A1 and stack A2. So let me create my first stack of integers A1, and I'll be pushing in until my queue is empty. I'll be pushing in A1 dot push q dot front and then q dot pop. Right now I'll create my stack of integers to, let's say, A2, and while A1 is not empty, I need to empty the entire A1 and put the elements in A2. A2 dot push A1 dot top, A1 dot pop. Okay. After this, what we were doing is, like, now we'll be removing the elements from A2 and we'll be checking if the consecutive difference is 2. So I'll make a bool result. Initial value, let me give it as true. I'll be going inside a while loop until and unless A2 ka size becomes, A2 ka size is greater than 1. A2 dot size is greater than 1. Then I'll simply pop out two elements at a time. Let me say integer x is A2 dot pop, A2 dot top, right, and I'll be popping out A2. Along with that, integer y is equal to A2 dot pop again and A2 dot pop. Right now I'll be checking the difference between A2 x and y. So if at all the absolute difference between x and y is not equal to 1, then I'll put the value of result equals to false. Okay, ji? And I'll be pushing back the elements in my queue. Push x kar diya, q dot push y, and I think this should suffice. Is there anything else that we are missing? We have created one stack A1 while my queue is not empty. I've popped out elements from my queue and pushed them into my stack A1. Then I've created stack A2. A1 ke elements are in A2 now. I'll be popping out two elements at a time from A2 and be checking the absolute difference between them. If it is not equal to 1, I'll make the value of result equal to false, else it is true. Also, side by side, I'll be pushing out x and y into my queue. At the end, what I need to return is return the value of result. I hope this should be fine. Let's try and see if we get the correct answer. There is some expected before pop. This is something that we missed. Yes, so we're getting the answer as yes. That means our queue is pairwise consecutive. The difference between 4 and 5 is 1. Absolute difference between 4 and 5 is 1. Minus 2 and minus 3 is also 1. 11 and 10 is 1. 5 and 6 is 1. So we have successfully solved this problem. Let's try with some other example. Let's say for this case, let me do minus 2 and minus 4. What is the answer coming? So the answer is coming out to be no. Why no? Because now the absolute difference between minus 2 and minus 4 comes out to be 2, which is not equal to 1. Hence the result variable here becomes false and it is automatically returned as false. I hope this question is clear to you, and let's meet in another video and see another question. Let's also touch upon the time complexities of queues. Let's say when I say time complexities of queue, like we have different operations. These operations include accessibility, that is if I want to get any particular element of the queue. Next thing is search, if I want to search any element in my queue. Next thing is insert, if I want to insert any element in the queue. And next is delete, if I want to delete any element of the queue. So there can be different cases. Let's say we generally deal it in the form of best case or the worst case. So we'll see what will be the accessibility of a queue in best case. Like this is my queue. Let's say this is my queue, for example. I have certain elements like 1, 2, 3, 4, and 5. If I want to access any element out of this queue, so I'll have to either pop out other elements, then move to that particular element. So in the best case, you can say that my element which I want to access is present at the first position only, so it will become O of 1, but will not take best case. Let me just name it as average case. In average, on average, we'll make it as O of n only. Let's say my element is here or somewhere else. In the worst case, let's say your element is at the last, again you'll have to traverse over the entire array or the entire queue. Then again your accessibility will be O of n time complexity. When I say search, if you want to search at any particular element in the queue, again you'll have to pop each and every element and see if that element is equal to the required element. For this also, the time complexity becomes O of n. In the worst case also, it becomes O of n, right? If the element is present at the last, let's say the element that we are searching is present at the last, again we'll have to traverse from the starting till end, and we'll have to traverse over n elements. Insert, if I want to insert an element in my queue, let's say I have this particular queue, there's one, like the queue size is 6. If I want to insert an element, I'll simply insert it at the back, at the rear end, and it will take the time complexity of O of 1. In average case also, in worst case also, in best case also, there's no doubt on insertion. So what will be the complexity of deletion? When I say deletion, basically the pop operation I'm doing. So pop operation in the terms of queues is also done in O of 1 only. Like if I want to remove this one, so it is the element which is present at the front end. I know that I can only remove the elements from the front end in a queue. So the complexity in this case would also be O of 1. Here also it will be O of 1, and probably we'll be able to understand how the time complexity in a queue goes on. For space complexity, let's say what will be the space complexity of queue. So when I say space complexity of the queue, so we are creating a queue, so we can create it using an array, or we have also seen we can create it using a linked list. So it will be O of n space. We need to create this particular array of size n or linked list of size n. So we can generalize it by saying that the space complexity of, in general, like in worst case also, you can say it will be O of n in general, right? I hope these complexities part is clear and you have practiced a lot of questions related to queues so that your entire topic can be covered. It's a very, very important topic from the point of view of interviews. Majorly, a lot of questions related to Dequeue. Dequeue is a very, very important topic. Like we have discussed so many problems related to Dequeue, so make sure you are well versed with some more problems related to Dequeue. Generally that involves sliding window, right? So you might have seen that we have done a problem in which we are finding sub-array maximum. So it's a very, very important problem with respect to interviews. Then there was a problem by the name of rotten oranges. So rotten oranges problem is also a very, very famous interview problem, right? Then one question in which we were calculating the distance from the binary, in a binary matrix, from the ones and zeros. So that question is also very, very important. So make sure this topic is revised well. Apart from that, questions relating to BFS of a graph entry. We have discussed the BFS of a tree in this video, but for graph also you need to use it. And if you have a sound understanding of queue, you can easily solve the problems related to BFS in trees. Like a lot of questions in tree will be based upon BFS. In graphs also, major problems are based upon BFS. So BFS is a very important topic, that is breadth first search, right? So make sure you practice these well. Apart from that, we have discussed about the time complexities. So time complexities you need to keep in mind while solving certain problems. Also, there can be some trivial problems that we have discussed, in which we were popping out elements into stack, pushing out elements in queue from the rear end, from the front end. So those questions need to be given a thought. You need to understand like what exactly is the demand of the question, and you need to supply the solution accordingly. So this is also very important thing that you should take into consideration while solving questions related to queues. uh, Apart from that, like most of the things we have covered, so make sure you revise this video once again if you feel any problem, and try making short notes, so that once you are done with the preparation, you can just easily go through the type of questions that we have done, so that the topics are revised in a much easier and efficient way, right? So this was all for this particular video. I hope you people enjoyed learning this extensive course on queue data structure. See you in some other video. Till then, stay tuned.
Hope you all like this amazing video. For more such amazing content, consider liking and subscribing this channel. We'll be bringing some more concepts related to data structures, some more topics like cloud, some more topics like the system design, and much more on this particular channel. So please do subscribe this channel, share this video, and like this video. Along with that, if you people have any doubts, any queries related to anything, don't forget to comment in the comment box, and we'll be more than happy to take all your comments from the comment section. Thank you so much.